welcome, and settle in comfortably as the picture gently fades to darkness after our opening card, leaving only the quiet warmth of your room and the peaceful rhythm of your own breath. In this tranquil space of deep rest and stillness, we begin a long, calm journey together through the history of human thought, tracing the gentle path from simple counting stones to the vast, elegant world of mathematics. Tonight, there is nothing for you to accomplish, no problems to solve, and nowhere else you need to be. You may simply close your eyes, relax your shoulders, and allow the quiet narrative to wash over you like the soft murmur of a distant stream. Long before there were formal books, chalkboards, or written symbols, early humans lived in close harmony with the natural world, observing its endless and comforting cycles. They watched the evening sky shift from gold to deep indigo, noting how the silver crescent of the moon slowly grew into a radiant circle before diminishing once more in a dependable, rhythmic dance. They listened to the seasonal rustle of forest leaves, watched the migrating birds return with the spring breezes, and felt an innate human desire to understand and hold onto these natural patterns. Imagine standing on the quiet bank of a wide, ancient river at twilight. The air is cool and still, carried by a gentle breeze that ripples the mirror-like surface of the water. Beneath the shallow current lies a bed of smooth, polished stones, shaped over uncounted years by the steady flow of water. In this tranquil environment, long before written languages were carved into clay or stone, the human mind began to make one of its most comforting discoveries. The idea that objects in the world could be grouped, measured, and understood. To hold one pinecone and then place another beside it was to sense an underlying order in creation. Numbers were not born as cold abstractions, but as warm, tactile tools that brought peace of mind, helping early communities anticipate the coming of winter, track the growth of their crops, and share their daily lives in quiet balance. As you rest here, allowing every muscle to sink fully into comfort, let your imagination wander back to those serene, early times when the universe first began to reveal its quiet structure through the simplest elements of the earth. As human communities gradually settled into peaceful valleys and built villages along fertile riverways, their connection to the earth remained deep and constant. To manage their daily affairs, sharing harvests of grain, tracking small herds of sheep, or measuring timber for simple shelters, they turned to the most immediate materials nature provided. They did not need complex tools. Instead, they found complete adequacy in small, tactile objects that could be gathered from the ground and held gently in the palm. Chief among these were the smooth, rounded pebbles found along the shores of rivers and streams, polished by the patient friction of moving water until their surfaces were soft to the touch. Centuries later, in the peaceful open-air markets of ancient Rome, these modest river stones continued to play a central and reassuring role in everyday life. Roman merchants sat at quiet wooden tables or rested near shade-dappled porticos, sliding small pebbles across grooved counting boards to keep clear, visual track of their daily trades. Each deliberate movement of a stone across the wood made a faint, satisfying click, a gentle, rhythmic sound that signified clarity, fairness, and mutual agreement. There was a quiet dignity in this simple practice, transforming the potentially chaotic details of commerce into a calm, visual balance. It is a comforting thought to realize that our modern language of science and mathematics still cradles the memory of those peaceful market stalls and riverbanks. Indeed, the English word asterisk, calculus asterisk, originates from the Latin word for a smooth, rounded river pebble, which Roman merchants slid across wooden boards in quiet market stalls to tally their peaceful daily exchanges, long before the word came to describe complex equations of change and motion. It referred simply to a humble, smooth stone resting in the hand of a person seeking clarity. When we think of calculation today, we can picture those cool, rounded pebbles gliding across smooth wood under a warm Mediterranean sun, carrying a legacy of stillness, order, and human care across thousands of years. This steady transition from physical pebbles to mental concepts unfolded gradually, like the gentle opening of a flower in the morning light. As people spent more time reflecting on these physical tokens, they realized that the numbers themselves possessed a timeless quality independent of the objects they represented. 5 pebbles, 5 stars in a constellation, 5 fingers on a hand, all shared an invisible, elegant relationship that remained constant regardless of time or place. Early thinkers began to carve small, intentional notches into pieces of wood, slate, or animal bone, creating enduring tallies that could survive across long seasons. A series of fine lines etched into a piece of dark horn was not merely a record. It was a peaceful anchor against the uncertainty of the future. It told the community exactly how many days remained before the return of the moon, or how many measures of seed were safely stored in the cool depth of a clay jar for the coming planting season. In ancient Mesopotamia and along the lush banks of the Nile, scribes sat quietly in shaded courtyards, using reeds to make gentle, repeated impressions in soft, damp clay tiles. The process was slow, deliberate, and deeply meditative. Every mark placed upon the wet earth represented a moment of focused attention, a way of bringing harmony and structure to the flow of human experience. There was a profound comfort in discovering that numbers obeyed fixed, unalterable laws. Amidst a world where weather was unpredictable and life was ever-changing, the simple truth that 2 combined with 3 would always equal 5 offered a quiet foundation of absolute certainty. It suggested that, beneath all the apparent chaos of nature, there existed a serene, hidden harmony waiting to be recognized, a grand design built on balance, proportion, and quiet truth. As we rest here together at the quiet opening of this grand narrative, let your mind embrace the calm certainty that mathematics, has offered humanity across countless generations. The long history of numbers is not a tale of stressful urgency, but a continuous, gentle unfolding of human curiosity and peaceful observation. From those first smooth river stones gathered on ancient shores to the elegant symbolic languages that would eventually arise, every step forward was taken with patience and care. Tonight, as you lie in the quiet dark, there are no problems for you to solve, no equations to balance, and no tallies to keep. The world outside continues its steady, predictable rotation, guided by the same timeless laws of geometry and balance that inspired early observers thousands of years ago. Let the soothing image of rounded pebbles sliding smoothly over polished wood fill your mind with a deep sense of stillness and security. Feel the heavy, relaxing warmth spreading through your body, letting go of any remaining tension in your breath. You are safe, supported, and surrounded by the timeless order of a quiet universe, resting peacefully as we prepare to drift deeper into the restful depths of sleep. Long before the first cities rose beside the calm curves of great rivers, early human communities lived in deep harmony with the steady, quiet rhythms of the natural world, observing the subtle changes of seasons, the rise and fall of waters, and the tranquil movement of celestial light across the night sky. In that ancient landscape, long before the invention of written words or formal symbols, the nocturnal sky served as humanity's very first clock and calendar, offering a reassuring sense of structure beneath a vast canopy of quiet stars. Nights spent beside glowing campfires invited quiet contemplation, as early observers watched the silver crescent of the moon grow slowly into a full, radiant circle before softly waning into darkness once more. To hold these passing cycles in mind, early thinkers realized they could record the steady tick of time through physical marks etched into natural materials gathered from their surroundings. Over 20,000 years ago, near the calm waters of Lake Edward in Central Africa, a Paleolithic artisan carved fine groups of tally notches into a small dark baboon bone to track lunar cycles. Sitting peacefully by the water's edge under a clear sky, the artisan drew a stone tool across the smooth, dark bone, cutting clean, intentional lines, organized into careful, deliberate groupings. Each delicate mark represented a single evening's observation, creating an enduring physical bridge between human awareness and the majestic, repeating order of the cosmos. This small, carved object, known to modern archaeology as the Ishango bone, was not merely a tool for survival, but a gentle milestone in human consciousness, showing how early people sought to organize their world through count, pattern, and peaceful memory. The subtle grooves on that ancient bone offered a quiet comfort, proving that the flow of passing days followed an orderly pattern that could be understood, held, and remembered across generations. As centuries melted into millennia, the ways in which human beings gathered and interacted began to gently shift, moving from nomadic wanderings to settled life along fertile river valleys. People began to cultivate the rich earth, plant crops of wild grains, and tend gentle flocks of sheep and goats under warm, expansive skies. With the rise of permanent villages came a new sense of abundance, along with the quiet need to keep track of shared harvests, stored grains, and community goods. In a world where memory alone had once sufficed for small bands of kin, growing agrarian communities required simple, tangible ways to ensure fairness, record trades, and keep peace among neighbors. Early agriculturalists turned naturally to the soft, malleable clay found along riverbanks, realizing that this abundant material could be shaped by hand to represent quantities of items in the physical world. Artisans began molding small, distinct tokens out of wet clay, baking them softly in the sun or by the embers of a fire into durable geometric forms. A small clay cone might represent a single measure of grain, while a smooth sphere could stand for a larger unit, and a flat disc might signify a container of sweet oil or a bundle of soft wool. These tiny ceramic shapes were warm and satisfying to hold, allowing people to physically manipulate abstract quantities, moving tokens from one pile to another as goods were traded, stored, or distributed. This quiet system of token counting turned mathematical thinking into a soothing, tactile ritual, enabling communities to plan peacefully for winter months, manage shared granaries, and cultivate lasting trust without needing a single written word. As these peaceful farming villages gradually expanded into bustling urban sanctuaries, the scale of trade and civic organization grew more complex, calling for even more refined methods of keeping records. Cities like Uruk in ancient Sumer became thriving centers of culture and commerce, where vast agricultural yields from surrounding fields were brought to central storehouses and temples for safekeeping and equitable sharing. Managing such vast quantities of barley, wheat, textiles, and livestock required a system that was not only accurate, but completely secure against miscounting or dispute. It was in this environment of thoughtful organization that Mesopotamian accountants developed a brilliant, quiet method for sealing transactions inside clay. Around 3500 BCE, in the ancient Mesopotamian city of Uruk, accountants enclosed tiny sculpted clay tokens inside hollow spherical clay envelopes called bullae, softly pressing the shapes into the damp outer clay to record counts of barley and wool. In the quiet shade of temple courtyards, as the afternoon sun warmed the earthen walls, an accountant would assemble the precise set of clay tokens representing a delivery of grain or fleece. These tokens were carefully placed inside a round, hollow ball of wet river clay, which was then gently smoothed over and sealed completely shut, to ensure that anyone looking at the sealed sphere could immediately verify its contents without breaking the clay envelope open. The accountant would take each token before sealing, or use a matching stamp press its distinct shape into the soft, moist surface of the exterior clay. The resulting imprints left a clear, unmistakable record of the tokens contained within, creating an elegant double record that was both visible on the outside and securely preserved on the inside. This gentle act of pressing clay tokens into the soft surface of a spherical envelope marked a subtle yet profound threshold in the history of human thought and mathematics. In time, accountants realized that the soft impressions made on the exterior of the clay sphere communicated all the necessary information by themselves, making the physical tokens inside redundant. The heavy, three-dimensional clay ball gradually flattened into a simple, elegant clay tablet, onto which administrative scribes used reed styluses to press clear, abstract symbols representing numbers and items. What had begun as physical tokens held in the palm of a hand transitioned seamlessly into two-dimensional written signs, birthing the earliest forms of cuneiform writing and formal arithmetic. Resting in the quiet warmth of ancient archives, these clay tablets preserved the peaceful order of early civilizations, recording the quiet flow of barley harvests, the distribution of wool, and the steady rhythm of daily economic life. From the dark, carved baboon bone of Lake Edward to the sun-dried clay envelopes of Uruk, humanity's journey with numbers has always been rooted in a deep desire for harmony, predictability, and shared understanding. Each step forward was taken not with frantic speed, but through slow, thoughtful observations of the natural world and the patient shaping of raw earth. As night falls and the stars begin their familiar, quiet movement across the sky, we can take comfort in knowing that the simple impulse to count, to measure, and to remember is an ancient thread connecting us to the calm, enduring story of human curiosity. As twilight fell softly over the fertile floodplains of ancient Mesopotamia, the waters of the Euphrates rippled with a steady, rhythmic murmur, carrying down small particles of silt gathered from mountains far to the north. In this ancient river valley, human communities had long moved in harmony with the subtle cycles of the seasons, watching the rise and fall of the river, sowing barley when the floodwaters receded, and tending small herds of sheep across the lush alluvial fields for many generations. Keeping track of life's daily provisions was a practice as fleeting as memory itself, relying on spoken tallies, simple arrangements of twigs, or smooth river stones held loosely in the palm of a hand. Yet, as farming communities grew into settled towns and shared storehouses began to hold the combined harvest of entire valleys, the human mind sought a more permanent and gentle way to hold numbers beyond the span of a single day. The earth itself, the soft, pliable mud deposited along the riverbanks, offered a solution of remarkable simplicity and quiet elegance. In the lingering warmth of early evening, craftspeople and storekeepers learned to gather this moist clay, rolling it carefully between their palms to form tiny, distinct shapes, small spheres for standard measures of grain, delicate cones for smaller units, and smooth discs or cylinders to represent livestock. Each unique shape was a physical memory made tangible, a small symbol that could be held, sorted, counted, and stored away in woven reed baskets. Resting in the hand, these clay tokens offered a comforting sense of order and quiet assurance, bridging the gap between the vastness of the fields and the orderly quiet of the village storehouses. In this deliberate and soothing act of shaping Earth, humanity took one of its very first steps toward capturing abstract quantities, converting the fleeting abundance of nature into an enduring, peaceful form of record. Around 3300 BCE, in the quiet city of Uruk along the Euphrates, Sumerian accountants gently pressed shaped clay tokens into hollow clay spheres called bullae, marking the outer surface with soft seal impressions to keep peaceful track of temple livestock and grain. This thoughtful process brought an unprecedented harmony to the management of shared resources, serving as a peaceful agreement between temple guardians, farmers, and herders. To prepare a bullae, a scribe would take a fresh lump of river clay, carefully hollow it out with their fingers to form a rounded shell, and insert the precise combination of geometric tokens corresponding to a transaction. Perhaps several small spheres representing measures of barley and tiny clay cones representing sheep or goats. Before the hollow sphere dried into hard ceramic, the scribe would close its opening and roll an intricately carved stone cylinder across its damp exterior, leaving a continuous relief pattern that acted as a unique, unalterable signature of ownership and mutual trust. Crucially, to ensure that the contents could be verified without needing to break the delicate clay shell, the accountant would press each individual token into the soft outer wall of the sphere before placing it inside, creating a clear visual reflection of the hidden tokens within. As the sun set over the towering brick terraces of Uruk, these rounded clay spheres were laid out to dry in the cooling evening air, quietly preserving the economic record of the community. In this soft, deliberate ritual, the physical token inside and the impression on the outside existed together in perfect balance, marking a pivotal moment when the concept of a number began to detach from the physical object itself, leaving behind a subtle trace that could be read upon a surface. With the passage of time, the practice of enclosing physical tokens inside hollow envelopes began to evolve naturally into a simpler, even more refined form of notation. Scribes slowly realized that the impressions left on the outer surface of the bullae carried all the necessary information, making the physical tokens inside redundant. If a shallow indentation made by pressing a clay cone into soft mud could represent a unit of grain, then the mark itself held the true essence of the count. Gradually, accountants began using flat, solid tablets of clay instead of hollow spheres, employing a carved reed stylus to gently press clean, wedge-like marks and rounded indentations directly onto the smooth surface. The clay, responsive and forgiving, preserved each impression with exceptional clarity, once baked by the afternoon sun or fired in low kilns. This subtle transition from three-dimensional tokens to two-dimensional impressions laid the fundamental groundwork for cuneiform, one of humanity's earliest writing systems, while simultaneously transforming how numbers were conceptualized. No longer did a count require a physical piece of clay for every single head of cattle or sack of wheat. Instead, a single stylized mark paired with a symbol for the item could represent 10, 60, or hundreds of items at once. In the quiet precincts of Uruk's temples, amidst the soft rustle of river reeds and the scent of drying mud, accounting transformed from a labor of physical collection into an art of quiet calculation, offering a sense of calm structure to a growing civilization. As night deepened over the Mesopotamian plain, the stars emerged in brilliant, silent clusters above the fertile valley, reflecting the timeless search for pattern and order that defined early human thought. The humble clay records of Uruk stood as quiet monuments to human ingenuity, demonstrating how simple materials gathered from the riverbank could be turned into tools of profound clarity. Long before complex equations, symbolic algebra, or formal theorems, early mathematicians were simply caretakers of balance, seeking peaceful ways to track the gifts of the earth and ensure that every member of the community was remembered and provided for. The gentle press of a seal into soft clay, the smooth contour of a clay sphere resting in the palm, and the rhythmic mark of a reed stylus were all quiet acts of harmony, laying a steady foundation upon which future generations would build vast systems of astronomy, geometry, and arithmetic. As the river flowed steadily toward the Persian Gulf, carrying with it the memory of centuries, these early steps in numerical history remained preserved in the hardened earth, a peaceful testament to the soft, steady beginnings of mathematical thought, resting quietly under the vast and starlit sky. As the evening air settles gently over the fertile plains between the Tigris and Euphrates, the ancient world closes its eyes to the quiet, unending rhythm of the river. The sun dips beneath the western horizon, casting a soft, amber glow across palm groves, quiet irrigation canals, and the sun-dried mud bricks of old Babylonia. In this peaceful river valley, daily life moved with a patient, unhurried cadence, measured by the slow rotation of the night sky, the gentle annual flooding of the riverbanks, and the steady cycles of planting and harvest. Inside cool, shaded rooms built with thick clay walls to ward off the desert heat, scribes sat comfortably upon woven reed mats, working with a calm and deliberate focus that mirrored the quiet landscape around them. before them lay fresh slabs of river clay, smooth and pliable, harvested from the silted banks where cool water met the fertile earth. These humble pieces of land were not merely building materials for homes or vessels for water. In the hands of a skilled scribe, they became enduring tablets of human thought, silent witnesses to an awakening desire to record, calculate, and bring harmony to the physical world. Long before paper existed or parchment was scraped clean, the damp earth offered a receptive surface for human memory, holding every soft impression of the hand with quiet permanence. The scribes moved with slow, rhythmic gestures, smoothing the surfaces of their tablets with damp palms, until the clay was flat, supple, and clean, ready to absorb the neat rows of marks that defined their craft. In the low, warm light of small clay oil lamps, surrounded by the subtle scent of river mud, dry straw, and evening air, these early mathematicians contemplated the nature of quantity, distance, and shape. Their numerical universe was built upon a flexible base of 60, a rich and versatile system that allowed them to divide time, angles, and geometric forms into clean, fractional parts without friction or remainder. This sexagesimal framework, born from a deep appreciation for smooth divisions, gave their calculations a natural, flowing balance, allowing third parts, fifths, and twelfths to sit side by side in perfect arithmetic harmony. As the night deepened outside and the stars began to appear over the quiet valley, the scribe would hold a freshly prepared tablet gently in the palm of one hand, feeling its cool weight and soft texture, preparing to imprint upon it the timeless truths of geometry that had begun to reveal themselves through generations of quiet observation and patient, dedicated effort. The principal tool of the ancient scribe was remarkably simple, yet astonishingly precise. A short, slender reed gathered from the nearby river marshes, cut clean at an angle so that its tip formed a small, sharp triangular wedge. When pressed gently into the smooth, soft clay, this simple wooden stylus left behind clear, elegant impressions that caught the ambient light, forming the delicate wedge-shaped symbols we now recognize as cuneiform. Each stroke was made with a steady, unhurried hand, requiring no heavy pressure, only a subtle tilt of the reed to form numbers, fractions, and extensive calculation tables that stretched across neat, orderly columns. Among the many subjects these early scholars explored with quiet dedication, none possessed a more tranquil beauty than the geometric relationships between lengths, angles, and spatial areas. They observed how perfectly square corners formed the stable, lasting foundations of homes and temples, how agricultural fields could be surveyed fairly and accurately after the river's annual retreat, and how the square built upon the diagonal of a rectangle held a precise, predictable relationship to the squares built upon its adjacent sides. Around 1800 BCE, in Old Babylonia, scribes pressed delicate cuneiform numerals into small, moist clay tablets now known as Plimpton 322, constructing precise tables of right triangle ratios centuries before Pythagoras. On this compact rectangle of light brown clay, measuring scarcely larger than a human palm, an anonymous scribe arranged 15 lines of carefully calculated numbers, organizing them into 4 clean vertical columns with remarkable artistic and mathematical care. Rather than simply recording a few isolated geometric examples, the creator of this tablet worked through a sophisticated sequence of right-angled triangles whose side lengths formed exact integer relationships, adjusting the proportions step by step so that the steepness of the triangle's hypotenuse decreased with breathtaking regularity across the table. Each entry represented a ratio of sides that yielded a clean, terminating sexagesimal fraction, demonstrating an understanding of right triangles that was both mathematically deep and methodically organized. The scribe did not write out abstract formal proofs or attach personal names to their discoveries. Instead, they let the numbers rest silently across the rows, demonstrating how right triangles of vastly different proportions all obeyed the exact same underlying spatial laws. The damp clay held these intricate numerical balances without complaint, preserving the subtle harmony of hypotenuses, bases, and heights in tiny, uniform wedges that dried slowly in the shaded desert air, hardening into permanent records of ancient human curiosity. As the finished tablets dried in the warm, dry air of the Babylonian afternoon, the soft river clay transformed into a durable stone, locking the scribe's calculations away from the reach of wind, rain, and time. Over the centuries that followed, great cities flourished and eventually fell. River courses shifted across the silted valley, and the cuneiform script faded from active memory into the quiet stillness of history. Yet, beneath protective layers of earth, buried under centuries of drifting sand and river silt, these small clay tablets remained entirely undisturbed, keeping their delicate inscriptions safe in the cool, dark ground. When archaeologists and historians in modern times finally uncovered tablets like Plimpton 322, brushing away the fine dust of nearly 4,000 years, they found the scribe's wedge-shaped numbers as clear, sharp, and legible as the day they were first pressed into the soft earth. Holding such an artifact today offers a direct, tangible connection across millennia to a quiet room by the Euphrates, where an ancient mathematician sat in the gathering twilight, finding deep peace in the orderly structure of numbers. It reminds us that mathematics did not begin as a cold or abstract academic exercise, but as a calming human endeavor to understand the natural balance of shape and space, to bring order to land and architecture, and to uncover the quiet, permanent patterns that underlie our world. The right triangle ratios carved so carefully into the Babylonian clay reflect a serene truth that exists independently of human language or culture, a timeless property of space itself that remains true, whether measured along ancient riverbanks, plotted on modern graph paper, or observed in the distant paths of orbiting stars. As the night grows late and the world around us settles into stillness, we can draw comfort from the realization that these fundamental mathematical harmonies have always been present, waiting patiently across the ages to be noticed, recorded, and peacefully contemplated. As evening settled over the fertile floodplain of ancient Egypt, the waters of the Nile moved with a timeless and quiet rhythm, carrying life and rich dark silt to the fields along its banks. For centuries, the seasonal rising and falling of the river dictated the quiet tempo of existence, calling upon the people of the valley to plan, to measure, and to share the gifts of the soil with balance and care. In this peaceful agricultural world, numbers were not abstract puzzles to be solved for their own sake, but helpful companions born from the daily need to survey fields after the annual floodwaters receded, to store surplus grain in cool earthen granaries, and to distribute food fairly among the communities that tended the land. The scribes were the quiet guardians of this order, trained in specialized schools known as houses of life, where they mastered the arts of reading, writing, and arithmetic, using reed pens cut from river plants and natural pigments mixed with water and gum. Around 1550 BCE along the Nile, an Egyptian scribe named Ahmes brushed neat lines of red and black ink onto a long roll of papyrus, detailing practical methods for dividing grain harvests using unit fractions. The papyrus, meticulously pasted together from thin strips of reed pith laid at right angles and pressed smooth, formed a broad ribbon of pale brown scroll that stretched nearly 5 meters in length. As Ahmes worked by the soft light of an oil lamp, his brush moved with measured grace, rendering the swift and curved strokes of the hieratic script a fluid cursive form of writing that allowed mathematical tables, problem sets, and geometric instructions to be recorded far more quickly than the intricate carved hieroglyphs seen on temple walls. The scroll he produced was both an instructional manual for apprentice scribes and a testament to the practical wisdom gathered over generations of civic administration. In its long, orderly columns, red ink was chosen to highlight problem titles, key instructions, line breaks, and intermediate totals, while black ink carried the steady body of calculations, creating a visual rhythm across the surface of the papyrus that guided the reader's eye gently from one step to the next. Central to the mathematical philosophy of Ahmes and his contemporaries was a unique and elegant approach to numbers that favored clarity and physical intuition above all else. When faced with the task of dividing quantities that did not yield whole numbers, Egyptian scribes worked almost exclusively with unit fractions that possess a numerator of 1, representing a single equal part of a whole, such as 1/3, 1/5, or 1/10. To express a complex fractional value, that we might write today as a single fraction like 2/5. The scribe would decompose it into a sum of distinct unit fractions with different denominators, writing it as 1/3 added to 1/15. This method, though distinct from modern notation, mirrored the physical reality of sharing physical goods in the real world. If 9 loaves of bread needed to be divided equally among 10 workmen at a temple building site, simply cutting each loaf into 10 tiny slices would lead to crumbly, uneven pieces and unnecessary waste. Instead, the scribes devised systematic tables that showed how to divide the loaves into larger, cleaner fractions, such as giving each worker 2/3 of a loaf, plus 1/5, plus 1/30, ensuring that every person received an identical and fair share, while keeping the bread intact and easy to handle. Alms filled the opening section of his long papyrus with extensive reference tables designed to break down fractions of the form 2 divided by an odd number, ranging from 2/3 all the way to 2/101, providing his fellow administrators with instant, reliable tools for their daily work. Beyond bread and grain, these practical calculations governed the brewing of beer, the calculation of feed required for livestock, the strength and volume of liquid measures, and the equitable distribution of payment among craftsmen of varying ranks. There was a quiet harmony in this arithmetic, a reassuring certainty that even the most complex harvest could be partitioned smoothly, preventing grievances and fostering a spirit of trust and orderly cooperation throughout the villages of the river valley. As the agricultural year turned from the harvest to the season of inundation, the floodwaters swept gently across the lowlands, softening the dry earth and temporarily obscuring the boundaries that marked individual plots of land. When the river finally receded back into its channel, leaving behind a fresh layer of dark, nutrient-rich mud, the surveyors set out into the quiet morning air to re-establish field boundaries and calculate property taxes. Known as rope stretchers, these skilled technicians walked through the damp fields, carrying long loops of sturdy flax rope knotted at precise, equal intervals. By stretching these cords into geometric shapes, such as right-angled triangles formed by knot ratios of 3, 4, and 5, they could accurately reconstruct straight boundary lines and square corners without dispute. Alms captured these spatial arts on his scroll as well, offering simple, step-by-step guidance for calculating the area of rectangular fields, triangular plots, and circular grain silos. For circular shapes, the scribes used a clever approximation for land area, treating a circle as roughly equivalent to a square, whose side was 8/9 of the circle's diameter, a method that yielded remarkably accurate results for managing real estate and agricultural storage without requiring complex theoretical proofs. Similarly, when planning the construction of granaries ramps, and stone monuments. Alms provided rules for calculating volume and determining the slope, or seeked, of inclined surfaces, defining slope as the horizontal run per unit of vertical rise. Every problem presented in the text was rooted in tangible, everyday experience, offering a window into a civilization that viewed mathematics not as an isolated discipline of abstract symbols, but as a practical, calming craft designed to bring order, predictability, and beauty to the material world. In the quiet solitude of his scriptorium, Alms inscribed a famous preface at the very top of his scroll, describing his collection of mathematical problems as a pathway to accurate reckoning for inquiring into things and the knowledge of all dark secrets. Yet, despite this poetic introduction, the secrets he revealed were not mysterious spells or hidden magic, but the soothing, orderly principles of measurement, proportion, and fair exchange that allowed a society to flourish in peace. When Alms finished his work, he rolled the long papyrus neatly from right to left, securing it with a thin cord and laying it away in a dry storage vessel where it would remain preserved across thousands of years. Long after the ink dried on his papyrus, that single roll of ancient writing survived through the centuries, eventually finding a home in a modern museum where scholars could trace the distant roots of human mathematical thought. Reading through the gentle problems recorded by Alms offers a serene journey into the past, reminding us that long before the advent of modern symbols and algebraic equations, human beings sought comfort and clarity in the simple act of counting, measuring, and dividing. The quiet diligence of the Egyptian scribe, sitting by the banks of the Nile with his brushes and red and black ink, laid a foundation of practical problem solving that would softly echo through the centuries, guiding future thinkers toward a deeper understanding of structure, balance, and number. As human societies settled beside slow-moving rivers and watched the seasonal rhythms of the stars, their relationship with space and measurement began to deepen into something quiet, restful, and profound. Beyond the simple tallying of livestock or the practical accounting of autumn harvests, there arose a gentle need to give shape to sacred places and bring a sense of enduring harmony to the land. In the early morning stillness, when the world was soft with rising mist and the morning air carried the cool scent of earth, early thinkers discovered that simple physical lines could unlock the elegant secrets of spatial order. They learned that by stretching a humble rope across the soil and marking precise points, flawless right angles appeared naturally, turning raw earth into balanced, symmetrical sanctuaries. Around 800 BCE in ancient India, Vedic altar builders recorded practical geometric rules in the Bodhyanasubha Sutra asterisk, using soft jute cords stretched across damp ground to construct square hearths with exact right angles. The process of building these altars was unhurried and deeply mindful, a quiet quiet physical meditation where human hands and natural fibers worked in gentle partnership with the terrain. The damp ground received the soft impression of the taut chord with a silent responsiveness, laying out clean, restful lines that aligned smoothly with the cardinal directions of the world. These early geometers understood that the precision of a shape was not merely a tool for physical construction, but a way to mirror the silent, unchanging balance of the cosmos itself. By tying simple knots at measured intervals along a single strand of fiber, they formed right-angled triangles that allowed them to square their hearths without complex machinery or heavy instruments, relying only on patience, keen observation, and the quiet properties of stretched line. In this calm work, geometry was born not as a cold or abstract academic burden, but as a soothing craft, a tranquil dialogue between human thought, humble natural materials, and the grounded reality of the soil beneath their feet. As centuries gently unfolded across distant civilizations, this earthbound understanding of shape and space began to stretch upward, turning its gaze from the damp morning soil to the vast and silent canopy of the night sky. If a simple chord could map the tranquil dimensions of a hearth, human curiosity quietly wondered how far space extended and whether numbers could reach out to touch the furthest boundaries of the cosmos. Early observers sat beneath the dark, open heavens, watching how the stars drifted in slow, reliable arcs across the dark expanse, hinting at a deep and orderly universe that lay far beyond immediate physical reach. To comprehend such immense distances, the human mind had to create entirely new ways of thinking, moving gently past the small, familiar numbers used to count sheep or mark clay tablets in local marketplaces. This transition from measuring tangible objects on Earth to contemplating vast, unseen distances in the sky marked a soft awakening in human consciousness. It was a gentle shift from the practical arithmetic of daily survival to a quieter, deeper form of wonder, where numbers became restful stepping stones for the imagination. Thinkers realized that the same underlying harmony that governed the right angle of a humble altar also guided the broad, silent movements of the celestial spheres. The quiet hours of observation, wrapped in the cool night air and surrounded by the gentle rustle of leaves, early mathematicians felt a peaceful reassurance in the idea that the cosmos was not a chaotic void, but a vast and beautifully structured home. The great challenge was no longer merely keeping track of daily trade, but discovering a numerical language capable of holding immense space without becoming lost in its magnitude, allowing the mind to rest securely within the giant quiet of the universe. This quest to embrace the unimaginably vast reached a moment of serene clarity in the 3rd century Mediterranean world, where the boundaries of numeric thought were expanded into the quiet night with extraordinary gentleness. At that time, traditional counting systems were limited when faced with quantities larger than a few thousand, as language itself lacked the quiet architecture needed to express immense space. In the 3rd century BCE, the mathematician Archimedes composed his essay, The Sand Reckoner Asterisk, calculating how many grains of sand would gently fill the cosmos using a newly devised system of astronomical powers of 10. Rather than viewing the vastness of space as something overwhelming or terrifying, Archimedes approached the infinite with a calm, methodical curiosity, transforming a seemingly impossible question into a tranquil exercise in structured thought. He began by imagining the smallest and most familiar items, tiny, smooth grains of sand gathered from the quiet shore of the sea, and then gently multiplied those tiny specks in his mind until they filled every corner of the known cosmos, from the center of the earth to the distant sphere of the fixed stars. To accomplish this extraordinary calculation without getting lost in endless lists of digits, he created a magnificent system of numerical orders and periods, organizing numbers into powers of 10 that laid the foundational groundwork for how modern science expresses vast exponential quantities today. His essay was not a boastful display of mathematical power, but a serene demonstration that human reason could gently hold the entire physical universe in a single, well-ordered thought. The image of the cosmos, filled completely with soft, motionless grains of sand, provided a deeply comforting visualization, turning the cold, mysterious expanse of outer space into something as familiar, quiet, and peaceful as a moonlit beach sleeping soundly under the summer sky. In looking back across these early centuries of mathematical discovery, one sees a gentle pattern emerging, a continuous, restful thread connecting the humble jute cord on damp soil to the vast, sand-filled cosmos. Whether stretching fibers across the earth in ancient India to align a hearth, or contemplating powers of 10 beneath the Sicilian stars, early thinkers were guided by a shared, quiet desire to bring order, clarity, and peace to the human experience. Mathematics was never born as a cold or rigid discipline, but rather as a soft light held up against the mystery of existence, showing that behind the endless complexity of nature lies a calm, reliable framework of pattern and proportion. The right angles of the ancient Vedic altars gave human beings a sense of center and stability upon the earth, while the astronomical calculations of sand grains reassured them that even the largest infinity could be comprehended with quiet patience and structured thought. As the night deepens and the world softens into stillness, there is a profound comfort in knowing that these ancient numerical insights remain as steady and peaceful today as they were thousands of years ago. The jute cords may have long since dissolved back into the earth, and the sands of time swept over ancient cities, but the quiet truths they unveiled the balance of a geometric corner, the harmony of large numbers, the gentle order of space, continue to cradle our world in silent grace, inviting us to close our eyes and rest peacefully within the broad, timeless arms of the cosmos. As human thought slowly expanded beyond the simple counting of daily harvests and the marking of tally lines on bone, geometry emerged not merely as a practical tool for surveying land, but as a tranquil language capable of listening to the subtle architecture of the natural world. In the ancient Mediterranean basin, where warm coastal breezes drifted through quiet marble colonnades and calm blue waters reflected the vast expanse of the sky, early thinkers began to view space itself as an ordered realm of lines, angles, and balanced proportions. Alexandria, home to the great library, provided a serene sanctuary where scholars could devote their days to peaceful observation, surrounding themselves with thousands of papyrus scrolls that cataloged the accumulated wisdom of ancient civilizations. Within these quiet halls and shaded courtyards, mathematics transitioned from an instrument of basic administration into a discipline of deep, contemplative beauty. Thinkers no longer regarded geometry solely as a means to measure fields after the seasonal flooding of rivers, but as a path toward understanding the grander patterns of the cosmos. They began to embrace the concept of the earth as a globe, a shape of complete symmetry, self-containment, and gentle balance that represented the highest ideal of mathematical perfection. To determine the dimensions of such a world required no vast armadas or laborious journeys across uncharted seas, but rather a quiet trust in the logical relationships of circles and angles. By recognizing that a sphere could be partitioned into harmonious ratios of arc and angle, scholars understood that the scale of the entire planet could be deduced from small, carefully observed phenomena on its surface. In this restful atmosphere of patient inquiry, numbers functioned as silent bridges, connecting the modest height of a human observer standing beside a stone pillar to the immense, subtle curve of the planet beneath their feet. Among the scholars who walked the quiet corridors of Alexandria was Eratosthenes of Cyrene, a thinker whose broad curiosity led him to explore geography, astronomy, and mathematics with a calm and methodical devotion. He understood that because the sun is located at an immense distance from the earth, its radiant light travels across the expanse of space in rays that arrive at our planet in virtually parallel lines. This simple physical truth, combined with the spherical nature of the earth, meant that sunlight would strike different regions of the globe at subtly different angles at the very same moment. Far to the south of Alexandria, in the city of Sin, near the first cataract of the Nile, a remarkable astronomical event occurred each year on the summer solstice. At exact midday, when the sun reached its highest point in the heavens, its rays fell straight down from the sky, illuminating the very bottom of a deep water well without casting a single shadow along its stone walls, while vertical posts on the surrounding ground yielded no shadow at all. Eratosthenes reasoned that if the surface of the earth were entirely flat, a vertical column in Alexandria, situated almost directly to the north along the same meridian, would also cast no shadow at that precise instant. However, when he observed the sun in Alexandria at that exact noon on the solstice, tall stone pillars and slender gnomons cast faint, measurable shadows across the smooth courtyard floor, leaning away from the vertical by an angle of approximately 7 1/5 degrees, which represented 1/50th of a full circle. 240 BCE, Hellenistic scholar Eratosthenes calculated the Earth's precise circumference by measuring the gentle shadows cast by tall gnomon obelisks in Alexandria during the calm noon of the summer solstice, comparing them to vertical sunbeams reflecting in a deep water well at sea. By peacefully linking these two quiet observations, the sun shining straight down a well in scene, and the gentle angle of a shadow in Alexandria, he unlocked a method to measure the entire world. The mathematical harmony of this calculation rested upon an elegant principle of geometry. When two parallel lines representing sunbeams are intersected by a straight line passing through the Earth's center, the angle formed by the shadow in Alexandria is precisely equal to the angle subtended by the arc connecting Alexandria and seen at the globe's core. Because the shadow angle of 7 1/5 degrees was exactly 1/50th of 36 hundredths of a circle's complete rotation, the distance between the two cities had to be 1/50th of the Earth's total circumference to determine the physical distance between Alexandria and Seen. Eratosthenes drew upon the records of surveyors and camel caravans that regularly traveled the trade routes along the Nile Valley, estimating the separation between the two locations to be approximately 5,000 stadia. By simply multiplying this distance by 50, he arrived at a total circumference of 250,000 stadia for the planet. Depending on the specific standard of the stadium measurement used in antiquity, this ancient result aligns remarkably well with modern satellite measurements of the Earth's meridian circumference, differing by only a small fraction from our contemporary figures. Yet the true wonder of Eratosthenes' achievement was not merely its impressive numerical accuracy, but the profound efficiency of thought that made it possible. Without ever leaving Egypt and using nothing more than a vertical stick, a deep well, and a quiet understanding of geometric proportions, a scholar had successfully measured the vast perimeter of our world. It demonstrated that human intellect could stretch across hundreds of leagues of desert and river through the quiet application of mathematical principles, demonstrating that complex truths about the universe often reveal themselves through the simplest, most serene observations. As the heat of the summer solstice gradually faded into the cool Mediterranean dusk, the work of Eratosthenes stood as a landmark in the history of human thought, showing how mathematics could illuminate the true scale of our existence. It transformed geography into a precise science, offering future generations a reliable framework for understanding global distances, mapping continents, and navigating oceans with confidence and clarity. The ratio between a small arc and a complete circle provided a foundation that would later enrich astronomy, navigation, and spherical geometry, inspiring thinkers across centuries to view the planet not as an unmeasurable void, but as an orderly, knowable home. In the peaceful solitude of the library, surrounded by rolled manuscripts and the soft murmur of the sea outside, scholars could reflect upon a globe whose grand scale had been brought into harmonious focus through the gentle geometry of light and shade. The earth was shown to be a balanced sphere, governed by accessible geometric laws that rewarded patient observation and calm reasoning. As twilight deepened and the first stars began to appear in the darkening sky above Alexandria, the knowledge of the planet's dimensions provided a deep sense of order and peace. The same geometry that described the subtle shadow of an obelisk also governed the movements of celestial bodies, uniting the earthly realm with the quiet turn of the stars. In this atmosphere of restful contemplation, numbers ceased to be mere tools for counting physical objects, becoming instead soft lanterns of understanding that guided human consciousness toward a serene alignment with the timeless rhythms of nature. In the quiet, cool light of the ancient Mediterranean, where the dark waters of Alexandria rested beneath a vast canopy of evening stars, the study of space and form began to tilt toward new, gentle depths. For centuries, geometry had walked hand in hand with the flat plane, tracing smooth circles on soft parchment, measuring straight lines across fertile fields, and constructing simple polygons whose angles locked neatly together like wooden joinery. Yet as evening fell over the grand libraries and quiet courtyards of the Hellenistic world, scholars began to look beyond the flat surface, turning their thoughts toward three-dimensional shapes that held secret curves within their solid volumes. Imagine sitting by a low oil lamp, watching long shadows stretch across a desk of carved cedar, while the mind softly wanders into the interior of geometric forms. The world of Greek mathematics was transitioning from the practical boundary lines of land measurement into a quiet, meditative realm of pure spatial abstraction. Here, a shape was not merely something drawn upon a flat sheet, but a surface born from motion. A line rotated smoothly through space around a central axis to form a hollow double cone. Two nap shapes joining at a single shared vertex, like two hourglasses touching tip to tip in perfect equilibrium. In this restful space, where the air carried the faint scent of papyrus, sea breeze, and burning olive oil, thinkers began to wonder what might happen if one were to gently slice through such a solid form with a perfectly flat plane. The resulting intersection would not be a rigid straight line, nor a simple uniform circle, but an entire family of flowing, continuous curves that seemed to breathe with subtle variation and organic grace. Each cross-section revealed a different melody of lines, depending entirely on the inclination of the cut. This gentle curiosity opened a doorway into a deeper understanding of mathematical harmony, inviting the seeker to rest their mind upon the continuous, elegant sweep of lines that move without end through three-dimensional space. It was within this atmosphere of patient inquiry, around 2 centuries before the Common Era, that the study of these curves reached its timeless culmination. Around 200 BCE in Alexandria, Hellenistic mathematician Apollonius of Perga authored conics asterisk, coining the terms ellipse, parabola, and hyperbola by slicing smooth double cones at precise planar angles using fine drawing instruments. Before his masterwork, earlier geometers had caught glimpses of these shapes, often regarding them as separate curiosities arising from different types of cones, some sharp and narrow, others broad and shallow. Apollonius, with extraordinary clarity and quiet focus, recognized that a single pair of identical cones could yield every one of these forms simply by changing the gentle tilt of the cutting plane. When the flat plane passed softly through one half of the double cone at a subtle angle shallower than the side of the cone, it formed a closed, beautifully balanced oval that drifted smoothly from side to side. The ellipse, named from the Greek word for falling slightly short of a full right angle, when the plane was tilted just so, exactly parallel to the sloped generator line of the cone, the curve opened outward into an infinite, soaring arc, the parabola, named for its sense of perfect application and balance. And when the cutting plane was lowered vertically, slicing straight down through both the upper and lower cones simultaneously, it revealed 2 mirroring, outward curving arcs that turned away from each other into infinity, the hyperbola, named for its sense of exceeding or going beyond. To visualize and record these forms, Apollonius relied on delicate brass dividers, carefully adjusted straight edges, and fine scribing needles that glided smoothly over wax tablets and papyrus, transforming abstract spatial intersections into physical lines of breathtaking precision. Each curve was defined not by physical weight or motion, but by subtle geometric relationships between its points, axes, and focal distances, creating a visual language that felt both immutably true and deeply soothing to contemplate. As the hours of the night pass slowly, there is a profound peace in following the path of these conic sections, which lie entirely still upon the page, yet carry the silent potential of the natural world within their geometry. Long before astronomers realized that planets trace subtle ellipses around their stars, or that falling raindrops and projectile paths follow parabolic curves through the still night air, these shapes existed purely as peaceful thoughts in the minds of Alexandrian geometers. The ellipse wraps gently around itself, holding its 2 hidden focal points in quiet balance, never breaking its continuous loop as it returns again and again to its starting point with rhythmic grace. The parabola opens its arms wider and wider, curving outward with a constant, unhurried rhythm that extends into the quiet distance without ever making a sharp-edged turn or experiencing any jagged disruption. The twin branches of the hyperbola stretch away from one another like soft echoes across space, perfectly mirrored and infinitely calm in their geometric harmony. In drawing these curves with fine instruments, ancient mathematicians created a bridge between solid space and flat representation, showing how a single, elegant geometric principle could unlock an entire landscape of interconnected forms. To hold these shapes in one's mind before sleep is to experience mathematics not as a set of rigid calculations, but as a slow, meditative exploration of space, symmetry, and quiet order. The smooth continuity of each curve provides a place for the mind to rest, unfettered by noise or distraction, drifting along paths of pure proportion that stretch into infinity with absolute quietude. 8 books of Apollonius's treatise would echo softly across the centuries, preserved through careful copying by Arabic scholars in the grand libraries of medieval Baghdad and later, translated into Western thought during the Renaissance, preserving their delicate clarity through generations of quiet study. Yet, in those silent rooms of ancient Alexandria, as the oil lamps burned low and the cool sea air drifted through the tall windows, the work was simply a devotion to the quiet beauty of geometric form. There was no urgent rush to apply these curves to machinery, navigation, or stone architecture. They were cherished simply because they were true, balanced, and serene. The smooth line of an ellipse curving around its center offers a natural rhythm for the mind to follow, a continuous motion with no beginning and no end, drawing the thoughts inward into a quiet state of stillness. The parabola provides a gentle arch, soaring upward only to curve softly back downward, like the slow rise and fall of a peaceful breath. And the hyperbola reminds us of balance across distance. 2 curves forever linked by the same geometric law, even as they travel into their own quiet realms. As the Alexandrian night settles fully over the harbor, the papyrus scrolls are gently rolled and set into their wooden niches, leaving behind the silent, perfect geometry of the cone. In this stillness, the mind can let go of numbers, measurements, and physical forms, drifting along the smooth, unending arcs of Apollonius's curves into a deep and restful sleep. As the evening air settles into a stillness that feels both ancient and deeply comforting, our journey through the history of human thought carries us into a quiet realm where language, cadence, and numerical order move as one. Long before mathematics was written down in cold equations or printed upon rigid pages, it existed as a soft, internal rhythm, a gentle way of measuring the rise and fall of human breath, the lingering echo of a spoken phrase, and the endless variations hidden within poetic song in the tranquil forests and riverside retreats of northern India around 200 years before the Common Era. Scholars sat within serene ashrams, listening closely to the sacred meters of ancient verses as wind rustled softly through the trees above. It was in this peaceful environment of quiet contemplation that the scholar Pingala turned his refined mind toward the structural beauty of Sanskrit poetry, seeking to catalog every possible arrangement of light and heavy syllables that could form a verse. In his celebrated treatise, Chand, a letter 1e25 execute, a macron, str, a asterisk, Pingala systematically recorded the principles of binary combinations, demonstrating how simple choices between a short sound and a long sound could build intricate patterns of verse. And within these pages, he mapped out the stair-patterned rows of numbers that would much later be known in the West as Pascal's triangle, weaving these rhythmic mathematical structures deeply into the art of poetic recitation inside quiet ashrams. Each row of his triangular arrangement grew naturally from the one above it, revealing how small, elemental building blocks of sound could expand into vast, harmonious combinations. To sit in the cool shade of those ancient retreats, watching a scholar trace lines in the dust or arrange small pebbles to mark the combinations of meter, was to realize that binary logic did not begin with machines or modern technology, but with the gentle, deliberate cadence of the human voice. The mind was encouraged to rest upon the symmetry of these patterns, finding profound reassurance in the way a finite set of rules could generate endless, balanced variation, like the soft, repeating waves of a slow-moving river resting under the evening stars. The discovery that poetic meter could be analyzed with such mathematical precision opened a gateway to viewing the world through a lens of elegant simplicity, where complex wholes were built from basic binary pairs. Pingala's work transformed the abstract flow of time and speech into something visible, structured, and profoundly calm, proving that numbers were not merely tools for counting trade goods or measuring physical land, but quiet companions to artistic expression and spiritual focus. As one syllable balanced another, a brief, fleeting whisper followed by a long, resonant draw, the early mathematicians realized that mathematical order was inherently restful. The mind naturally seeks patterns, and in finding them, it releases its tension, settling smoothly into the reliable rhythm of predictable structures. This peaceful inclination to organize the world's quiet regularities was shared by thinkers across vast distances, spanning continents and cultures that had never met, yet were linked by the same human desire to understand the sky, the seasons, and the subtle mechanics of cosmic change. Moving eastward across silent mountain passes and quiet river valleys toward the fertile plains of East Asia, we find a parallel devotion to clarity, order, and visual harmony. There, under vast night skies illuminated by the steady, unblinking glow of distant stars, another great civilization was developing its own unique methods for visualizing quantity, turning abstract calculation into a graceful, physical ritual that brought calm focus to the observing mind. During China's Han Dynasty in the 2nd century before the Common Era, this search for mathematical harmony found a home within the serene study halls of court astronomers and devoted scholars. These thinkers understood that the movements of the sun, the moon, and the planets were governed by long, cyclical turnings that required delicate precision to trace and predict across the changing seasons. To manage these expansive calculations without losing their way, scholars sitting before smooth wooden counting tables would arrange polished bamboo rods called *chu in neat, balanced horizontal and vertical grids. Using these simple physical markers to calculate complex astronomical cycles with remarkable accuracy and visual clarity, the counting table became a quiet workspace of orderly geometry, where numbers were represented not by written symbols alone, but by the physical placement and orientation of the slender, hand-carved bamboo sticks. Alternating between horizontal and vertical alignment for consecutive place values, a scholar could represent units, tens, hundreds, and thousands with crisp, uncluttered simplicity, sliding the smooth rods across the wood with light, measured motions of the hand. In this tactile method of computation, every number had its rightful place within the grid, and 0 was understood as an empty, peaceful space on the table waiting patiently to be filled. As the scholars calculated the subtle shifts of the lunar phases, the timing of eclipses, and the grand alignment of the planets, the soft click of bamboo against wood echoed through the quiet rooms like the ticking of an ancient, natural clock. There was no hurry in their work. Each movement of a rod was a step toward aligning human understanding with the majestic order of the cosmos, allowing complex numerical problems to resolve themselves into neat, symmetrical forms. Looking back across the centuries at both the poetic ashrams of northern India and the quiet counting halls of Han Dynasty China, one sees a shared human devotion to bringing stillness out of complexity. Whether mapping the alternating syllables of a sacred chant into stair-patterned rows, or shifting slender bamboo rods across a wooden grid to follow the stars, these early pioneers of mathematical thought were engaged in a form of quiet meditation. They showed that numbers are not arbitrary or chaotic, but gentle frameworks that help us perceive the deep, underlying harmony of the universe. In both traditions, mathematics was an invitation to slow down, to observe, and to arrange thoughts with care and intention, creating a space where the mind could rest securely in the beauty of logic. As the night deepens and the world falls silent around us, we can take comfort in the knowledge that human curiosity has long sought out these soothing patterns, finding solace in the rhythmic balance of binary choices and the quiet order of polished rods on a smooth wooden board. The legacy of these ancient scholars lives on not as burdensome work, but as a quiet, enduring lullaby of structure and peace, reminding us that beneath the surface of all things lies an elegant, resting harmony. As the golden light of the ancient Mediterranean dusk faded into the cool, silent indigo of evening, the early scholars of geometry began to turn their eyes from the flat sands and parchment diagrams upward toward the vast, sweeping dome of the heavens. For centuries, the study of numbers and shapes had been deeply rooted in the practical, tactile world of land measurement. Flat surfaces and straight lines drawn upon wax tablets, where Euclid and his contemporaries had meticulously laid down the fundamental rules of points, lines, and plane figures. Yet when night fell and the dark sky unfolded its quiet map of shimmering stars, a new mathematical imperative presented itself to the human mind, one that required understanding not merely flat triangles resting upon a dusty tabletop, but the subtle, rounded arcs of a spherical universe. The celestial vault appeared as a magnificent, slowly rotating sphere, moving with a rhythm so steady, serene, and unbroken that it felt almost like a single, calm breath drawn across time. To comprehend this grand cosmic motion, mathematicians had to invent a language that could seamlessly bridge the familiar, rigid geometry of straight lines with the fluid, curved realm of circles and spheres. They began to realize that every star in its journey traced a delicate arc across the sky, and that the space between any two celestial bodies could be understood by examining the angle they subtended relative to an observer resting peacefully upon the earth. This quiet shift in perspective laid the groundwork for a profound transformation in how humanity viewed space, turning the nighttime sky into a vast, natural observatory where geometry, time, and arithmetic blended together into a single, soothing study. As the cool sea breezes swept inland across ancient coastal settlements, thinkers sat by low oil lamps and open courtyards, pondering how the length of a straight line drawn inside a circle might correspond to the length of the arc it embraced, seeking an elegant mathematical harmony that could bring quiet order to the infinite expanse above. Around 150 BCE, on the quiet island of Rhodes, Hellenistic astronomer Hipparchus of Nicaea compiled the earliest known table of trigonometric chords, using bronze sight rings to divide circles into 360 degrees beneath starlit night skies. Working in the still, clear air of the Aegean night, far from the noisy distractions of daytime life, Hipparchus spent countless hours peering through simple, yet remarkably precise observational instruments, watching the slow and deliberate wheeling of the constellations as they drifted gracefully across the dark vault above. To capture these ethereal motions in concrete, enduring numbers, he drew upon the ancient Babylonian convention of dividing a full circle into 360 equal parts, a system born from early calendar keeping and base 60 arithmetic that divided both space and time into harmonious, easily divisible units. Inside these divided circles, Hipparchus focused his attention on the chord, which is a straight line segment connecting any 2 points along the circumference of a circle. By systematically calculating the exact lengths of these chords for a wide variety of central angles, he effectively constructed the world's very first trigonometric table, creating a reliable reference guide that allowed astronomers to convert angular measurements across the sky into linear distances within a geometric model. Each entry in his table represented a quiet victory of human reason over the vastness of space, providing a mathematical key that could unlock the distances between stars. The subtle shifts in the moon's monthly path and the slow, rhythmic procession of the equinoxes, resting beneath the open canopy of starlight. Hipparchus worked with an unhurried, methodical patience, recording his calculations onto parchment scrolls so that future generations might look up at the night sky and see not an unsearchable chaos, but a beautifully ordered, measurable tapestry governed by precise geometric laws. The creation of this chord table marked the true birth of trigonometry, a word derived from ancient roots meaning the measurement of triangles. Though its earliest form was deeply and beautifully intertwined with the geometry of the circle, where earlier mathematicians had examined triangles as self-contained shapes resting statically upon a flat plane. The work of Hipparchus and those who followed him transformed the triangle into a dynamic, living instrument for exploring circular motion and celestial coordinates. By placing a triangle inside a circle, with its primary vertex resting at the very center, and its opposite base formed by a chord stretching across a curved arc, astronomers could relate the angle at the center directly to the length of the straight line, bridging the circle's rim. This elegant synthesis allowed one to determine the unknown sides or angles of a celestial triangle simply by consulting a pre-computed list of numbers, saving endless hours of repetitive geometric construction beneath the night lamp. The 360 degrees of the circle provided a shared universal language that brought extraordinary precision to navigation, sundial design, and eclipse prediction, bridging the gap between abstract theoretical mathematics and the practical rhythms of the natural world. The influence of the sexagesimal system, with its 60 subunits of minutes and 60 further subunits of seconds, lent an impressive depth to these calculations, allowing early astronomers to record minuscule fractions of a degree with remarkable clarity and calm precision. In the gentle stillness of ancient observatories, the rhythmic process of measuring arcs and looking up their corresponding chords created a sense of profound intellectual peace, reassuring early scholars that behind the grand complexity of planetary wanderings lay a calm, underlying numerical beauty that responded to patient observation and quiet thought. As the centuries unfolded, this foundational work carried out beneath the starlit skies of Rhodes would travel quietly across oceans and continents, flowing naturally into the scholarship of later civilizations in India, the Islamic world, and Renaissance Europe, where the concept of the chord would eventually evolve into the modern functions of sine, cosine, and tangent that form the backbone of advanced mathematics today. Yet in its earliest and most peaceful form, this branch of mathematics remained an intimate, tranquil dialogue between a solitary observer, a set of bronze sight rings, and the silent stars. The chord tables were not merely tools for calculation. They were quiet monuments to human patience and wonder, demonstrating that even the vast and unreachable heavens could be mapped with gentleness, precision, and grace. As the night grew deep and the constellations drifted toward the western horizon, the ancient astronomers could rest with the comforting knowledge that the universe operated in predictable, harmonious cycles. The numbers transcribed in those early tables served as a gentle bridge between the earthly realm and the cosmic expanse, inviting the mind to settle into the steady, reassuring rhythm of a world where every angle has its chord, every arc has its place, and the quiet music of geometry guides the stars on their timeless, peaceful journey. As dusk settles softly over the quiet river valleys and terraced hillsides of Han Dynasty China, a tranquil silence falls across the scholar's study, where paper lantern light flickers gently against dark timber beams, and the soft rustle of bamboo leaves outside mirrors the slow rhythm of the evening breeze. In this peaceful age, mathematics was not an abstract exercise performed in isolation, but a quiet art of harmony and order, deeply intertwined with the steady pulse of daily life, the measurement of seasonal harvests, the allocation of communal grain stores, the surveying of fertile lands, and the fair distribution of civil responsibilities across vast and varied provinces. Long before written symbols were rendered upon paper to represent abstract mathematical operations, practitioners of this ancient craft relied upon tactile tools of remarkable elegance, gathering in spacious, quiet rooms where long, smooth wooden counting tables rested beneath warm candlelight like serene landscapes waiting to be carefully arranged. Upon these polished wooden surfaces, calculations unfolded not through written figures, but through the deliberate, rhythmic placement of small, uniform rods crafted from bamboo, bone, or ivory. Each slender stick moving across painted grid lines with a faint, satisfying click that echoed softly in the still evening air. Known as counting rods or Suanchu asterisk, these physical tokens allowed mathematicians to represent decimal numbers with extraordinary flexibility, arranging them horizontally or vertically to indicate units, tens, hundreds, and thousands within a place value system that had flourished in China for many centuries. To observe a master of numbers at work in those quiet hours was to witness a gentle dance of physical tokens, where arithmetic became a visual and spatial meditation, an ordered layout of rows and columns, where quantities of grain, geometric areas, and administrative accounts found their natural equilibrium without hurry or strain, reflecting a profound cultural desire bring clarity, balance, and peaceful structure to the complex affairs of an enduring civilization. In this quiet environment, the counting table served as a neutral, welcoming slate where every value, whether large or small, found a designated place to rest, allowing the human mind to step back from the burden of mental calculation and simply observe the harmonious patterns taking shape upon the wood, like ripples smoothing over the surface of a still pond. It was within this long-standing tradition of visual calculation that a monumental shift in human thought took shape, quietly recorded in a text that would guide generations of scholars, engineers, and administrators for centuries to come. Around 100 CE in Han Dynasty China, anonymous scholars compiled the 9 treatises on the mathematical art asterisk, formalizing the earliest known rules for negative numbers by arranging red bamboo rods for positive counts and black bamboo rods for negative tallies across smooth wooden counting tables. This classic text, known in Chinese as asterisk jiezheng suanshu, gathered centuries of practical mathematical wisdom into 9 structured sections, addressing everything from agricultural surveying and civil engineering to commercial trade, fair taxation, and the sharing of resources. Yet among its most profound gifts to world mathematics was its treatment of values that represented shortages, debts, or deficits, concepts that had long proved elusive or perplexing to other ancient mathematical traditions around the globe. Rather than viewing a deficit as an impossible or unnatural quantity, the scholars of the Han Dynasty recognized that a debt was simply the natural counterpart to a surplus, existing in perfect, symmetrical harmony with it. To make this abstract duality instantly clear upon the counting board, they introduced a striking visual distinction that transformed the physical manipulation of numbers. Slender bamboo rods dyed a warm, vibrant red were laid down to represent positive amounts, such as grain received, taxes collected, or land owned, while rods dyed a deep, restful black were arranged to represent negative tallies, such as grain owed, expenses incurred, or debts to be repaid. As these red and black rods were placed side by side within the rectangular cells of the wooden table, arithmetic operations ceased to be abstract mental burdens and became clear, intuitive movements of color and space, where positive and negative values could mingle, balance, and neutralize one another with absolute visual clarity and quiet grace. The 8th section of the treatise, titled asterisk, Fengcheng asterisk, or rectangular arrays, introduced an extraordinarily sophisticated method for solving systems of simultaneous linear equations, laying out multiple unknown quantities into neat columns of numbers across the counting surface. Within this grid-like arrangement, the red and black bamboo rods allowed calculators to perform systematic row-by-row operations, subtracting one column from another and keeping track of changing balances with remarkable precision. The text set forth explicit, practical rules for combining these signed quantities, instructing the mathematician on how to add and subtract positive and negative numbers without confusion or hesitation. When adding quantities of the same color, the counts simply grew together in quiet harmony, adding red to red or black to black. But when combining opposite colors, the rods of lesser value were subtracted from the rods of greater value, leaving behind only the net remaining color to indicate the true balance. When a positive count and a negative count of equal size met within the same cell, the red and black rods completely canceled each other out, leaving the square entirely empty. This empty cell on the counting board represented 0, not as a symbol of nothingness, failure, or absence, but as a state of perfect, peaceful equilibrium, where debt and asset rested in exact alignment. This visual system was so natural and intuitive that it allowed hand scholars to work effortlessly with negative results, anticipating mathematical concepts that would not be formally embraced in Western mathematics for another 1,000 years. The counting board thus became a living landscape of commerce, geometry, and science, where complex problems involving crop yields, livestock trades, and administrative obligations were brought into gentle alignment through the quiet, rhythmic shifting of colored bamboo across polished wood. Beyond its immense practical utility, this approach to negative numbers reflected a deep philosophical alignment with the natural world, echoing ancient Chinese understandings of cosmic harmony, where light and shadow, movement and rest, presence and absence exist not as opposing conflicts, but as complementary aspects of a unified whole. Just as the warmth of summer naturally gives way to the quiet stillness of winter, and the inhalation of breath is followed by its peaceful release, the red and black rods demonstrated that every gain carries within it the quiet potential for loss, and every deficit points toward a future restoration of balance. As the evening deepens and candlelight burns low in the quiet study, the scholar's work draws gently to a close. One by one, the red and black bamboo rods are gathered from the smooth wooden tables, returned to their silk pouches, and set aside until the coming dawn. The polished counting boards lie clean and bare under the midnight sky, resting in the cool, still air of the silent room, free of all tallies and demands. In this peaceful stillness, the legacy of asterisk Jiazhang Suanshu endures as a timeless reminder of humanity's quiet journey toward understanding a world where numbers, whether positive or negative, cease to be sources of strain or complexity, fading instead into a serene, orderly harmony that cradles the inquiring mind and invites a deep, undisturbed sleep. As night settles gently over the ancient landscapes of the earth, the human mind has long looked upward and outward, seeking a sense of quiet order within the vast, steady rhythm of the cosmos. Across dense canopies of green and beneath vast, velvet skies untouched by modern illumination, early thinkers discovered that the grand movements of light and shadow across the firmament could be gathered into harmonious patterns of numbers deep within the lush silence of Central America, where humid night breezes rustle softly through tall limestone temples and thick forest foliage. Scholars of time watched the subtle drift of planets across the darkness with profound patience and serene reverence. Around 300 CE, in the rainforest cities of the Maya lowlands, astronomers recorded vast planetary calendar cycles using a base 20 system, where a softly carved seashell represented 0 as a token of quiet completion. In this tranquil mathematical tradition, 0 was not viewed as a harsh void of nothingness or an absence of value, but rather as a peaceful placeholder marking a full turn of the wheel, a quiet moment where a tally rested in stillness before beginning its journey anew. The carved shell, smooth and comforting to touch, embodied this gentle pause between cosmic cycles, bridging the distance between past counts and future horizons with quiet grace. By grouping their calculations in scores of 20, inspired perhaps by the natural tally of fingers and toes resting upon the warm earth, Mayan astronomers traced the intricate, long-period dances of Venus, the moon, and distant constellations with astonishing accuracy. Their records, delicately incised in stone lintels and painted on bark paper scripts, were not hurried declarations of power, but slow, meditative testimonies to a universe governed by predictable and reassuring beauty. In the quiet hours before dawn, as nocturnal forest creatures called softly through the canopy, these ancient observers understood that to measure time was to participate in a timeless stillness, holding the infinite within simple, elegant symbols that allowed the restless mind to settle into calm understanding. This profound appreciation for quiet structure, numerical elegance, and geometric harmony was never confined to a single continent or culture. Across the entire globe, human curiosity turned toward the soothing balance found in curves, boundaries, and natural forms. Among all geometric shapes, the circle in particular has held a sacred place in the human imagination, a smooth, unbroken path with neither beginning nor end, quietly embodying ideas of eternity, wholeness, and equilibrium. To measure the circle, to uncover the precise relationship between the straight line spanning its center and the sweeping curve of its outer rim, required a patience so deep and unbroken that the work itself resembled a form of quiet prayer in the tranquil study halls of antiquity. Far removed from the noise of daily commerce, early scholars sought ways to capture this elusive ratio, known to later generations as the constant pi, by gently coaxing straight lines to approximate the infinite softness of a curve. They recognized that while square fields and rectangular courtyards could be measured through direct, simple steps, the circle invited a softer and more gradual approach, stepping closer and closer to its true boundary through fine, infinitely repeating layers of geometric reasoning. Each added corner, each carefully subdivided line brought the practitioner one breath nearer to the hidden balance of the shape, demonstrating how human thought could steadily approach perfection through quiet, persistent effort. As ideas flowed along ancient trade routes and through quiet scriptoria, the search for mathematical truth became a shared, comforting lullaby of human progress, proving that despite differences in tongue, climate, and belief, the quiet desire to find order in space and time was a universal comfort shared under the same starry sky, far across the eastern oceans, along the tranquil banks of the Yangtze River in southern China. Another great master of calculation was engaged in his own dedicated pursuit of numerical perfection and harmony. The ancient city of Jiankang rested under cool twilight mists as scholar engineers and astronomers refined the traditional instruments of land measurement and star mapping, seeking to comprehend the underlying proportions of the physical world with absolute clarity. Around 480 CE in Jiankang, southern China, astronomer Zhu Changzhai calculated the value of pi to 7 decimal places by patiently inscribing a 24,576 sided polygon onto smooth wooden boards using fine counting rods. With extraordinary stillness of mind, laying out delicate rods of bamboo or ivory across polished tabletops, Zhu Changzhai began his work with basic inscribed shapes and doubled their sides again and again, stepping methodically from a simple hexagon to a dodecagon, and onward into thousands of minutely rendered, razor-thin geometric segments. Each step in this immense sequence required total concentration and thousands of individual mathematical operations, carrying long divisions and square roots to unprecedented levels of precision without the assistance of paper calculations, written equations, or mechanical computers. His hands worked with rhythmic, gentle grace in the soft glow of oil lamps, shifting the slender counting rods into precise alignments that locked the elusive ratio tightly between 3.1415926 and 3.1415927. This astonishing achievement, which would remain unequaled anywhere in the world for nearly 1,000 years, was not born from a desire for speed or public acclaim, but from a quiet, lifelong devotion to mathematical truth. The wooden boards became both a working canvas and a silent sanctuary, holding the vast complexity of tens of thousands of geometric facets within a clean, orderly grid that brought serene focus to the inquiring mind. Looking back across the long span of human history, one can trace a continuous thread of calm reflection, connecting the rainforest observatories of the Maya lowlands to the peaceful wooden writing tables of 5th century Jiankang. Whether carving the smooth curves of a seashell to denote a completed tally, or carefully laying out fine counting rods to reveal the subtle secrets of the circle, These early pioneers of mathematics were united by a shared devotion to quiet order and patient observation. They demonstrated that numbers are not merely cold, abstract rules or rigid burdens, but rather a comforting, universal language designed to help humanity navigate the cosmos with stillness, clarity, and grace. Through their quiet labor, the frightening vastness of the night sky and the intimidating complexity of geometric curves were rendered familiar, gentle, and reassuring, offering an enduring shelter of logic against the unpredictable winds of time. As the night deepens and the modern world slows its hurried pace, the enduring legacy of these ancient scholars invites us to rest in the peace of predictable rhythms and timeless truths. The carved shell rests in its zero state of quiet fulfillment. The multi-sided polygon dissolves softly back into the infinite curve of the circle, and the mind is left to drift peacefully upon the calm, boundless ocean of mathematics that has guided humanity safely through the ages. As twilight settles gently over the ancient plains of northern India, the heavy heat of the afternoon gives way to a cool, restful breeze carrying the fragrance of river soil, wild lotus, and blooming jasmine across the quiet countryside. For centuries, human thought had been gathering steady momentum along the fertile banks of great rivers, where simple counting stones, notched wooden tallies, and clay tokens had gradually transformed into rich, symbolic languages of number, measure, and space along the slow and peaceful waters of the Ganges. Generations of scholars and astronomers looked upward into the cloudless night sky, seeking an underlying order that matched the calm, repeating rhythms of the natural world. In the quiet sanctuaries of learning scattered across the Gangetic plain, surrounded by dark orchards of mango and sal trees, mathematics was not viewed as a harsh collection of rigid rules or exhausting computations, but rather as a serene contemplation of harmony, pattern, and cosmic balance. The steady rising and setting of constellations provided a natural, celestial clockwork, whispering of grand cycles of time that spanned thousands of years, and inviting patient minds to map the hidden geometry of the universe. Here, in the soft, flickering illumination of oil lamps, scribes prepared smooth strips of dried palm leaves, carefully trimming their edges and polishing their surfaces with fine river sand so that they might receive the deliberate, beautiful strokes of an iron stylus. The atmosphere in these courtyards was one of profound stillness, where the subtle rustle of parchment-like leaves blended with the soft, continuous murmur of the water, creating a timeless space where abstract thought could unfold with unhurried grace. As the night deepened and the stars drifted across the dark vault above, the search for numerical truth became a gentle form of meditation, anchoring the immense expanse of the cosmos within simple, elegant lines of poetic verse. It was within this peaceful environment of quiet reflection and empirical observation that astronomical and mathematical thought achieved one of its most remarkable moments of clarity. Scholars had long observed how the moon traced its monthly path through the 27 lunar mansions, and how the bright wandering planets drifted with subtle irregularities against the fixed background of the stars. Yet, capturing these continuous curves required a far more refined mathematical language than the ancient world had previously possessed. In 499 CE, at the Quiet Academy of Kusumapura, along the Ganges, Indian polymath A macron RY, a BH, a letter 1E60, composed the asterisk A macron RY, a BH, a letter 1E60, I macron Y, calculating exact sine tables and defining the Earth's daily rotation on soft palm leaf manuscripts. Writing at the young age of 23, his extraordinary insight led him to propose that the apparent nightly rotation of the heavens was not caused by the entire stellar sphere revolving around a stationary world, but rather by the smooth, continuous rotation of the Earth itself, spinning silently upon its own axis from west to east. To mathematically describe the positions of planets within this rotating framework, he replaced the cumbersome chord calculations of earlier Greek and Babylonian traditions with the far more elegant concept of the half-chord, known in Sanskrit as asterisk Jaya asterisk, or simply Jaya asterisk, which formed the true historical ancestor of the modern trigonometric sine function by dividing a quadrant of a circle into 24 equal segments of 3 3/4 degrees each. A macron RY, a BH, a letter 1E60, computed remarkably precise values for these trigonometric ratios, recording them in concise, metrical verses designed to be memorized and chanted with the calm, rhythmic ease of a lullaby. His masterwork brought a profound unification to the study of time and geometry, demonstrating that the complex movements of celestial bodies could be understood through predictable, proportional relationships preserved on fragile, dried leaves that could be held gently in the palm of a hand. Beyond these brilliant trigonometric breakthroughs, the intellectual culture of this period was defined by a revolutionary approach to numerical notation that would quietly alter the course of human history. The decimal place value system, which allowed any quantity, no matter how vast, to be expressed using only 10 simple digits, found its natural expression in the poetic structure of Indian mathematical treatises. Numbers were often assigned evocative names drawn from nature, philosophy, and the natural world, where 0 was spoken of as asterisk sunya asterisk, meaning the void or unclouded sky, and the digits carried a melodic quality when spoken aloud in the quiet evening air. This positional framework made complex calculations fluid and intuitive, releasing mathematicians from the cumbersome mechanics of older counting boards and permitting them to explore quadratic equations, square root algorithms, and planetary orbits with unprecedented ease. The physical manuscripts that preserved these insights were crafted with extraordinary care and reverence. Long, slender strips of palmyra or talipot palm leaves were dried, boiled, and smoothed, then inscribed by scratching delicate Sanskrit characters into the surface before rubbing the leaf with charcoal powder and aromatic oil to make the text appear dark and clear against the golden leaf. Bound together with cotton cords passing through tiny central holes and protected by carved wooden covers, these compact bundles held vast repositories of knowledge. Each page represented hours of calm, dedicated labor, where intricate astronomical tables and algebraic rules were distilled into precise two-line stanzas known as asterisk sutras. When scholars studied these works under the shade of academy verandas, they were engaging with a living tradition that blended intuitive aesthetic beauty with rigorous logic, proving that numbers need not be rigid or cold, but could serve as a peaceful bridge between the human mind and the orderly cosmos. As centuries drifted past like the gentle currents of the Ganges, the ideas recorded in the quiet courtyard of Kusumapura began a long, peaceful journey across lands and cultures, silently laying the groundwork for modern science, trigonometry, and algebra, traveling westward along ancient trade routes through desert oases, mountain passes, and vibrant river ports. These Sanskrit treatises were studied, translated, and expanded by scholars in the great centers of Islamic learning during the golden age of Baghdad. There, the Sanskrit term Jaya asterisk was transliterated into the Arabic asterisk Jiba asterisk, which later scholars interpreted as asterisk Jabe asterisk, meaning a fold or bay, leading European translators in the 12th century to render the concept into Latin as asterisk sinus asterisk, the simple, elegant decimal numerals, and the profound concept of zero traveled alongside these trigonometric tables, gradually replacing the awkward Roman numeral system throughout Europe and transforming the way humanity calculated distance, time, and planetary movement. Yet, despite their global impact, these monumental advances originated not in noisy workshops or places of conflict, but in the quiet contemplation of a starry sky over 1,500 years ago along the banks of a sacred river. The universe, in all its silent grandeur, continues to turn smoothly on its axis, just as it did when those early palm leaf manuscripts were first inscribed under the soft glow of an oil lamp. The steady, repeating rhythms of geometry and number remain a peaceful anchor for the spirit, inviting us to quiet our restless thoughts, release the burdens of the day, and rest securely in the timeless, harmonious order of the stars. Long ago, beneath the warm and quiet night skies of the Indian subcontinent, the movement of time unfolded in a slow, rhythmic cadence observed by patient thinkers who looked up at the stars. For generations, ancient astronomers and scholars had watched the gradual turn of the constellations, measuring the quiet geometry of the celestial sphere and seeking ways to capture the subtlety of the cosmos within written form. In these tranquil settings, where the gentle rustle of leaves accompanied the nocturnal breeze, mathematics was not merely a tool for commercial trade or architectural measurement, but a quiet language of harmony and contemplation. Across earlier ages, counting had naturally grown from tangible things, pebbles placed in smooth furrows of sand, notches carved into seasoned wood, or tokens arranged in neat rows, always representing physical presence, abundance, and tangible objects that could be gathered or shared. Yet as mathematical thought matured and expanded, a deeper and more subtle question began to linger in the quiet hours of study. How might one represent that which is not present, not as an error or a gap in computation, but as a meaningful, tranquil presence unto itself? Across various cultures, blank spaces on counting boards or simple punctuation marks had sometimes been used to hold a position, preventing numbers like 102 from collapsing into 12. But these early markers were merely temporary placeholders, quiet pauses in a stream of digits, rather than numbers capable of being added, subtracted, or understood as living mathematical entities. As the centuries drifted forward, the intellectual traditions of India offered a uniquely welcoming soil for a new conceptual synthesis, where deep philosophical reflections on existence, space, and quietude blended effortlessly with rigorous mathematical inquiry, preparing the way for a profound shift in how humanity would come to view the nature of numerical reality and the quiet beauty of nothingness. It was in this atmosphere of scholarly devotion and calm observation that one of the most transformative milestones in the history of mathematics was quietly recorded. In the year 628, in central India, the astronomer Brahmagupta wrote the Brahmasphutasiddhanta asterisk, formally defining zero using the Sanskrit word *sunya, which evokes the calm emptiness of open sky. Within the pages of this monumental astronomical treatise, composed in poetic verse so that its truths could be memorized and recited with a soothing cadence, zero was no longer treated as a mere blank space or a silent void waiting to be filled by a digit of substance. Instead, Brahmagupta recognized that this serene concept possessed its own intrinsic character and governing principles, establishing explicit rules for how it interacted with other quantities in arithmetic. He explained with clear and patient logic that when zero is added to a number or subtracted from it, the quantity remains entirely unchanged, resting peacefully in its original state, as if touched by a gentle breeze that leaves no mark. He demonstrated that multiplying any number by zero causes that number to dissolve smoothly into zero itself, returning all finite quantities back to that central receptive stillness. In doing so, he elevated what had once been an invisible absence into a fully realized mathematical object, giving the world a number that could sit alongside 1, 2, or 100 with equal dignity and grace. The word *sunya rooted in an ancient linguistic heritage that spoke of space, openness, and unburdened vastness, reflected a perspective that viewed emptiness not as a terrifying vacuum or a lack of value, but as a restful, expansive realm of boundless potential. Much like the clear blue canopy of a cloudless day, or the silent darkness of the night sky stretching above the quiet earth. This formal introduction of zero into arithmetic brought an extraordinary, weightless clarity to the art of calculation, transforming the way humans worked with numbers and thought about mathematical structure. Before zero was embraced as a number in its own right, performing long calculations often required heavy physical apparatuses, complex tallying boards, or cumbersome systems of notation, where every power of 10 required a new symbol or a separate column of counters. By pairing zero with the place value system, where the position of a digit determines whether it represents units, tens, hundreds, or thousands, mathematicians could now express any imaginable magnitude using only 10 basic symbols, allowing numbers of breathtaking size to be written with minimalist elegance and perfect order when a place held no value of its own. Zero sat quietly in that column, preserving the precise alignment of the neighboring digits without adding unnecessary complexity or weight to the overall expression. This elegant system allowed calculations to flow with a gentle, rhythmic ease, as algorithms for addition, subtraction, multiplication, and division could be carried out smoothly on paper or slate without the need to physically rearrange tokens or recalculate complex symbol groups. Beyond the practical convenience it offered to merchants, scholars, and star trackers, zero introduced a soothing symmetry to the numerical landscape, serving as the serene fulcrum around which positive and negative quantities rested in perfect balance. On one side lay quantities representing gains, assets, or steps taken forward. On the other lay debts, losses, or steps taken backward. And at the very center stood zero, the calm and neutral ground from which all direction originated, and to which all opposing forces could peacefully return, as the knowledge of Brahmagupta's work diffused through the scholarly networks of Asia, and eventually into the broader world. The concept of asterisk sunya traveled along quiet trade routes and translation paths, transforming every culture it touched. Translated into Arabic as asterisk sifr asterisk, meaning empty, the concept retained its serene essence as it became the cornerstone of Islamic mathematics and algebra, before eventually entering European languages as asterisk, cipher asterisk, and asterisk zero. Yet at its origin, the idea remained deeply connected to that soft Indian evening in 628, where an astronomer gazed into the vast expanse of the night sky and realized that nothingness could be defined, understood, and woven into the very fabric of human knowledge. There is a deep, quiet comfort in contemplating how a concept so fundamental to modern science, computing, and everyday life arose not from a desire to conquer or accumulate, but from a willing embrace of open space and quiet stillness, just as the open sky holds the stars, the sun, and the drifting clouds without ever being diminished or altered by them. The number 0 holds space within our calculations, providing the quiet foundation upon which all mathematical reasoning softly rests. In our own lives, amidst the continuous accumulation of tasks, thoughts, and daily efforts, the history of 0 reminds us of the quiet value of the unwritten page, the empty room, and the silent pause between breaths. As the night deepens and the world outside settles into a peaceful hush, we can let our minds rest in that same expansive clarity, releasing the need to measure or count, and drifting effortlessly into the calm, open space of quiet sleep. As the night deepens and the busy noise of the daytime world recedes into soft, quiet shadow, our journey moves gently across the centuries to ancient India, where the contemplation of the heavens and the fundamental structure of numbers bloomed in serene, uninterrupted stillness. In the historic city of Ujjain, long regarded as the sacred prime meridian of Indian astronomy, generations of scholars spent their nights beneath a vast canopy of stars, observing the slow, majestic movements of planets and measuring the endless rhythms of time. In this tranquil environment, calculation was not merely a practical tool for commerce, but a spiritual and philosophical quest to comprehend the order of the cosmos. For centuries, civilizations across the globe had used counting stones, clay tokens, and carved notches to track physical objects. Yet numbers remained strictly tied to tangible things: a flock of sheep, a bushel of grain, a measure of land. Even when early mathematicians left an empty space or drawn dot to signify an empty column in a counting board, this mark was viewed only as a silent placeholder, an empty vessel waiting to be filled by a real digit. To transform mathematics into a truly universal language, this silent void needed to step into the light as a full numerical quantity in its own right, possessing its own laws of harmony, addition, and interaction. It was within the quiet courtyards of Ujjain, surrounded by the cool night air and the gentle rustle of palm trees, that a profound breakthrough was committed to text. In 628 CE, in the quiet astronomical observatory of Ujjain, Indian astronomer Brahmagupta composed the treatise Brahmasphutasiddhanta *, establishing for the first time explicit mathematical rules for computing with 0 as an active numerical quantity on dried palm leaf manuscripts, with a delicate iron stylus etching fine, precise Sanskrit characters onto narrow, preserved palm leaves. Brahmagupta systematically defined how 0 operates within arithmetic. He explained that when 0 is added to or subtracted from any number, that number remains unchanged. And when any quantity is multiplied by 0, it settles peacefully into zero itself. Furthermore, he introduced the concepts of positive numbers as fortunes and negative numbers as debts, establishing zero as the calm, neutral fulcrum around which the entire continuum of numbers balances. In his calm and poetic verses, zero, known as asterisk, shunya asterisk, the void, was no longer an absence of value, but an active, peaceful presence from which infinite mathematical possibilities could flow. Over the centuries that followed, these revolutionary ideas traveled softly across continents and cultures, carried along the winding trade routes of Asia by traveling merchants, scholars, and pilgrims. Knowledge moved like a deep, quiet river, finding its way into regions where learning was cherished and protected. By the early 9th century, the vibrant center of global scholarship had established itself gracefully in the fertile valley of the Tigris River, within the round city of Baghdad. Under the enlightened patronage of the Abbasid caliphs, the famed House of Wisdom, or Beit al-Hikmah asterisk, was founded as a magnificent sanctuary for human thought, a place where manuscripts from ancient Greece, Persia, India, and Syria were gathered, preserved, and translated into Arabic. Within its cool, lofty halls, lined with thousands of hand-bound codices and fragrant leather scrolls, the atmosphere was one of quiet devotion to truth and contemplation. Fountains splashed gently in shadowed stone courtyards, creating a continuous, restful rhythm that accompanied scholars as they worked late into the night beneath the soft glow of oil lamps and the faint scent of night-blooming jasmine. It was an era of extraordinary synthesis, where thinkers of diverse backgrounds sat together upon woven carpets, debating astronomy, geometry, medicine, and arithmetic. Here, the Indian decimal place value system and the concept of zero were carefully translated and studied, freeing mathematics from the cumbersome limits of Roman numerals and physical counting boards. Scholars realized that with just 10 simple symbols, 9 digits, and the humble zero, any number, no matter how vast or minuscule, could be expressed with perfect elegance and ease. This universal notation provided the quiet foundation for a new way of thinking, setting the stage for a profound leap in human reasoning that would bridge the gap between simple arithmetic and the abstract structure of equations. Among the dedicated minds working within the peaceful arcades of the House of Wisdom was a brilliant Persian mathematician and astronomer whose work would forever reshape how humanity resolves the unknown. In 820 CE, at the House of Wisdom in Baghdad, Persian scholar Muhammad ibn Musa al-Khwarizmi authored Kitab Al-Jabr wal Muqabala, introducing systematic algebraic reduction by restoring balanced terms with fine reed pens on soft parchment, sitting at a low wooden writing desk as moonlight filtered through the arched windows. Al-Khwarizmi dipped his carefully split reed pen into dark, soot-based ink, crafting a clear and methodical guide to solving complex numerical problems. The title of his masterpiece contained the very essence of his methodology: Al-Jabr asterisk, which signified the restoration or completion of a quantity by adding subtracted terms back to both sides of an equation, and al-Muqabala asterisk, which referred to the balancing and reduction of positive terms of the same kind. Rather than treating mathematical problems as rigid, isolated puzzles, al-Khwarizmi conceptualized equations as dynamic, living balances. If an unknown quantity, which he poetically termed asterisk shay asterisk, meaning the thing, was obscured by subtraction or complicated fractions, he used gentle, systematic operations to restore its wholeness and bring it into clear view. With fine, fluid strokes of his reed pen on smooth parchment sheets, he set down 6 standard forms of linear and quadratic equations, explaining step by step how to simplify them through logical reduction. His work was thoroughly practical, yet deeply philosophical, designed to assist in real-world tasks such as dividing inheritances, measuring agricultural land, surveying canals, and computing trade transactions, all while revealing the underlying harmony that governs quantitative relationships. The emergence of algebra marked a magnificent awakening in human thought, transforming mathematics from a static art of counting into a fluid, expressive language of relationships and transformations. Al-Khwarizmi's systematic approach demonstrated that what is unknown need not cause confusion or distress. Through patience, balance, and structured reasoning, hidden values can be gently brought into light without disturbing the equilibrium of the whole. His legacy was so profound that his very name, rendered into Latin in later centuries as asterisk algorithmi asterisk, gave birth to the word algorithm, describing step-by-step procedures for calculation, while the title Al-Jabr evolved into asterisk algebra asterisk, a discipline that eventually swept across Europe and laid the groundwork for modern science, engineering, and digital technology. Yet beyond its immense practical utility, this ancient mathematics offers a serene and comforting vision of the universe. Just as Brahmagupta showed that zero rests at the quiet center between positive and negative realms, Al-Khwarizmi showed that every complex equation carries within itself the balanced steps necessary for its own resolution. The flow of algebra mirrors the natural rhythm of restful breathing, inhaling a complex question, holding the balanced terms in quiet space, and exhaling into resolution and clarity. As you rest in the quiet quietude of the present moment, allow your mind to settle into the peaceful rhythm of these timeless discoveries. Imagine the cool night air of Ujjain, where palm leaves held the first rules of zero, and the gentle scratch of reed pens on parchment in Baghdad, where equations found their balance. All the numbers now rest in perfect harmony. The unknown values are peacefully settled, and the vast, beautiful world of mathematics cradles the mind in quiet, unbroken tranquility. As dusk settled softly over the fertile floodplain between the Tigris and Euphrates rivers, 9th century Baghdad glowed with the warm, golden radiance of oil lamps, casting a tranquil hush across its grand circular avenues, brick gateways, and shaded palm gardens. Within this sanctuary of learning, known across continents as the House of Wisdom, scholars and translators gathered from distant regions to study, preserve, and contemplate the vast tapestry of human knowledge. Deep inside its quiet halls, manuscripts written in Sanskrit, Greek, Syriac, Persian, and Arabic lay, carefully unrolled upon low carved wooden desks. Their parchment and rag paper pages containing geometric proofs from Alexandria, planetary tables from Babylon, and numerical traditions from the Indian subcontinent. Scholars worked side by side, translating fundamental works such as Euclid's Elements Asterisk, Ptolemy's Almagest Asterisk, and the ancient mathematical treatises of India, weaving disparate traditions into a single, cohesive ocean of human understanding. The introduction of smooth, durable rag paper from Samarkand had allowed books to be transcribed and bound with unprecedented ease, filling the vast archives with neat rows of leather-bound volumes that preserved the wisdom of centuries. The air inside the grand library was pleasantly cool and still, scented with the subtle aroma of dried papyrus, beeswax, oak gall ink, and the delicate fragrance of night-blooming jasmine drifting in through high-arched courtyard windows. In this atmosphere of deliberate, unhurried inquiry, scholarship was held not as a competitive pursuit, but as a gentle stewardship to be gathered with reverence, studied with infinite patience, and harmonized for the common good. Scholars moved softly through lofty corridors lined with floor-to-ceiling shelves, their soft robes rustling against polished tiles as they carefully copied intricate diagrams of circles and triangles, recorded the silent movements of stars across nocturnal charts, and reflected deeply upon the invisible order that connects the physical world to abstract thought. Outside, the clear desert sky unfolded like a dark velvet canopy, studded with countless glittering stars, inviting quiet meditation on the timeless laws governing quantity, measure, and form. Here, in the heart of the city of peace, mathematics was experienced not as a set of rigid or demanding exercises, but as a deeply calming language of symmetry and truth, where every drawn line and recorded symbol worked gently to illuminate the underlying patterns of nature. The quiet rhythm of dipping reed pens into dark ink became a form of meditation, anchoring the mind to the slow, steady assembly of understanding, allowing all daily anxieties to drift away in the quiet beauty of structured thought. In this sanctuary of quiet inquiry, one scholar in particular spent long, contemplative hours examining how quantities could be arranged, simplified, and restored to perfect equilibrium. In 9th century Baghdad, mathematician Muhammad ibn Musa al-Khwarizmi composed his treatise on equations inside the tranquil courtyards of the House of Wisdom, popularizing the term *Al-Jabr*, which originally referred to the gentle act of restoring balance, to appreciate the spirit of his foundational work. one must picture the peaceful courtyard where he worked, where water trickled softly from a bronze fountain into a central marble basin, creating a steady, soothing murmur that accompanied the rhythmic movement of his reed pen. The word Al-Jabr carried a deeply human and comforting meaning in the language of the time. In everyday speech, it was used to describe the setting of a fractured bone by a compassionate healer, or the tender repairing of something that had broken or fallen out of alignment. Al-Khwarizmi viewed mathematical equations through this exact lens of healing and restoration, seeing an unknown or subtracted quantity not as an intimidating obstacle, but as a temporary void waiting to be made whole again. If a negative or missing value weakened one side of an expression, he showed how adding an equivalent amount to both sides restored the balance smoothly, bringing the entire mathematical statement back into a state of serene harmony. Working alongside Al-Jabr was its companion principle, al-Muqabala asterisk, which involved reducing and balancing equal terms across opposite sides of an equation. Much like a merchant adjusting small brass weights upon a set of hanging balance scales, until the central needle comes to rest precisely at vertical zero. In his treatise, Al-Khwarizmi systematically cataloged 6 canonical forms of linear and quadratic equations, offering step-by-step geometric proofs for each type, so that the reasoning behind every step was fully visible and tranquil to comprehend. These methods were not designed merely as abstract theories for scholars in isolation, but as practical, compassionate tools to aid everyday life across the vibrant Islamic world. Al-Khwarizmi wrote his compendium to assist citizens in solving real-world problems with fairness and absolute clarity, calculating the equitable division of family inheritances according to complex legal guidelines, surveying agricultural fields after the seasonal swelling of rivers, computing trade accounts fairly, and measuring land boundaries so that every neighbor received their true and rightful share without dispute. Through these orderly steps, confusion and disagreement dissolved into the quiet certainty of geometric logic, leaving behind a profound sense of fairness, order, and deep intellectual rest. The true beauty of Al-Khwarizmi's algebraic vision lay in its universal simplicity, transforming mathematics from a collection of isolated, specialized calculations into a unified and flowing art. Before his treatise, ancient mathematicians had often approached each problem as a separate puzzle, requiring its own unique geometric drawing or verbose explanation, making arithmetic feel distant and complex to master. By establishing clear, systematic operations for reducing and restoring equations, Al-Khwarizmi introduced a single, elegant framework that allowed anyone to navigate numerical relationships with quiet confidence and clarity. Essential to this transformation was his seamless integration of the decimal place value system developed by Indian scholars centuries earlier, including the profound concept of zero. known in Arabic as asterisk cipher asterisk, meaning an empty space filled with quiet potential. This elegant base-10 system, using just 9 simple digits and the tranquil circular 0, replaced cumbersome calculation boards with fluid pen strokes on smooth paper, allowing large numbers to be added, subtracted, multiplied, and balanced with effortless grace. As copies of his books were carefully transcribed by scribes and carried along trade routes to North Africa, Andalusia, and eventually into the monastic libraries of Western Europe. Al-Khwarizmi's very name was Latinized into algorithmi, giving birth to the modern word algorithm to describe any step-by-step path toward solving a problem. Similarly, the Latinized translation of his book title introduced the word asterisk algebra to the Western world, while the Arabic word asterisk cipher asterisk transformed into terms like asterisk cipher asterisk and asterisk 0. Generations later, scholars such as Leonardo of Pisa, known as Fibonacci, would learn these methods along Mediterranean trade ports and share them across Europe, unlocking new horizons in architecture, astronomy, navigation, and commerce. Yet, despite its far-reaching legacy, the core of algebra remained rooted in the tranquil atmosphere of that Baghdad courtyard. A gentle invitation to gaze upon what is uneven or unknown without fear, and step by step, with patience and care, guide it back into balance. As the night deepens and the mind turns inward, we can imagine the cool night breeze rustling through the palm fronds above the House of Wisdom, the slow drip of the courtyard fountain, and the silent satisfaction of equations coming to rest, reminding us that all things in nature seek their natural state of equilibrium, quiet, and peace. As twilight settles softly over the historic city of Damascus, where ancient trade routes meet beneath the quiet glow of evening stars, one can imagine the calm rhythm of daily life slowly giving way to the gentle stillness of the night. For generations, the scholars, merchants, and accountants of the ancient world had gathered in peaceful courtyards to calculate the movement of goods, the division of land, and the passage of time. In those early centuries, as mathematical ideas traveled across oceans and deserts from the Indian subcontinent, they carried with them a revolutionary way of thinking about numbers, a place value system built upon 10 simple symbols, including the quiet placeholder of 0. Yet, despite the profound elegance of this new arithmetic, the physical act of calculation remained bound to an age-old medium: the wooden dust board or sand tray. Scribes would carefully sprinkle fine sifted sand or pulverized earth across a flat wooden surface, creating a delicate canvas upon which they could trace figures with a pointed stylus or the tip of a finger. Each step of a calculation required the mathematician to write down a set of digits, perform an operation, and then physically wipe away the intermediate numbers with the palm of their hand to to make room for the next phase of the problem. While this method possessed a simple, fluid beauty, it was inherently fleeting and marked by a perpetual rustling sound as sand grains were brushed back and forth across the board. The constant erasing meant that once a step was completed, its history vanished into the smooth earth, leaving no permanent record for future review. Scribes working in quiet scriptoriums or busy marketplaces had to endure the soft, dry rasp of shifting grit, carrying out complex mental steps under the constant risk of accidentally smudging their work with the swipe of a sleeve. The sandboard was a tool of transient thought, ideal for quick transactions, yet less suited for the enduring, contemplative scholarship that was beginning to flourish across the Islamic world during the 10th century. In the year 952 CE, within the serene surroundings of Damascus, a profound shift took place that would forever change how numbers were recorded and contemplated. The introduction of paper, which had made its way westward along the Silk Road, offered a remarkably smooth, light, and durable alternative to heavy clay, expensive parchment, and shifting sand. However, adapting the fluid, place-value methods of Indian arithmetic to paper posed a unique challenge, because ink drawn upon a paper page could not be easily wiped away with the touch of a finger, as one had done on a sandboard. It required a thoughtful redesign of the mathematical steps themselves, so that calculations could proceed forward in an orderly, cumulative manner without needing to erase earlier lines. In 952 CE in Damascus, scholar Abul Hasan al-Khwarizmi wrote the earliest known manual adapting Indian arithmetic to paper, allowing scribes to replace noisy trays of fine sand with quiet reed pen strokes. In his remarkable treatise on Indian computational methods, al-Khwarizmi systematically modified traditional mathematical routines so that each line of calculation could be set down neatly beneath the previous one, preserving every step of the process in permanent black ink. Scribes no longer needed to carry heavy wooden boards dusted with sand, nor did they have to work amid the soft rustle of shifting earth that had accompanied calculation for centuries. Instead, they could sit in quiet contentment, dipping a finely split reed pen, known as a kalam, into rich walnut ink, letting the point glide effortlessly across smooth paper sheets. Al-Khwarizmi's manual provided clear, serene instructions for addition, subtraction, multiplication, and division, as well as the treatment of fractions, demonstrating how each procedure could be performed calmly and methodically on paper without a single erasure. This innovation not only made mathematical work vastly quieter and more precise, but it also bestowed upon scribes the comforting ability to pause their work, step away, and return later, confident that every intermediate step remained safely captured on the page before them. The transition from sand to paper marked a gentle turning point in the history of human thought, allowing mathematical ideas to be preserved, studied, and shared with unprecedented ease and quietude. With the stroke of a reed pen, calculations transformed from temporary movements in the dust into enduring records that could travel across wide distances. From the libraries of Damascus to the scholarly centers of Cairo, Baghdad, and Cordoba. In Al-Khwarizmi's work, one also finds the quiet emergence of decimal fractions, an elegant extension of the place value concept that allowed mathematicians to express parts of whole numbers with the same seamless logic used for units, tens, and hundreds. By separating the whole number from its fractional part with a small vertical mark, Al-Khwarizmi introduced a visual clarity that rendered complex financial calculations and scientific measurements effortlessly readable. As this peaceful method of writing numbers spread across continents, it laid the quiet groundwork for future generations of mathematicians who would build upon these paper-based algorithms to advance algebra, astronomy, and navigation. The silence of the paper manual replaced the constant rustle of sand, bringing a deep, restful focus to the work of scholars who spent long evenings by lamplight contemplating the harmony of numbers. Each page filled with steady lines of ink represented a quiet victory for human patience and order, proving that numbers could be organized not through frantic erasing, but through gentle, sequential steps set down with care. Tonight, as we reflect on this quiet evolution from noisy sand trays to the serene stroke of a pen, we can appreciate how the simple act of writing numbers on paper helped bring order and tranquility to the human mind, inviting a calm and lasting peace to settle over our thoughts as we drift gently toward rest. As twilight settles softly over the quiet courtyards of medieval Europe, the rhythm of study rests securely within the thick stone walls of abbey scriptoria and cathedral schools, where scholars labored by the gentle, flickering glow of tallow candles and oil lamps. For generations, the keeping of monastic accounts, the precise calculation of Easter dates upon the liturgical calendar, and the measuring of field boundaries had relied upon traditional Roman numerals and simple counting boards laid upon wooden tables, while Roman numerals served with noble clarity for recording fixed quantities upon monumental stone or enduring parchment. Performing intricate arithmetic with them was a slow and painstaking endeavor, requiring long series of additions and subtractions using uniform pebbles or metal jettons arranged in temporary rows. Across the wider Mediterranean world, however, ideas were traveling along peaceful trade routes and through scholarly exchanges, carrying whispers of a different way of conceptualizing numbers, a system born far to the east in India and refined throughout the vibrant learning centers of the Islamic world, where 9 distinct numerical characters and a symbol for empty space allowed any magnitude imaginable to be expressed with elegant simplicity through positional value alone. in the quiet halls of Western sanctuaries, a few forward-looking scholars began to study these rare mathematical manuscripts, contemplating how the static numerical expressions of antiquity might give way to a fluid mathematics of movement, placement, and spatial order. In these peaceful places of quiet devotion, the contemplation of numbers was seen not merely as a practical tool for administrative record-keeping, but as a form of silent meditation, an avenue through which curious minds sought to perceive the hidden harmony and structural order underlying the physical world. As night fell over silent cloister walks, scholars transcribed ancient texts letter by letter, preserving the accumulated insights of geometry, astronomy, and arithmetic, carefully laying a serene foundation for a broader intellectual shift that would gradually transform how human minds calculated, reasoned, and understood the infinite patterns of numerical relationship. Among those drawn to this quiet revolution of thought was a remarkable scholar whose curiosity spanned the sciences of music, astronomy, and calculation, seeking harmony in both the cosmos and the mechanical tools of learning. Having traveled in his youth to the borderlands of Catalonia, he encountered the rich traditions of Andalusian scholarship, absorbing advanced mathematical ideas that bridged the wisdom of the classical world with the innovative methods of Arabic mathematicians. Upon returning north to teach in the cathedral school of Reims, he sought a practical and visual way to demonstrate the subtle mechanics of positional notation to his students, translating abstract numerical concepts into a tangible instrument that could be touched, observed, and gently manipulated. In the late 10th century in Reims, the scholar-monk Gerbert of Aurillac constructed an abacus with numbered horn tokens called asterisk apices, sliding them quietly across leather sheets divided into 27 columns to demonstrate place value arithmetic. Each token was meticulously carved from smooth animal horn and inscribed with a single Arabic numeral digit from 1 to 9, replacing the need for multiple unnumbered counters within a single column. The leather sheet, supple and laid flat upon a heavy oak table, provided a soft, non-reflecting surface upon which the 27 vertical columns were neatly ruled, grouped into sets of 3 to represent units, tens, and hundreds across vast orders of magnitude. As Gerbert moved a single horn token from one column to the next, its value multiplied tenfold, illustrating with effortless clarity how a solitary symbol could represent a simple unit, a group of 10, or a fraction of 1,000, merely by virtue of its spatial position upon the leather grid. The soft sound of horn sliding across polished leather filled the quiet classroom, offering a peaceful, tactile experience of calculation that turned complex arithmetic from a tedious burden into an orderly, rhythmic art. This ingenious abacus represented a profound conceptual bridge between the physical counting boards of antiquity and the abstract, written algorithms that would eventually dominate European mathematics. By reducing the number of physical counters needed for calculation, requiring only one inscribed token per column rather than 9 identical pebbles, the system uncluttered the visual field, allowing the mind to focus upon the elegance of place value and mathematical transformation. When a column contained no token at all, its emptiness was not a void of failure, but a quiet placeholder, visually anticipating the vital function that the digit 0 would perform in written arithmetic as the centuries progressed. Scholars watching the movement of the apices could see at a glance how addition was reduced to the smooth regrouping of tokens, how subtraction became the gentle shifting of values to adjacent columns, and how multiplication and division could be unfolded step by step through orderly spatial shifts. The quiet mechanics of the board created a serene environment for mental focus, where errors could be corrected with a simple slide of a fingertip, rather than the arduous rewriting of ink upon costly vellum. Although the broader adoption of Arabic numerals across Western Europe would take several more centuries to fully take root in merchants, counting houses, and royal treasuries, Gerbert's columned leather abacus sowed the quiet seeds of understanding among the educated minds of his era, demonstrating that mathematics could be both deeply logical and beautifully intuitive. The leather sheets, easily rolled and carried from monastery to cathedral, preserved this tactile wisdom, passing down a quiet legacy of structured thought through generations of teachers and students who viewed calculation not as an exhausting trial, but as a peaceful exploration of numerical patterns. As the evening air grows still and dark shadows lengthen across the stone arcades of Reims, the scholar's instruments are set aside, resting in the quiet sanctuary of the scriptorium until the return of morning light. The horn tokens, polished by years of gentle handling, are gathered into their small wooden boxes, while the leather sheets are carefully folded, holding within their ruled lines the quiet memory of a day spent tracing the timeless principles of number and space. Outside the cathedral windows, the night sky opens wide and silent, filled with countless stars, whose distant movements have long been calculated by astronomers using these very same principles of order, proportion, and positional measure. The evolution of mathematics, from the ancient counting stones washed smooth by river currents to the sophisticated place value boards of the Middle Ages, reflects a long, peaceful human endeavor to find clarity in complexity and rest in understanding. In the soft hush of nightfall, the steady progress of knowledge seems to breathe in rhythm with the quiet world, reminding us that every great leap in human thought rests upon such patient, gentle moments of inquiry, where a single scholar quietly slides a token across a leather grid to illuminate a truth that will outlive kingdoms. Now, as the last candles are snuffed and a restorative silence settles over the ancient halls of learning, the mind is invited to rest, cradled by the calm certainty that numbers, like the stars, remain steadfast, orderly, and beautifully at peace in the quiet expanse of the universe. As the night air settled gently over the city of Cairo, near the turn of the 11th century, the quiet flow of the Nile seemed to reflect the calm, steady rhythm of mathematical discovery taking place throughout the Islamic Golden Age. In this era of deep intellectual inquiry, scholars worked in peaceful courtyards and serene libraries, preserving ancient wisdom while quietly expanding the boundaries of human understanding. The study of shapes and numbers was not merely a practical discipline for commerce or land measurement, but a quiet search for the underlying harmony of the physical universe. It was in this tranquil setting that natural philosophers began to look closely at three-dimensional forms, asking how the volume of complex, continuously curving vessels could be calculated with absolute precision rather than rough approximation. Around 1000 CE in Cairo, polymath Ibn al-Haytham derived the formula for summing fourth powers in his treatise on the volume of a paraboloid asterisk, calculating smooth curved volumes by measuring fine horizontal slices of water vessels beneath soft lamplight. To achieve this remarkable feat, he conceived of a curved solid, such as a parabolic water jar, as a stack of infinitely thin, circular discs layered gently from the flat base to the upper brim. By examining the radius of each individual cross-section as it varied along the central axis, he observed that the areas of these circular slices grew in direct proportion to the square of their position along the vertical height. To sum the total volume of all these fine layers combined, it was necessary to calculate the sum of the fourth powers of consecutive integers, a mathematical challenge that had eluded previous generations of ancient geometers. With remarkable patience and analytical clarity, Ibn al-Haytham developed an algebraic formula for these higher degree sums, effectively creating an early precursor to integral calculus centuries before its formal codification. Sitting in the quiet hours of the night, illuminated only by the warm, flickering flame of an oil lamp, he watched the soft shadows fall across parchment sheets filled with meticulous diagrams and numerical tables. Each line of his proof moved with measured grace, demonstrating that even the most complex, continuously curving surfaces could be fully understood by breaking them down into simpler, infinitely repeatable parts. This method of horizontal integration did not just solve a specific geometric puzzle regarding water vessels. It established a universal approach to measuring irregular spatial volumes, showing that abstract numbers could perfectly mirror the physical contours of crafted objects. The gentle persistence of his work embodied the contemplative spirit of the era, where deep focus and quiet thought turned intricate mathematical obstacles into clear, elegant principles that would guide natural philosophers for generations to come. This elegant technique of slicing complex shapes into simpler, manageable units reflected a broader shift in how medieval natural philosophers viewed the physical world around them, where earlier classical traditions had often treated geometry as a collection of fixed, ideal shapes detached from daily life. The scholars of the Islamic world sought to connect abstract mathematical theory directly to the tangible realities of nature, craft, and physical space, as Ibn al-Haytham's work on paraboloids demonstrated. Understanding the total behavior of a continuous form required only that one carefully examine its smallest constituent layers and sum them with orderly mathematical precision. This realization created a profound sense of continuity across different branches of science, bridging the quiet study of domestic water vessels with the vast, sweeping geometry of the earth itself. As news of these analytical breakthroughs circulated along trade routes and through royal libraries from North Africa to Central Asia, other polymaths applied similar principles of patient observation to the grandest scales of space. Thousands of miles to the east, across mountain passes, high plateaus, and fertile river valleys, another great thinker was contemplating how simple geometric relationships could unlock the hidden dimensions of the entire planet. Abu Rayhan al-Biruni, a Persian scholar of extraordinary breadth and curiosity, had long been fascinated by the challenge of measuring the Earth's true curvature without relying on the exhausting, imprecise surveying methods of the past. Traditionally, determining the circumference of the globe required large teams of observers to march across vast expanses of flat desert, physically pacing out long distances along a single line of latitude while taking celestial measurements of star elevations at sunrise or nightfall. Such endeavors were exceptionally costly, prone to cumulative human error, and severely limited by the practical difficulty of traveling across rugged or inhospitable terrain. Al-Biruni recognized that just as Ibn al-Haytham had measured the volume of a vessel from a single stationary perspective, by understanding its internal geometry, one could determine the size of the Earth from a single, elevated vantage point, using the subtle principles of spherical trigonometry and visual optics. This innovative approach transformed planetary measurement from an arduous physical journey into a serene act of mathematical deduction. In 1023 CE, Persian polymath Abu Rayhan al-Biruni stood atop the sandstone fort of Nandana in modern Pakistan, using a handheld astrolabe to measure the subtle dip of the horizon over flat plains, calculating Earth's radius within 1% of modern measurements. From the quiet height of the fortress walls, the surrounding landscape unfolded in a breathtaking, peaceful expanse, where the fertile lowlands of the Punjab stretched out smoothly toward the distant haze of the horizon. Standing still against the cool evening breeze, Al-Biruni first calculated the exact height of the mountain fortress above the surrounding plain, by measuring the angle of elevation to the fort's peak from two separate locations on the flat ground below. With the vertical height of his observation point established with precision, he waited for the evening air to settle, allowing the distant line where the earth met the sky to become razor sharp against the soft, fading light of dusk. Holding his finely crafted brass astrolabe steady in his hands, he measured the minuscule angle by which the visual horizon dipped below a true horizontal reference line. This tiny angle of dip, though barely visible to an unassisted eye, formed the vital vertex of a grand right-angled triangle, whose hypotenuse extended from the center of the earth all the way up to his solitary standing place on the fort. Using the sine law and elementary trigonometric ratios, he transformed this single angular measurement and the height of the hill into a direct calculation of the planet's radius. The mathematical elegance of his method was matched by its astonishing accuracy. His final result differed from modern satellite measurements by less than 16 miles, a testament to both his instrumental skill and his conceptual brilliance. As night descended over the ancient sandstone walls of Nandana, the quiet plains below sank into shadow, leaving the solitary scholar under a canopy of emerging stars. In that peaceful moment, the micro-world of Ibn al-Haytham's sliced water jars and the macro-world of al-Biruni's measured globe came together in a shared testament to human curiosity. Both men had shown that through patience, fine tools, and the gentle language of mathematics, the mysteries of shape, volume, and planetary scale could be brought into quiet, harmonious clarity, offering rest to minds seeking order in the cosmos. As night descended upon the ancient city of Isfahan, the desert heat yielded to a cool, refreshing stillness that washed over the tiled courtyards, quiet arcades, and soaring domes of the Royal Observatory. High above the bustling streets, where the daily murmur of trade and conversation fell silent beneath a vast canopy of stars, scholars gathered their instruments and manuscripts to observe the timeless rhythms of the heavens in this calm atmosphere of intellectual reflection. The study of mathematics was deeply intertwined with the observation of the sky, for both offered a glimpse into an underlying harmony that governed the cosmos. The air inside the observatory was soft and still, carrying the subtle sense of dry earth, dried herbs, and burning oil lamps whose flames cast warm, dancing shadows against white plaster walls. Here, time seemed to slow down, measured not by frantic urgency, but by the slow, predictable rotation of the celestial sphere, and the gentle drip of water clocks marking the passage of the night hours. For centuries, thinkers across the Islamic world had nurtured a sanctuary for thought, translating, preserving, and refining the mathematical heritage of Greece, India, and Babylon, while weaving their own profound insights into the tapestry of human knowledge. From the early foundation of algebra laid by thinkers who classified equations with words, and geometric diagrams, to the refined astronomical tables used to navigate the desert and compute calendar cycles. Mathematics was seen as a pathway to quiet clarity. In the silence of these evening hours, the pursuit of truth was a meditative act, requiring patience, precision, and an open mind receptive to the subtle patterns hidden within geometry and arithmetic. Among those who walked these quiet halls, observing the stars and pondering the balance of numbers, was a scholar whose mind moved fluidly between poetry, astronomy, and the structural beauty of equations. As he looked out across the shadowed rooftop toward the dark horizon, the heavens provided a backdrop of infinite order, inviting a deeper contemplation of how abstract algebraic relationships could be brought into clear, visible focus through the calm grace of geometric form. For generations, mathematicians had sought ways to solve equations that involved higher powers, moving beyond simple linear relationships and quadratic balances toward the more complex realm of the cubic. While earlier traditions could handle problems involving squares and simple areas, equations involving the cube of an unknown quantity presented a subtle puzzle that resisted straightforward arithmetic techniques of the era. A cubic equation, representing relationships of volume and three-dimensional magnitude, required a leap in imagination to visualize and resolve. Rather than viewing an equation merely as a sequence of numerical operations, the Persian polymath approached the problem with a deeply spatial intuition, recognizing that algebraic balances could be embodied as physical curves whose points of intersection held the key to hidden solutions. In 1079, at the quiet observatory of Isfahan, Persian scholar Omar Khayyam solved cubic equations geometrically by drawing the peaceful intersections of smooth parabolas and circles across brass plates. Working by the steady light of a lantern, he carefully guided fine scribes across the cool, polished metal surfaces, etching lines that curved with absolute mathematical fidelity. A parabola, rising with quiet grace from its vertex, would sweep smoothly across the plate until it crossed the steady arc of a carefully drawn circle or hyperbola. At the precise point where these two smooth lines met, the coordinate of their intersection revealed the positive real root of the cubic equation, transforming what had been an abstract algebraic challenge into a clear, tangible geometric reality. This method did not rely on mechanical computation or tentative guessing, but on the intrinsic balance of conic sections, forms that had been admired by ancient geometers for their aesthetic purity. Now, given fresh purpose in unlocking the structure of degree equations, the brass plates, reflecting the soft amber glow of the oil lamp, became silent maps of numerical truth where curves met in perfect stillness, demonstrating that algebra and geometry were not separate domains, but two harmonious languages describing the same underlying structure of reality. This synthesis of geometric forms and algebraic equations represented a momentous step in the history of mathematical thought, bridging the rigorous spatial reasoning of antiquity with the versatile symbolic methods that would flourish in later centuries. By drawing upon the classical study of conic sections, curves, originally explored by ancient thinkers like Apollonius of Perga, by slicing a cone at various gentle angles, he demonstrated how parabolas, circles, and hyperbolas could be systematically brought together to classify and solve distinct families of cubic equations. Each type of cubic equation, depending on the arrangement of its terms, corresponded to a specific pairing of intersecting curves, allowing a geometer to systematically determine the existence and location of real roots with quiet, visual certainty in an era before modern algebraic symbols and formulas had been devised to represent complex polynomials easily on paper. This geometric approach provided both clarity and rigor, allowing mathematicians to visualize abstract relationships as physical intersections in space. The process required immense focus and delicate craft, as the accuracy of the solution depended upon the smooth, unblemished curve etched onto the brass plate. Yet, within this meticulous work lay a profound sense of tranquility, for it showed that complex numerical problems possessed inherent geometric order that could be revealed through patience and clear reasoning. Across the wider Islamic world, from Baghdad to Cordoba, manuscripts detailing these geometric solutions were copied, studied, and discussed in quiet courtyards and library alcoves, preserving this elegant synthesis for future generations. The practice of geometry became a form of quiet contemplation, where the scholar listened to the silent logic of lines and angles, finding a deep sense of rest in the knowledge that behind the apparent complexity of numbers lay a serene and enduring order. As the night wore on over Isfahan, and the constellations shifted slowly across the deep blue vault of the sky, the observatory remained a quiet haven of peace and discovery. The brass plates, inscribed with their intersecting circles and parabolas, rested upon wooden tables alongside iron dividers, compasses, and sheets of smooth paper filled with neat lines of calligraphy. In the silence of the late hours, as the cool desert wind whispered softly through the stone arches, one could feel the quiet continuity of human inquiry stretching across time and space. The work accomplished in those peaceful evening hours would radiate outward through the centuries, traveling along trade routes and through scholarly exchanges, until it reached the universities and study rooms of Renaissance Europe, where mathematicians would later build upon these foundation stones to forge modern symbolic algebra. Yet in this moment, unhurried by the future, the beauty of the mathematics rested entirely in its immediate clarity, the simple, breathtaking truth of two smooth lines coming together at a single, perfect point on a brass surface. The stars above continued their silent, eternal dance, reflecting the same geometric balance that guided the scholar's hand below. The soft glow of the lantern flickered gently against the brass, casting quiet reflections that seemed to quiet the mind and invite deep rest. In the calm embrace of the night, the mind finds comfort in knowing that the search for mathematical truth has always been a gentle, patient journey, guided by curiosity and sustained by the quiet beauty of forms that endure unchanged across the ages. In the quiet expanse of central India, where rolling forest slopes give way to gentle river valleys, the ancient city of Ujjain had long stood as a peaceful sanctuary for scholars, astronomers, and thinkers. Positioned upon a pleasant plateau along the banks of the sacred Shipra River, Ujjain occupied a place of profound significance in the history of science, serving as the prime meridian for classical Indian astronomers who mapped the steady movement of the stars across the night sky for generations. Mathematicians in this serene region gathered beneath the leafy shade of courtyard trees, or within the cool stone sanctuaries of ancient observatories, observing the cosmic clockwork with patient reverence. In this tranquil environment, the study of numbers was never treated as a cold or mechanical exercise, nor was it confined to dry commercial accounting. Rather, it was understood as a deeply harmonious expression of natural order, intimately woven into the fields of grammar, music, poetry, and seasonal rhythms. The gentle rustle of palm leaves in the evening breeze provided a rhythmic accompaniment as scholars pondered the subtle properties of zero, the elegant symmetry of positive and negative quantities, and the hidden geometric relationships governing the natural world. Water clocks dripped with a steady, soothing cadence into polished stone basins, measuring out the passing hours in unhurried increments, while astronomical instruments crafted from brass and wood caught the soft, silvery light of the evening stars. In the deep stillness of these scholarly retreats, mathematical inquiry became a form of quiet meditation, carried out far away from the noise and haste of daily life, driven by a simple and abiding wonder at how numerical patterns underlay every corner of the cosmos. As twilight settled softly over the surrounding groves and quiet waterways, this contemplation of harmony invited the mind into a state of restful clarity, allowing the cares of the day to fade away into the calm, predictable rhythm of the universe. This deep appreciation for the harmony between nature and numerical reasoning reached an extraordinarily graceful expression during the 12th century, when the mathematical tradition of India welcomed poetic beauty as its natural companion and guide. In 1150 CE, in the verdant hills of Ujjain, Indian astronomer Bhaskara II composed the mathematical treatise Lilavati *, phrasing complex algebraic problems as soothing Sanskrit poems featuring swarms of bees and lotus blossoms floating in calm ponds. Within the pages of this celebrated work, mathematical challenges were presented not through intimidating symbols or rigid abstractions, but as tender inquiries addressed to a curious listener, inviting the mind to wander through peaceful countryside scenes to uncover the unknown quantities hidden within them. A typical verse might describe a quiet, sunlit pool where a delicate lotus flower grew, standing a certain height above the surface of the water, until a soft, passing wind gently pushed the blossom sideways, until it touched the water at a specific distance from its root, asking the scholar to use the properties of triangles to determine the depth of the pond. Another poem might portray a portion of a buzzing swarm of wild bees alighting upon the sweet nectar of a jasmine flower. Another fraction settling upon a cluster of blue water lilies, and a remaining pair hovering lazily in the warm air above, prompting the student to calculate the total size of the swarm through a balanced algebraic equation. Other verses spoke of peacocks perched atop high poles watching serpents glide toward their burrows, or gentle herds of elephants wandering through forested glades, turning every calculation into a vivid story filled with natural splendor. Through these evocative imagery-laden couplets, Bhaskara II demonstrated that quadratic equations, linear combinations, ratios, and permutations could be approached with a spirit of playfulness and serene contemplation. The mathematical language was deliberately crafted to be recited aloud in melodious verse, so that the gentle cadence of Sanskrit poetic meters would calm the spirit while guiding the intellect through complex logical steps, transforming rigorous study into a soothing ritual. The decision to frame advanced algebra through the medium of lyrical poetry reflected a profound educational philosophy, one that understood that true intellectual clarity flourishes most easily when the mind is relaxed, unhurried, and peaceful, rather than separating quantitative reasoning from qualitative beauty. The tradition of Ujjain viewed them as complementary aspects of a single, coherent reality, where numerical precision added depth to art, and artistic imagery rendered abstract thought accessible and inviting. The mathematical subjects explored in the Lilavati encompassed a broad spectrum of medieval knowledge, detailing the fundamental operations of arithmetic, the properties of fractions, the calculation of interest, the rules governing shadow lengths measured by simple gnomons, and methods for determining the surface areas and volumes of geometric solids. Furthermore, the text delved into sophisticated algebraic techniques, including methods for solving indeterminate equations of the first and second degrees, topics that would later captivate mathematicians across continents for centuries to come. Yet, despite the technical depth of these subjects, the narrative voice throughout the text remained consistently warm, encouraging, and reassuringly patient. Bhaskara II addressed his reader with gentle affection, offering words of praise and encouragement as each mathematical concept was unlocked. reassuring the student that patience and clear observation would illuminate even the most intricate numerical relationships. In doing so, he transformed what might have been a demanding discipline into a comforting, restorative practice, where numbers moved across the page with the quiet elegance of swans gliding over a moonlit lake. As scholars and students chanted the verses under the quiet night sky, the boundary between logical problem-solving and sensory appreciation dissolved into a seamless experience of calm focus, teaching that the pursuit of truth could be as peaceful as a quiet breath. As night deepened over the verdant hills and quiet orchards surrounding Ujjain, the palm leaf manuscripts and ink pots were gently set aside, their pages wrapped in soft cloths and stored in the cool alcoves of the observatories. The fading light of oil lamps cast long, peaceful shadows across the stone floors, where scholars had spent the day calculating the trajectories of planets and the subtle properties of numbers. Outside, in the stillness of the midnight hour, the real lotus blossoms closed their petals against the cool evening air, resting quietly upon the calm waters of the temple ponds, while the swarms of bees slept peacefully within their hives deep in the forest. The distant planets and stars, whose movements Bhaskara II had calculated with such remarkable accuracy in his astronomical works, continued their silent, timeless journey across the dark canopy of the sky. The enduring legacy of Ujjain's mathematical poetry would eventually travel far beyond the borders of central India, crossing oceans and deserts in translation, inspiring scholars throughout the Islamic world and Renaissance Europe, and helping to lay the groundwork for global algebraic thought. Yet at its heart, this rich mathematical heritage remained forever anchored in the quiet, reflective spirit of its origin, a timeless reminder that the search for mathematical order can be a source of deep tranquility and wonder. In the quiet darkness of the night, the peaceful verses of the Lilavati continue to echo like a gentle lullaby, inviting the mind to let go of analytical effort, to rest within the beauty of timeless patterns, and to sink into a deep, uninterrupted, and soothing sleep. Across the calm, sunlit waters of the medieval Mediterranean, trade routes moved with the slow and steady rhythm of wind and tide, carrying not only merchant vessels laden with spices, silks, and olive oil, but also carrying subtle, transformative ideas about the nature of numbers. Along the North African coast, the harbor of Buja rested beneath quiet hills, where customs officers and scholars conducted business with a quiet efficiency that caught the eye of a young Italian traveler named Leonardo of Pisa, sent there by his father to learn the customs of international commerce. Leonardo observed how local clerks tallied cargo and calculated exchange rates without the bulky wooden counting boards or complex Roman numerals typical of European scriptoriums. Instead, they wrote with 9 fluid symbols and a gentle 0, allowing complex arithmetic to unfold across paper like a tranquil stream. In 1202, Italian mathematician Leonardo of Pisa published Liber Abaci after watching customs clerks in the port of Bugitali cargo using Hindu-Arabic digits, filling thick parchment pages with peaceful arithmetic lessons for Mediterranean merchants. Within its extensive pages, Leonardo unfolded the elegance of positional place value notation, guiding readers step by step through the calm mechanics of addition, subtraction, multiplication, and division. He demonstrated how practical problems of commerce, calculating interest, dividing profits among partners, converting currencies, and measuring weights could be resolved with clarity and grace. The text replaced the tedious manipulation of physical countertokens with a quiet visual discipline, where each digit drew its value from its position within a row, bringing an unprecedented stillness and order to the bookkeeping houses of Pisa, Florence, and Venice. As merchants adopted these peaceful figures, the burden of calculation lifted, turning the daily management of human trade into an orderly, harmonious art. As the centuries drifted onward, these new numeric tools expanded beyond the counting houses of coastal merchants and traveled into the quiet libraries, cathedral schools, and nascent universities of Western Europe. Throughout the 13th and 14th centuries, scholars began to gaze past the practical needs of commerce, turning their attention toward the quiet patterns of the natural world and the continuous nature of physical change. In the silent scriptoriums and stone study halls of medieval academia, natural philosophers pondered how qualities such as warmth, illumination, velocity, and color intensity moved through space and time. Rather than viewing numbers solely as static measures of fixed quantities, such as sacks of grain or coins in a vault, they began to imagine quantities as continuous, flowing entities that expanded, diminished, or held steady like a soft breath in the intellectual center of Paris, where the gentle waters of the Seine flowed quietly past tall Gothic arches. Scholars sat at heavy oak desks, lit by the steady flame of beeswax candles, copying ancient texts and expanding the boundaries of natural philosophy. They realized that to understand the physical world, the slow cooling of a heated iron rod, the steady acceleration of a falling drop of rain, or the gradual fading of twilight, they needed a visual language capable of rendering continuous variation visible and serene. This profound shift in perspective laid the groundwork for a broader contemplation of movement, transforming mathematics from a collection of isolated calculations into a tranquil mirror reflecting the gradual, harmonious rhythms of natural processes. It was within this contemplative environment at the University of Paris that the French master and theologian Nicole Orsmy sought a clear, harmonious method to visually portray how physical qualities fluctuate across space and time. Around 1360, at the University of Paris, scholar Nicole Orsmy devised early coordinate graphing by drawing perpendicular lines on parchment, mapping intensity as vertical height above a serene horizontal baseline. In his influential treatise on the configurations of qualities, Orsmi instructed the scholar to draw a straight, tranquil horizontal line across the parchment, representing the extended subject or the duration of time, which he called the longitude. Above each point along this baseline, he directed the quill to rise vertically, drawing perpendicular lines, whose lengths corresponded precisely to the degree or intensity of the quality at that exact moment or location. A dimension he termed the latitude. When the tops of these vertical lines were connected, they formed clear geometric shapes, soft rectangles for uniform qualities that remained constant, and gentle triangles or sloping trapezoids for qualities that varied steadily over time. By translating abstract, continuous change into static, beautiful geometry, Orsmi allowed the human eye to perceive the total quantity of a changing phenomenon as a tranquil area enclosed beneath a geometric boundary. A uniform motion became a calm, level plane. A steady acceleration became an ascending slope of perfect symmetry. This breakthrough provided a peaceful visual bridge between the geometric traditions of antiquity and the future development of coordinate systems and calculus, proving that even the most dynamic forms of physical motion could be understood as serene, balanced forms resting quietly upon a page. As nighttime settles over the quiet rooms of history, these ancient lines remain still, inviting the mind to rest in the perfect balance of geometry, motion, and quiet thought. As the centuries folded softly into one another across the ancient trade routes of the East, the human relationship with mathematics began to undergo a quiet, profound transformation, moving gradually away from the static measurements of farmland and stone monuments toward the subtle, continuous mysteries of motion, light, and time. For generations, scholars in ancient river valleys had learned to count discrete objects, pebbles resting on dusty tiles, bushels of grain stacked in clay storehouses, or the clean geometric angles of shadows cast by gnomons in the bright noon sun. Yet, the natural world around them remained stubbornly fluid, filled with smooth celestial arcs, wavering planetary paths, and the steady, unbroken flow of river currents. In the quiet sanctuaries of learning scattered across the Indian subcontinent, thinkers realized that to truly understand the sweeping curve of the heavens and the subtle rhythms of celestial bodies, numbers needed to stretch beyond rigid integers and simple geometric ratios into something infinitely soft, continuous, and adaptable. They began to look closely at the circle, that timeless symbol of completeness and eternity, wondering how a straight line might be coaxed to measure an arc without ever breaking its perfect smoothness, and how a finite human mind might touch the very edge of the infinite. Across peaceful courtyards shaded by heavy boughs of banyan and mango trees, manuscripts written on carefully cured palm leaves were passed from master to student, filled with delicate Sanskrit verses that blended astronomical observation with poetic reverence for the orderly cosmos. In these quiet centers of inquiry, the study of geometry merged smoothly with the study of numerical ratios, giving rise to the flowering of trigonometry, the art of measuring the subtle relationships between the sides and angles of triangles nested within circles, the concepts of sine and cosine, which had begun as humble chord lengths in early Greek, Babylonian, and classical Indian astronomical tables, were gradually recognized not merely as static lookup values for navigators and stargazers, but as fluid, breathing functions that described every wave, cycle, and rotation in the physical universe. As dusk settled over quiet observatories, scholars would gaze upward at the night sky, tracking the slow, predictable journeys of Jupiter and Saturn through the zodiac, knowing that behind the velvet dark lay a deep mathematical harmony waiting to be coaxed into light through patient, restful calculation. This patient tradition of mathematical inquiry reached a remarkable and serene culmination in the lush, green landscapes of southern India, where the warm breezes of the Arabian Sea met the forested slopes of the Western Ghats. During the 14th century, along the palm-lined Malabar coast of India, astronomer Madhava of Sangamagrama derived infinite series for trigonometric functions, summing endless sequence fractions while listening to evening monsoon rains. In the quiet solitude of his retreat, surrounded by the rhythmic pitter-patter of raindrops falling upon broad banana leaves and thatched roofs, Madhava looked far beyond the geometric limitations of his predecessors. He realized that a trigonometric ratio like the sine, cosine, or arctangent did not need to be locked within a rigid geometric diagram, but could instead be expressed as an infinite sum of simple, alternating terms that diminished with exquisite regularity, rather than attempting to measure a complex curve with a single static ruler. He understood that one could combine an endless sequence of tiny, carefully calibrated numerical fractions, each subsequent step bringing the total closer to the ideal truth, much like a steady stream of rainwater filling a bronze vessel drop by drop until it rests perfectly level with the rim. Through this extraordinary leap of intuition, Madhava constructed mathematical series where terms were alternately added and subtracted in a soothing, balanced cadence. A positive fraction followed by a slightly smaller negative fraction, rocking gently back and forth like a soft pendulum, gradually narrowing the margin of uncertainty until the sum converged upon an exact, tranquil value. His work laid the foundations for what later generations would recognize as the calculus of infinite series, anticipating European developments by more than 2 centuries through sheer depth of geometric insight, numerical mastery, and quiet, unhurried meditation. Sitting by his window as the evening air turned cool and mist drifted through the dense coconut groves. Madhava recorded these discoveries in elegant verse, creating mnemonic chants that allowed his disciples to memorize complex mathematical expansions as naturally as sacred poetry, preserving his profound insights within the living memory of the Kerala school. The realization that an infinite number of progressively smaller quantities could be added together to produce a precise, finite result was a breathtaking shift in human thought, transforming infinity from an intimidating, unapproachable void into a gentle and cooperative partner in understanding the world. Through Madhava's series for the arctangent, the elusive value of pi, the fundamental ratio of a circle's circumference to its diameter, could be calculated to any desired degree of precision simply by evaluating an endless alternating chain of fractions, beginning with 1, subtracting 1/3, adding 1/5, subtracting 1/7, and continuing onward into the calm distance. Each additional step in the sequence softened the remaining error, drawing the calculated value closer and closer to absolute mathematical truth with the delicate, methodical care of a woodcarver polishing a smooth wooden sphere. With these infinite series, the scholars of the Kerala school constructed trigonometric tables of astounding accuracy, allowing astronomers to predict lunar and solar eclipses, calculate planetary positions, and determine geographic latitudes with a quiet confidence that far surpassed any methods previously known. There was no urgent need for complex mechanical instruments or rapid computation. The entire process relied on the quiet discipline of the human intellect, working in harmony with dried leaf pages, natural inks, and endless patience. The infinite series demonstrated that true precision was not achieved through brute force or rigid measurement, but through a soft, continuous approach that embraced the infinite, allowing each tiny fraction to contribute its small, harmonious weight to the whole. As these mathematical techniques were passed down from master to student along the tranquil river valleys of Kerala, they reflected a culture that viewed intellectual exploration not as a competitive race, but as a peaceful, lifelong practice of observation and reflection, deeply connected to the natural world. As night deepened over the Malabar coast and the monsoon clouds parted to reveal a tapestry of glittering stars, these mathematical insights settled into the long history of human thought, like quiet waters finding their natural rest. The transition from counting simple stones to balancing algebraic equations, and ultimately to summing infinite series, marked a profound voyage of the human spirit, a journey from the immediate, tangible world of the senses into the vast, quiet realm of abstract beauty. The work of Madhava and his contemporaries in southern India proved that mathematics was not merely a practical collection of rules for commerce and land surveying, but a universal language capable of describing the infinite nuances of motion, space, and time. before these series would travel across oceans and continents to inspire mathematicians in distant lands. They existed as peaceful songs of numerical harmony, crafted in quiet rooms while rain fell upon palm fronds outside. The infinite series taught humanity that even when a path stretches out without end, each small, mindful step brings us closer to clarity, and that within the endless flow of numbers lies a deep, reassuring order that governs both the motion of distant galaxies and the gentle rhythm of a falling drop of water. In contemplating these endless sums, the mind is invited to release its restless striving, settling into the quiet certainty that behind all the complexities of the universe lies a simple, elegant balance. As the lamps were extinguished in the ancient observatories of Kerala, the scholars rested in the quiet dark, leaving behind a legacy of numbers that continues to whisper its calm, timeless truth across the centuries, coaxing the weary mind into peaceful, undisturbed sleep. Long after the daytime trade along the Silk Road had quieted into soft shadows, the ancient oasis city of Samarkand rested peacefully under a vast, dust-free canopy of night stars. Here, in the opening decades of the 15th century, the pursuit of mathematics was not merely a practical enterprise for architects and merchants, but a deeply contemplative art, practiced in harmonious tandem with the study of the heavens. At the heart of this intellectual golden age stood the majestic stone observatory commissioned by the astronomer Prince Ulugh Beg. Constructed upon a quiet, windswept hill just beyond the city's turquoise domes and scented gardens. Built into the living rock of the hillside was a monumental ark, a giant meridian sextant of polished limestone, designed to capture the subtle shifts of celestial bodies with unmatched precision. Within these thick stone walls, far removed from the stir of the city below, scholars gathered in shared silence to map the sky and refine the laws of geometry. The atmosphere inside the observatory was cool and tranquil, carrying the faint, soothing aromas of tallow candles, dried reed ink, and heavy rolls of handmade paper. Illuminated by the warm, steady glow of oil lamps, thinkers moved with unhurried reverence. They understood that, to decipher the secret patterns of the cosmos, one had to listen closely to the quiet language of numbers, where every curve, ratio, and angle harbored a piece of universal truth. As the constellations turned slowly overhead, the work within the observatory proceeded with a rhythmic, restful discipline, linking the quiet observation of the earthbound mathematician to the eternal movements of the cosmos. Among the brilliant minds drawn to this sanctuary of learning was the Persian astronomer and mathematician Jamshid al-Kashi, a scholar whose extraordinary patience and computational genius were celebrated across the Islamic world. Raised in the historic city of Kashan, al-Kashi had spent decades mastering the arts of astronomy and arithmetic before being invited by Ulugh Beg to lead the computational work at Samarkand. He possessed a profound fascination with the fundamental constants of nature, most notably the timeless ratio, comparing a circle's circumference to its diameter, known today as pi. For generations, mathematicians had sought to determine this ratio with ever finer accuracy, building upon the geometric foundation laid by Archimedes in antiquity. The classical method involved enclosing a circle between two regular polygons, one inscribed inside the circle and one circumscribed around its exterior. By progressively doubling the number of sides of these polygons, a mathematician could squeeze the circle's perimeter into an increasingly narrow numerical range. Al-Kashi resolved to pursue this classical approach with a level of rigor and scale never before attempted in human history. Night after night, sitting in the quiet stone chambers of the observatory, he filled sheet after sheet of paper with intricate geometric diagrams and exhaustive calculations. In 1424, at the tranquil stone observatory of Samarkand, Persian astronomer Jamshid al-Kashi computed pi to 16 decimal places. By inscribing a polygon with over 800 million sides onto sheets of paper to achieve this astounding level of exactness, he conceived an imaginary polygon possessing 3 times 2 to the 28th power of sides, which equaled precisely 805,306,368 distinct straight edges. Through thousands of iterative steps, he manually extracted square roots with flawless accuracy, relying solely on his deep intuition for arithmetic, specialized computational tables, and the steady, rhythmic movement of his reed pen upon the paper. Each calculated digit brought the ratio into sharper focus, extending the calculation out to 9 sexagesimal places, which translated seamlessly into 16 correct decimal places, a world record of precision that would stand unbroken for nearly 2 centuries. The quiet triumph of al-Kashi's work lay not only in the astonishing accuracy of his result, but also in the conceptual clarity and elegant methods he refined along the way. In his masterwork on the subject, titled the Asterisk Treatise on the Circumference Asterisk, he demonstrated a brilliant synthesis of numerical traditions, bridging the base 60 sexagesimal system, long favored by astronomers, with the newly developing framework of decimal fractions. Al-Kashi recognized that positional notation was far more than an abstract tool. It was a flexible, living language capable of rendering complex physical realities simple and transparent. By systematically converting sexagesimal fractions into decimal forms, he made it possible to express minute fractions of a circle without cumbersome conversions, effectively anticipating the modern decimal system by generations. His work demonstrated how an infinitely smooth, flowing curve could be approached through discrete, perfectly ordered numerical steps, bringing a sense of calm predictability to what had once seemed unknowable. Every line of text he inscribed on those peaceful nights reflected a deep belief in the underlying order of the universe, a conviction that behind the apparent complexity of nature lies a simple, reassuring harmony that can be understood through patience and quiet focus. The steady addition of each decimal digit served as a gentle reminder that progress in knowledge does not require rushed effort, but rather a slow, deliberate accumulation of small truths, each built securely upon the last. As the first gentle light of dawn began to paint the horizon in soft shades of rose and gold over the mountains of Samarkand, Al-Kashi would carefully set down his pen, allowing his ink to dry alongside sheets filled with neat rows of numbers. The great observatory would slowly wake to the morning breeze, its stone arches catching the early sunlight, while the stars faded quietly into the brightening sky. Though centuries have passed since those quiet nights of study, and the grand limestone instruments of Samarkand have worn away with time, the mathematical truths calculated within those stone walls remain unshakable. The 16 decimal places of pi computed by Al-Kashi stood as an enduring bridge between the geometric traditions of the ancient world and the algebraic breakthroughs of the coming centuries, illustrating the quiet power of human thought when aligned with nature's timeless laws. Mathematics, in this tranquil setting, was experienced as a calming, meditative endeavor, a quiet sanctuary where the mind could find stillness amidst the boundless scope of the universe. As we reflect on this remarkable legacy of patience, accuracy, and quiet wonder, the mind is naturally drawn into a state of peaceful rest, letting go of the noise of the day and settling gently into the quiet, harmonious rhythms of numbers and stars. As twilight settles gently over the towering, snow-capped peaks of the South American continent, a cool and restful stillness descends upon the high mountain valleys and terraced hillsides. Up in these elevated sanctuaries, where the thin air carries an extraordinary clarity, and the night sky opens into an infinite tapestry of brilliant stars, ancient societies cultivated a deep and tranquil connection to the rhythm of their environment, while civilizations in other corners of the world chose to record their thoughts, transactions, and astronomical discoveries by carving symbols into hardened clay or applying ink to delicate sheets of papyrus and parchment. The people who inhabited the vast Andean landscape developed a system of memory and calculation that was uniquely tactile, remarkably supple, and woven directly into the fabric of their daily life. In this quiet alpine world, where soft winds whisper gently through the high puna grasses and mist settles low in the valleys at dusk, numbers were never abstract marks etched upon rigid, unyielding surfaces. Instead, they existed as a physical architecture of spun fiber, crafted from the fine fleece of grazing camelids, or harvested from the quiet cotton fields of the sun-warmed coastal valleys below. To interact with a record in this mountain realm was to hold the soft weight of history in one's palms, to let one's fingertips trace the subtle variations in texture, ply, and color. and to marvel at how human thought could transform simple threads into intricate repositories of quantitative wisdom. Every strand hung with quiet intention from a central main cord, like the soft branches of a sleeping willow tree, waiting patiently in the dimming light to be read by those who understood its silent, harmonious language. Here, high above the clouds, the mathematics of agriculture, tribute, community, and time existed not as cold equations, but as a calming, tactile art form that brought enduring order and peaceful balance to a sprawling empire. During the 15th century in the high Andes, Inca record keepers called quipucamiocs cataloged harvest totals and calendar cycles by tying neat, intricate knots into soft, dyed cotton threads along primary cords. These honored guardians of memory approached their work with a quiet, meditative devotion, sitting comfortably upon woven mats as their skilled hands guided the pliable strands with effortless grace. From a sturdy, horizontal primary cord hung dozens, sometimes hundreds, of secondary pendant threads, each meticulously dyed in natural pigments derived from mountain plants, minerals, and insects. A rich palette of deep indigo, warm ochre, quiet charcoal, earthy terracotta, and soft natural cream allowed every string to speak a silent, specialized language, where different colors represented distinct categories of life, such as yields of golden maize, stores of dried potatoes, counts of grazing herds, or the quiet progression of days within the seasonal year. By placing knots at precisely measured vertical intervals along these suspended cords, the quipucamiocs instituted an extraordinarily logical decimal place value system that rivaled the mathematical systems of any contemporary global power. Near the bottom of a hanging thread, single units were tied with delicate simplicity, while higher positions along the cord held knots representing tens, hundreds, and thousands, ascending toward the primary cord like steps carved into a tranquil mountain path. A simple figure 8 knot might mark a single unit resting softly near the bottom edge, whereas long, multi-loop knots were tied with exquisite care to represent digits from 2 to 9. Their smooth, spiraled loops holding numerical truth with permanent clarity. Once a comprehensive accounting was complete, the main cord could be loosely rolled or folded into a compact, lightweight bundle, ready to be carried across thousands of miles of stone highways by swift, sure-footed runners. In the serene chambers of regional storehouses, bathed in the soft, flickering light of small oil lamps, these record keepers spent their evenings in peaceful contemplation, running their hands down thread after thread, conducting the administration of an entire continent in absolute silence, save for the faint rustle of cotton against cotton. The creation and reading of these knotted instruments, known as quipus, was far more than an exercise in practical record keeping. It was a rhythmic, meditative practice that connected human consciousness to the vast cycles of nature and time. High in the mountains, where the weather shifted with subtle grace, and the seasons dictated the survival of whole communities. Keeping accurate count of time was essential for maintaining harmony between human labor and the land. The calendar cycles preserved upon these dyed cotton cords traced the steady, predictable movements of the sun, the waxing and waning of the silver moon, and the annual movement of constellations like the Pleiades as they drifted across the dark velvet sky. By intertwining these astronomical observations with detailed harvest counts, the Quipucamiocs created a unified, holistic record that bridged the cosmic rhythms above with the earthly abundance below. There was a profound and soothing dignity in how these textiles held memory, bypassing the need for spoken or written words in favor of a universal, tactile language of color, not type, and spatial orientation that could be understood across vast distances and diverse regional languages. As the cool night air seeped into stone courtyards, carrying the clean scent of wood smoke and mountain pine, a Quipucamioc could unroll a cherished cord and quietly recall the exact yields of far-off valleys from decades prior, tracing the historical flow of grain, cloth, and community work with serene confidence. The physical medium itself insisted upon a restful, unhurried pace. One could not rush the tying of a precise, multi-turn knot, nor could one read a chord without giving complete, calm focus to every single fiber. In this way, mathematics became a tranquil act of stewardship and care, ensuring that every village, every field, and every family was remembered and valued within the woven fabric of the community. Stepping back to contemplate this remarkable epoch in the global story of human thought, we are reminded that the impulse to count, measure, and organize our world is one of humanity's most peaceful and enduring endeavors. Long before complex symbolic algebra was written in books or calculated on screens, human beings found creative, beautiful ways to bring clarity to their surroundings, turning simple materials gathered from their immediate environment into powerful tools of understanding. Whether carved into ancient bones, pressed into wet clay tablets, slid across the wires of an abacus, or tied into soft, dyed cotton threads high in the Andes Mountains, numbers have always served as a gentle bridge connecting human curiosity to the quiet, reliable order of the universe. They allow us to rest easily in the knowledge that the world operates according to predictable patterns, that winter will always yield to spring, that harvests can be preserved to sustain life through cold months, and that the stars will keep their patient course across the night sky. As we settle into the stillness of the present evening, we can take comfort in the quiet legacy of the Quipucamiocs and the countless ancient thinkers who came before us, who devoted their time to creating order, harmony, and peace out of complexity. Their neat, intricate knots still carry a timeless lesson in mindfulness and care, whispering to us across the centuries that knowledge can be gentle, beautiful, and deeply reassuring. calm mountain winds fading into silence, and the dark sky holding its ancient stars, we can let our minds rest in the peaceful certainty of a world thoughtfully measured, gently understood, and securely held in quiet order. As the light of the late 15th century softened across the market towns of Central Europe, the gentle rhythm of daily commerce called for a simpler, more peaceful way to record the movements of trade. In dusty, timber-framed warehouses, where cool evening shadows settled over stacked oak barrels and woven sacks of grain, merchants spent long hours inspecting cargo, measuring weights, and noting down the quiet variations in their inventories for generations. Keeping track of items that weighed slightly more or slightly less than standard measures required long, written descriptions, creating cumbersome pages of text that weary eyes had to parse by flickering candlelight. A merchant might write out entire sentences merely to explain that a single chest of flax contained a few ounces beyond the standard measure, or that a vat of oil fell slightly short of its expected volume. This tedious process weighed heavily on the minds of storekeepers at the close of long market days. A change arrived quietly through the growing art of print, where single ink marks could capture complex thoughts in a fraction of a second without cluttering the page. In 1489 in Leipzig, German mathematician Johannes Widmann published Behend und Rechnung asterisk, introducing the plus, and minus symbols into print to denote small surpluses and deficits in merchant crates resting in quiet market warehouses. The little cross of the plus sign, adapted from a fluid Latin shorthand for and, along with the clean, horizontal stroke of the minus sign, provided a soft visual anchor upon the page. No longer did a merchant need to write tedious phrases to show that a cask held 2 extra pounds or was short by 3. Instead, these minimalist symbols stood as quiet sentinels of balance, making arithmetic feel as natural and unhurried as sorting river stones into smooth linen bags. The print run of Widmann's handbook traveled gently from hand to hand, carried along cobblestone streets and across misty river valleys by traders who found deep comfort in its practical clarity. Within its pages, numbers began to cast off their bulky verbal wrappings, dressing instead in a clean, elegant attire that allowed calculation to flow with effortless grace. As accountants and storekeepers adopted these simple marks, a shared visual language took root throughout the bustling trading hubs of Northern Europe, easing the mental labor of calculation and inviting a restful clarity into the quiet counting houses of the late medieval world. Further south, where the stone palaces of Venice rose softly above tranquil waters, another great current of mathematical order was taking shape inside the quiet rooms of a monastic study. Venice was a city of echoes and light, where ships from distant ports arrived under pale morning skies, their holds laden with silks, aromatic resins, glass beads, and hand-bound manuscripts from foreign lands. Here, The flow of maritime trade required an even deeper sense of harmony, a system that could reflect not merely the weight of individual goods, but the entire living breath of a commercial enterprise over time. Every purchase, every loan, every partnership, and every long voyage across open seas created a complex web of financial obligations that needed to be held in perfect, peaceful balance. It was within this reflective atmosphere that a devoted monk and scholar turned his mind to organizing the vast array of arithmetic tools that had accumulated across centuries of European and Mediterranean commerce. In 1494, in Venice, Franciscan friar Luca Pacioli published Summa de Arithmetica Asterisk, formalizing double entry bookkeeping by pairing terms debito asterisk and asterisk credito across smooth paper pages to bring serene order to merchant ledgers. Pacioli's comprehensive volume was a masterpiece of typographic care, printed on fine rag paper that felt soft beneath the fingers, and held the deep black ink of the Venetian presses with pristine sharpness. By establishing the rule that every entry on the left side of a ledger, representing what was owed or placed into trust, must be exactly matched by a corresponding entry on the right side, representing what was given or withdrawn. He transformed record-keeping into a quiet, meditative practice of numerical equilibrium. The terms debito asterisk and credito asterisk, derived from the Latin concepts of obligation and trust, acted as two resting weights on a finely tuned scale, ensuring that no value appeared or vanished without leaving a clear, harmonious trail. Merchants who adopted Pacioli's method discovered that at the end of a long day of transactions, the act of balancing their books offered a soothing sense of closure, as the total sums on opposing pages settled smoothly into equal alignment. This elegant symmetry freed the mind from worry, replacing chaotic piles of loose notes with structured, bound ledgers, where every coin found its rightful place. Printed on the celebrated presses of Venice, Pacioli's work traveled along maritime routes and alpine passes, spreading the comforting discipline of double entry ledger, keeping to accounting rooms across the continent, where it quieted financial uncertainties and established an enduring standard of truth. As the new century dawned, these dual innovations in practical mathematics, the simple clarity of operational signs and the balanced symmetry of ledger entries, began to weave themselves seamlessly into the broader tapestry of human thought. What had started as humble tools for storekeepers and maritime traders slowly softened the rigid boundaries between daily commerce and abstract philosophy. Scholars resting in quiet university libraries began to realize that if plus and minus signs could represent physical surpluses and deficits in timber or spice, they could also represent pure numerical relationships, independent of any material object. Similarly, the realization that an equation is simply a ledger brought into perfect balance allowed mathematicians to view numbers as harmonious entities seeking resolution. The page of a mathematical text began to look less like a dense forest of Latin words and more like an open, tranquil landscape where symbols danced with calm, rhythmic precision. The mental space saved by using simple signs and structured columns allowed thinkers to contemplate far larger questions, drifting gently from basic arithmetic into the vast, quiet realm of symbolic algebra. In this unfolding era, calculation ceased to be an exhausting chore of long division and verbal proofs. It became a quiet, contemplative stroll through orderly gardens of thought, where every operation was clearly marked and every balance was naturally maintained. As night fell over the historic cities of Europe, from the foggy alleys of Leipzig to the moonlit canals of Venice, candle flames flickered softly in quiet rooms where scholars and merchants alike laid down their quills. The numbers on their pages rested in neat, balanced rows, undisturbed by the passage of time. The simple plus, the tranquil minus, and the unwavering symmetry of debit and credit had transformed the world of numbers into a peaceful haven of order, offering to the human mind a serene sanctuary where every equation settles softly into place, leaving only the quiet comfort of absolute clarity. As the intellectual landscape of 16th century Europe slowly unfolded into a time of quiet reflection and systematic inquiry, the manner in which human minds recorded and pondered mathematical truths underwent a serene, gradual transformation. For many generations, those who sought to resolve the hidden relationships within numbers had relied entirely upon long, descriptive prose, writing out every calculation and unknown value in full, unbroken narrative. In this older tradition, known to later historians as rhetorical algebra, an equation was not a compact visual pattern upon a page, but a spoken story, a slow, measured recitation of quantities added, subtracted, and multiplied through continuous sentences. A scholar seeking to express a square root or an unknown factor had to guide the reader through an elaborate passage of text, carefully describing each step of the journey with patience and care. Yet, as scholars sat in the calm silence of their studies, surrounded by sheepskin manuscripts and the faint scent of ink, a profound desire for visual elegance and mental rest began to take hold. The mathematical discoveries of the Italian peninsula, where thinkers had gracefully referred to the unknown quantity as asterisk cosa asterisk, meaning simply the thing, drifted quietly northward across the Alpine, passes into the bustling towns of the Rhineland and Central Europe. Those who practiced this specialized craft of calculating the unknown became known as the casuists, individuals who spent their quiet hours weaving arithmetic into a more orderly visual discipline. In their hands, the study of numbers began to shed its cumbersome verbal weight, moving away from heavy sentences toward a language that could communicate deep numerical truths without unnecessary noise. It was a delicate threshold in human history, where the spoken word began to yield to silent, beautifully balanced symbols, inviting the mind to perceive complex relationships effortlessly, as though gazing upon a still and perfectly balanced landscape. In the vibrant city of Strasbourg, nestled near the gentle curve of the Rhine, this search for visual clarity found one of its most lasting and tranquil expressions. The year was 1525, a time when the relatively new art of printmaking was filling workshops with the soft thrum of wooden hand presses and the comforting smell of damp rag paper and oil-based ink. Among the scholars working within this creative atmosphere was a mathematician named Christoph Rudolph, who set out to compose a comprehensive textbook designed to introduce the methods of casuist algebra to students and artisans alike. Rudolph recognized that reading page after page of dense mathematical text could easily tire the eyes and clutter the imagination, especially when dealing with the repeated extraction of roots. In earlier times, scribes had written out the Latin word radix, meaning root or foundation, whenever they wished to indicate that a number should be traced back to its underlying side or square. Sometimes this word was shortened to a simple letter. But on a crowded page, even isolated letters could blur into the surrounding text. Sitting at his desk with a wooden block carver nearby, Rudolph sought a gesture that would be both swift to write with a quill and unmistakably clear when carved into a relief block for printing. With a quiet and intuitive stroke of penmanship, he took the lowercase letter *R*, the initial letter of *radix*, and gently elongated its upper stroke, letting the fine line reach out over the top of the numerical digits that followed. In 1525, in Strasbourg, mathematician Christoph Rudolph published cos*, introducing the modern square root symbol by softly elongating the lowercase letter *R*, for *radix across the wooden block prints of his algebra manual. This small, graceful modification transformed a simple letter of the alphabet into a restful visual shelter, wrapping the number inside a protective canopy that signaled to the reader's eye exactly where the operation began and where it came to rest. The introduction of this elongated radical symbol was far more than a mere spatial convenience for the printer's workshop. It represented a profound, gentle shift in how human consciousness interacts with abstract ideas. When a reader opens a mathematical manuscript governed entirely by rhetorical prose, the mind must continuously parse grammar, word order, and syntax before reaching the underlying quantitative truth, adding a layer of subtle exertion to every step of reasoning by placing a single, sweeping mark over numerical value. Rudolph allowed the eye to absorb the operational instruction instantaneously, freeing the intellect from the burden of verbal decoding and allowing it to rest peacefully upon the core harmony of the mathematical relationship itself. Underneath the delicate overhang of the radical sign, numbers seemed to sit in quiet equilibrium, shielded from ambiguity, and held within a calm, well-defined sanctuary on the page. As copyists, teachers, and fellow scholars examined the crisp pages of Rudolph's manual, they immediately recognized the serene efficiency of his design. The practice of using intuitive visual signs to replace repetitive phrases began to spread softly across Western Europe, passing through the lecture halls of Central European universities, the busy trading houses of the Low Countries, and the secluded libraries of England. Other mathematicians in subsequent decades would refine and build upon this notation, eventually linking the radical symbol with a horizontal line to cover longer algebraic expressions. Yet the essential curve born in Strasbourg remained constant, anchoring the visual language of algebra for centuries to come. Each time the symbol was drawn with a quill or pressed into rag paper, it carried forward a quiet philosophy of design. That clarity is found by stripping away excess words, leaving only the essential structure to shine in calm, uncluttered simplicity. In this way, mathematics was gradually transformed into a visual art of stillness, where intricate numerical patterns could be contemplated without effort, inviting a deep sense of order into the mind of anyone who paused to read its restful lines. As night fell over the print shops of the Renaissance, and the candle flames flickered down in quiet rooms across the continent, the silent revolution of notation continued to shape the future of human thought. The work of Christoph Rudolph and his fellow casuists established a foundation upon which later thinkers, such as Francois Viet and René Descartes, would construct the modern symbolic algebra that we recognize today. Where once algebra had been a dense forest of descriptive language, requiring immense patience to navigate, it was becoming a clear, open meadow of symbols, where ideas could move fluidly and rest without friction. The square root symbol, born from the humble elongating of a handwritten letter R, remains one of our most enduring monuments to this quiet transition, a gentle bridge connecting the physical world of roots and measurements to the serene realm of pure abstraction. To look upon a mathematical equation formatted in this symbolic shorthand is to witness a triumph of human stillness, where complex truths are held in perfect balance by just a few graceful lines upon a page. As the centuries have passed, millions of students and thinkers have traced that same soft, sloping line over numbers, perhaps without realizing that they were recreating a quiet gesture crafted centuries ago in a peaceful Strasbourg print shop. In the stillness of evening, as we reflect on the long story of numbers, from the ancient stones counted by starlight to the elegant symbols resting in modern books, we find that mathematics is not merely a tool for calculation, but a quiet language of peace, offering a calm and structured refuge for the wandering mind. As the soft light of the 16th century deepened across the quiet studies and scriptoriums of Europe, the study of numbers was undergoing a subtle, graceful transformation. shifting slowly from the heavy cadence of spoken prose toward a visual language of tranquil clarity. For many centuries before this gentle turning point, thinkers who sought to unravel the mysteries of quantity, measure, and proportion had to record their insights using long, elaborate sentences, writing out every relationship in full words that stretched across pages of thick parchment like slow-moving, winding streams. In the stillness of evening, illuminated only by the warm, flickering glow of a candle, or the fading indigo light of dusk beyond a tall window, a mathematician working through a problem would be obliged to write out phrases such as is equal to, is equivalent to, or is made identical unto dozens upon dozens of times. This rhetorical tradition, inherited from medieval scholars and ancient philosophers, possessed a formal dignity. Yet it imposed a quiet burden upon the human mind, filling pages with dense text to convey relationships that were, at their core, pure, simple, and light. The mind, seeking stillness and effortless understanding among complex ideas, longed for visual marks that could convey these connections, instantly soothing anchors that would allow the gaze to glide across the page without pausing to read repetitive verbal statements. In this reflective era of early printing and expanding scholarly correspondence, thinkers across the continent began to experiment with delicate shorthand, searching for simple strokes of ink that could capture the innate harmony of mathematical balance. They sought a way to demonstrate that two different expressions, though composed of distinct digits, symbols, or unknown quantities, held within them the exact same intrinsic value, resting side by side in quiet, unwavering equilibrium. It was a search not merely for brevity or convenience, but for an aesthetic and intellectual harmony, a way to make the invisible order of truth visible, serene, and immediately reassuring to the human eye. It was within this atmosphere of patient scholarship and quiet innovation that the Welsh mathematician, physician, and educator Robert Record sat down to compose a comprehensive treatise on algebra, a book he tenderly titled The Whetstone of Wit Asterisk, which was published in London in the year 1557. Record was a scholar of notable warmth and empathy, devoted to making the art of calculation accessible to students and curious readers in their own native English tongue, rather than concealing mathematical beauty behind obscure Latinate jargon. As he worked methodically through the manuscript, arranging long sequences of algebraic equations, he found himself growing weary of repeating the phrase, is equal to, over and over upon every single page of his work. In the peaceful quiet of his study, surrounded by stacks of bound leaves and the gentle scratching of a feather quill, he resolved to design a symbol that would express this fundamental relationship with absolute purity, economy, and visual grace, seeking a design that could convey complete fairness, balance, and exact identity without requiring a single spoken syllable. He chose to place upon the paper two twin parallel lines of identical length, drawn horizontally side by side, because, in his quiet reasoning, no two things in all of creation could be more equal. These twin lines, crafted with deliberate care, provided an immediate, intuitive resting place for the reader's eyes, capturing the essence of perfect equivalence far more beautifully than any lengthy sentence ever could. Record understood that two parallel lines of equal length travel forward together in total harmony, never drifting apart and never encroaching upon one another, maintaining between them an enduring space of serene balance. With this gentle innovation, introduced almost softly within a textbook written to refine and sharpen the intellect, the modern equals sign was given to the world, taking its place upon the page as a timeless monument to the peaceful simplicity that rests at the heart of all mathematical thought. The introduction of these twin parallel lines brought a profound sense of calm and visual rest to the practice of algebra, transforming the page from a dense thicket of words into an open landscape of balanced thought. Prior to the arrival of Recordsmark, an algebraic manuscript could feel heavy and demanding, requiring the reader to maintain intense vigilance simply to locate where one side of a statement ended and the next began. With the simple equals sign positioned quietly at the center of an expression, the entire equation suddenly took on the serene posture of a balanced scale resting in perfect stillness, where the left side and the right side hung in complete and effortless harmony. This visual symmetry allowed mathematicians to contemplate complex relationships with a tranquil mind, as the twin lines acted as a peaceful fulcrum, holding two equivalent truths in balance without tension or strain. Over the decades that followed, as copies of the Whetstone of Wit traveled through university libraries, private studies, and quiet reading rooms, scholars across Europe gradually recognized the quiet wisdom embedded in Record's choice. Although the adoption of new symbols was a slow and gentle process, as long-established habits yield only gradually to new ways of seeing, the intrinsic beauty of the two parallel lines eventually prevailed over all other competing notations, such as written abbreviations, single bars, or elaborate floral symbols. By the middle of the 17th century, mathematicians in distant lands, speaking different languages, and living under vastly different skies, were using these exact same two horizontal strokes to join their mathematical thoughts, creating an unbroken, silent bridge of understanding that transcended borders and brought a shared tranquility to scientific discourse. The symbol was so simple, so natural, and so restful to behold that it quickly felt as though it had always existed, waiting patiently in the quiet realm of geometry until a gentle scholar called it forth to bring peace to the written page. When we reflect upon the long journey of human thought, tracing the path of numbers from ancient counting stones pressed into soft river clay to the elegant abstractions of modern algebra. The emergence of such quiet, elegant symbols stands as a testament to our enduring desire for clarity and peace. The twin lines introduced by Robert Record do far more than merely shorten our writing. They offer the mind a place to rest, reassuring us that despite the apparent complexity or length of an expression, an underlying harmony holds everything in quiet balance. In the still atmosphere of evening study, where thoughts move with the slow, soothing rhythm of a calm tide, these symbols allow intricate mathematical truths to settle gently into place, requiring no struggle, no noise, and no unnecessary words. As night falls softly across the land, and the busy activities of the day give way to deep rest, the timeless order of mathematics remains constant, motionless, and serene, like distant stars keeping their silent watch across the nocturnal sky. Each symbol, crafted by thoughtful hands centuries ago, continues to serve its quiet purpose, inviting us to release our daily anxieties and trust in the steady, balanced laws that govern the cosmos. In this peaceful realm, where the left side and the right side rest as one, we can quietly close our eyes, knowing that all things are held in perfect, enduring balance, aligned in complete and unbroken stillness. As the late 16th century settled over the quiet cities of Western Europe, the way human minds recorded and calculated quantities underwent a profound, peaceful transformation, replacing centuries of cumbersome reckoning with a soft, rhythmic clarity. For generations, trade merchants, navigators, astronomers, and scholars had navigated the intricate world of broken quantities, the fractions of whole units, by relying on complex, varied systems that often required laborious mental effort to convert, add, or divide. A merchant measuring bolts of fine cloth or weighing sacks of spice in a bustling market had to struggle with differing denominators and regional measurement units, while scholars tracking planetary paths spent long hours untangling sexagesimal fractions inherited from ancient Babylonian astronomy. In 1585, in the quiet printing shops of Leiden, Flemish mathematician Simon Steven published Asterisk de Thiend, introducing simple decimal notation that allowed scholars and trade merchants to tally fractions with effortless ease. By demonstrating that the familiar base 10 place value system could gracefully extend beyond the single unit mark into tenth parts, hundredth parts, and thousandth parts, Steven opened a doorway to unprecedented simplicity. No longer did arithmetic demand intricate conversions between unwieldy numerators and denominators. Instead, numerical values flowed continuously across a modest mark on the page, moving smoothly down through smaller and smaller powers of 10. In the quiet rooms where ledgers were kept, ink was dipped onto parchment with a new, tranquil efficiency, as calculations that once required entire sheets of scrap paper were reduced to a few gentle strokes of the pen. Merchants sitting beside glowing candles could tally their daily accounts without pausing to wrestle with fractional remainders, and builders could calculate structural dimensions with a serene precision that matched the peaceful order of the evening. Steven's little booklet, modest in physical size, yet vast in its ultimate impact, helped demystify the art of computation, transforming what had been an obscure craft known only to specialized reckoners into an intuitive, accessible skill for everyday life. As night fell over the misty canals of Holland, the steady cadence of pen on paper signaled a world coming into harmony with a simpler, more elegant language of measure. With the arrival of decimal notation, the realm of numbers became far easier to navigate. Yet another subtle barrier still stood between thinkers and the deeper structures of mathematical truth. For centuries, the discipline that we now recognize as algebra was conducted almost entirely in prose, a method often referred to by historians as rhetorical algebra. When ancient Babylonian scribes, classical Greek geometers, or medieval Islamic scholars sought to solve a problem involving unknown quantities, they had to describe every step using long, descriptive sentences written in their native languages. An equation was not a clean, balanced line of symbols, but rather a quiet, winding story about a square, a side, a pile of coins, or a missing sum, written out word by word across dense pages of manuscript. To find an unknown number, a reader had to follow a delicate narrative trail, holding multiple verbal concepts in mind at once, and carefully tracking how each quantity transformed as the sentence progressed. While this narrative style possessed a certain literary charm, it made complex abstract reasoning extraordinarily heavy and slow, as the human mind had to constantly translate dense paragraphs of text back into underlying numerical relationships. Scholars sat beneath soft lamplight, reading page after page of descriptive instructions, just to balance two opposing sides of a single problem, searching for a clearer, more serene way to glimpse the universal laws governing numbers. There was a growing desire for a visual language that could transcend individual spoken tongues, a peaceful shorthand that would allow the essential architecture of an equation to shine forth without the clutter of extraneous words. This longing for structural clarity found its fulfillment in the quiet countryside of Western France, where the slow rhythm of rural life provided a peaceful setting for deep intellectual contemplation. In 1591, in the tranquil Loire Valley of France, scholar Francois Viet introduced symbolic algebra by consistently assigning vowels to unknown variables and consonants to known constants, turning pages of wordy prose into serene, compact equations. By choosing a systematic convention using vowels such as A, E, and I to represent quantities yet to be discovered, and consonants like B, C, and D to stand for fixed, known parameters, Viet elevated algebra from a collection of isolated problem-solving tricks to a unified, general science of form. Before his work, a mathematician solving a problem about lengths or areas had to work through specific numerical examples, treating each new scenario as a fresh puzzle to be described in full prose. Viet's symbolic innovation allowed thinkers to see the overarching rules that governed entire classes of equations at once, holding general principles in a single, balanced line of text. The visual landscape of the mathematical page was transformed overnight. Dense, sprawling paragraphs melted away into crisp, elegant formulas where relationships between knowns and unknowns sat in calm equilibrium. One could look at a single, brief arrangement of letters and immediately understand how the parts depended upon one another, without needing to decipher long paragraphs of explanations. In the quiet solitude of his study, surrounded by the gentle rustle of leaves along the Loire River, Viet had crafted a universal alphabet for thought, a silent, tranquil notation that freed the human mind to soar above specific numbers into the quiet ether of pure mathematical structure. The dual breakthroughs of Stevin's decimals and Viet's symbolic variables together laid the silent, enduring foundation upon which modern mathematics would comfortably rest. Within a single remarkable decade, at the end of the 16th century, the act of thinking with numbers had been gently untangled from the weight of tradition, where calculation had once been a noisy, friction-filled effort of converting awkward fractions and parsing long verbal instructions. It now became a quiet contemplation of pure form and continuous measure. Decimal points allowed the infinitely small to be written with the same easy grace as the immensely large, creating a smooth continuum of numbers that reflected the calm, unbroken flow of time itself. Meanwhile, symbolic algebra provided a quiet mirror for the mind, reflecting abstract truths in tidy, balanced equations that required no translation across borders or languages. Scholars across Europe could read the work of their distant peers with immediate, effortless understanding, as a shared visual language began to unite minds across vast distances in a quiet, collective search for truth. As the quiet hours of the night deepen and the world outside softens into sleep, we can appreciate how these humble symbols, simple dots on parchment, and soft arrangements of letters brought a deep sense of order to our understanding of the universe. The chaotic complexity of the physical world, from the orbits of distant stars to the rhythmic sway of ocean tides, could finally be captured in peaceful, compact lines of code, offering the human mind a serene sanctuary of clarity and rest. As the late 16th century drifted into the early decades of the 17th, a quiet revolution began to transform the way humanity observed the natural world. As astronomers, mariners, and natural philosophers sought to unlock the hidden geometries of the earth and the heavens. Across Europe, the night sky was no longer viewed merely as a static dome of fixed lamps. but as a vast, living tapestry governed by subtle mathematical harmonies that invited precise, patient measurement. In cold stone observatories, high castle turrets, and quiet domestic studies, scholars sat beneath the dark canopy of night, adjusting brass quadrants, armillary spheres, and early telescopes to track the subtle wandering of planets across the zodiac. Yet, behind every breathtaking realization of cosmic order lay an invisible and crushing weight of manual computation. To calculate the position of a ship amidst dark ocean waves, to forecast a lunar eclipse, or to map the intricate path of Mars across the night sky required working with sprawling trigonometric tables filled with sines, cosines, and tangents, calculated to 7 or 8 decimal places. Skywatchers, cartographers, and mathematicians found themselves trapped in a grueling ritual of arithmetic, spending endless, quiet hours performing long multiplication and tedious long division with numbers that stretched across the full width of their parchment pages. By the dim, flickering light of tallow candles, a scholar might spend an entire evening multiplying 2 10-digit numbers together, meticulously carrying digits from column to column, adding endless subproducts, and repeating the entire arduous process again and again to guard against inevitable human error. The physical toll of this work was immense. Eyes grew weary, hands cramped over ink-stained leaves, and a single misplaced digit could quietly unravel days of careful astronomical observation, turning what ought to have been a restful, inspiring contemplation of the universe into an exhausting trial of mental endurance. The grand era of exploration and scientific discovery was in danger of grinding to a halt under the sheer friction of hand calculation. There grew across the scholarly world an unspoken, deep-seated longing for relief, a gentle mathematical key that might simplify these heavy computational burdens, transforming the rigid, sharp edges of long arithmetic into a smooth, quiet stream, so that the human spirit might spend less time locked in mechanical labor and more time resting in the calm beauty of the stars. High above the rolling hills and misty pastures of Scotland, within the thick stone walls of Merchiston Castle near Edinburgh, a solitary scholar spent his life contemplating this very challenge. John Napier, the Laird of Merchiston, was a man of deep intellect, quiet contemplation, and profound patience, who preferred the solitude of his private library to the noisy affairs of public life. From the windows of his secluded castle tower, he looked out across the quiet Scottish landscape, where mist gathered in the valleys and rain fell softly upon the ancient trees. Inside his sanctuary, surrounded by shelves of classical texts, mathematical instruments, and piles of handwritten notes, Napier pondered how the fundamental operations of numbers might be reimagined to lighten the burden of human thought. He began to explore a mesmerizing concept based on the relationship between geometric sequences, numbers that grow by multiplication, and arithmetic sequences, numbers that step forward by simple addition. Through deep, meditative reflection, Napier visualized 2 points moving along parallel paths. One point moving at a steady, uniform speed, stepping forward at equal intervals, while the other point moved at a speed proportional to its remaining distance, slowing down as it approached its destination. He realized that if numbers could be mapped along these corresponding paths, the complex relationship of multiplication between values in the geometric progression could be perfectly mirrored by the far simpler act of adding their corresponding markers in the arithmetic progression. To bring this vision into practical reality required an astonishing display of devotion and mental stamina, working entirely by hand, without the aid of any mechanical calculating devices. Napier spent years constructing exponential tables of breathtaking complexity, calculating millions of ratios with meticulous, unwavering precision to establish a universal system of transformation. In 1614, Scottish scholar John Napier published his invention of logarithms after spending 20 years in his quiet castle tower, laboriously compiling mathematical tables to turn tedious long multiplication into simple addition for stargazers, coining the term logarithm from the Greek words logos asterisk, meaning ratio, and arithmos asterisk, meaning number. Napier introduced his work to the world in a modest Latin treatise titled Asterisk Mirafis Logarithmorum Canonis Descriptio, or a description of the wonderful law of logarithms asterisk. With this landmark publication, he offered scholars everywhere a quiet sanctuary of computation, where the exhausting labor of multiplying multi-digit numbers collapsed effortlessly into the peaceful, gentle routine of adding 2 numbers together. The news of Napier's discovery spread across the European continent like a gentle, warming breeze, bringing immediate comfort and quiet relief to a generation of scholars who had long suffered under the weight of manual arithmetic. When the renowned German astronomer Johannes Kepler first received a copy of Napier's logarithm tables, he was in the very midst of analyzing decades of dense observational data regarding the orbit of Mars, a heroic mathematical effort that would eventually yield his famous laws of planetary motion. Kepler embraced the logarithm tables with profound gratitude, declaring that Napier's invention had effectively tripled an astronomer's working lifespan, freeing skywatchers from the wearying prison of manual calculation and allowing them to devote their energy to interpreting the true harmony of the heavens. Inspired by this breakthrough, an English mathematician named Henry Briggs traveled to Scotland to meet the aging scholar in his castle. Together, in a spirit of warm collaboration, they refined the system into base 10 logarithms, creating the common logarithms that made decimal calculations even more intuitive and fluid. This elegant numerical framework soon took physical form in the hands of inventors like Edmund Gunter and William Ovid, who transferred logarithmic scales onto straight and circular wooden rules by placing two marked wooden scales side by side and sliding them smoothly past one another. Sailors at sea, architects on land, and scientists in their laboratories could instantly perform complex multiplications, divisions, and square roots simply by measuring distances with their eyes, giving birth to the slide rule, a quiet, handheld tool that would remain an indispensable companion for human progress for over 3 centuries. Beyond its practical utility, the discovery of logarithms marked a profound turning point in the history of mathematics, bridging the gap between arithmetic and continuous algebra, and demonstrating that complex operational relationships could be translated into simple, elegant forms. As candle flames flickered low in observatories around the world, scholars no longer dreaded the arrival of the night's calculations. Instead, they turned the soft pages of logarithmic tables with a sense of calm serenity, knowing that the grandest mysteries of the universe could now be approached with ease, leaving the mind free to rest in the quiet, timeless harmony of the cosmos. As the evening quiet settled over the towns, universities, and countryside of 17th century Europe, the ancient study of mathematics was gently expanding its gaze from the static forms of earthly geometry to the sweeping, continuous motions of the night sky. For thousands of years, scholars across different civilizations had cataloged the movements of light across the darkness, recording planetary positions on wet clay tablets, drawing intricate parchment charts, and calculating exhaustive tables of chords and signs with extraordinary, quiet patience. Yet beneath these diligent collections of numbers lay a deeper, more serene question that had intrigued philosophers since antiquity: whether the physical universe itself was fashioned according to an underlying mathematical architecture, a silent and harmonious order wherein geometry, proportion, and arithmetic moved together in absolute unison. Earlier thinkers had long envisioned the celestial spheres as rigid, unyielding circles of perfect constancy. But as observational methods grew more refined and specialized instruments measured the subtle shifts of the wandering stars with unprecedented accuracy, a far richer and more nuanced truth began to take shape. Mathematics was no longer merely a practical tool for counting seasonal harvests, dividing plots of land, or tracking commercial debts. Nor was it restricted to the fixed, unchanging shapes of classical Euclidean proofs. It was steadily evolving into a subtle, universal language capable of expressing continuous change, dynamic velocity, and the invisible threads of geometric harmony that bound distant celestial bodies to one another. In the stillness of long night watches, as candles flickered softly against pages filled with handwritten figures, logarithmic tables, and delicate geometric diagrams. Mathematicians began to realize that the gentle, rhythmic speed of a planet as it traveled through its celestial path was not arbitrary or accidental, but governed by precise, immutable numeric relationships. This gradual awakening to dynamic mathematics transformed the dark expanse of the cosmos into a vast, peaceful canvas of natural law, inviting curious minds to look past the superficial appearance of chaotic skyward motion and discover a deep, comforting symmetry that bridged the physical world of observation with the pure, tranquil abstractions of human mathematical thought. It was within this atmosphere of patient, contemplative inquiry that Johannes Kepler spent years immersing himself in the immense treasury of astronomical observations gathered by Tycho Brahe, searching for the subtle mathematical rules that governed the paths of the planets. Working in Austria amidst a period of great personal hardship and widespread historical uncertainty, Kepler sought solace and quiet clarity in the eternal constancy of numerical order, remaining firmly convinced that the geometric proportions of the heavens reflected a divine, serene harmony. He laboriously calculated and recalculated the orbit of Mars over many years, courageously discarding old, cherished assumptions of uniform circular motion when the empirical data revealed minute discrepancies of mere arc minutes that could not be ignored by an honest observer. This relentless devotion to precision led him to the groundbreaking realization that planetary paths were not circles at all, but subtle ellipses with varying velocities as their distances from the sun continuously changed throughout their journeys. In 1619, in Linz, astronomer Johannes Kepler published Harmonics Mundi Asterisk, translating the varying orbital speeds of planets into quiet musical intervals on a 5-line stave to derive his third law of planetary motion through geometric ratios. In this landmark publication, Kepler demonstrated that when a planet reached its perihelion, its closest approach to the sun, moving at its swiftest pace, its heightened angular velocity corresponded to a higher, more energetic note on his conceptual musical stave, whereas at its distant aphelion, moving at its slowest and most leisurely reach, it resonated with a lower, calmer pitch. By mapping these subtle variations in speed as exact mathematical ratios corresponding to musical intervals, such as major and minor thirds, fifths, and octaves, he elegantly bridged the ancient quadrivium of arithmetic, geometry, astronomy, and music, ultimately demonstrating that the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. This profound discovery revealed that celestial motion was not an unyielding, monotonous repetition, but a gentle, continuously shifting symphony of geometric proportions, where every planetary path was linked to the others by a shared, harmonious measure that maintained the quiet equilibrium of the entire solar system. The revelation that natural dynamic motion could be transcribed onto a musical stave and captured through precise geometric ratios marked a pivotal moment in the history of mathematics, demonstrating that abstract numbers possessed the unique power to reveal hidden truths about the physical world that lay far beyond direct human touch or visual perception. For centuries prior to this era, algebra had developed primarily as a practical technique for solving localized equations and balancing unknown quantities across equal signs, while geometry had remained largely focused on the spatial properties of fixed lines, angles, and two-dimensional figures. Here, in the quiet pages of Kepler's astronomical works, these distinct streams of human reasoning began to flow together into a unified understanding of physical systems. By viewing the varying orbital speeds of the planets not as chaotic or inexplicable irregularities, but as smooth, continuous transitions between harmonious mathematical ratios, mathematicians began to cultivate an entirely new way of contemplating rate of change and continuous movement. The ancient view of numbers as static, discrete counters gradually gave way to a far more fluid understanding of numbers as dynamic expressions of ongoing relationships, where spatial distance, elapsed time, and orbital velocity were permanently intertwined through elegant mathematical proportions. This conceptual evolution allowed natural philosophers across Europe to see that the physical cosmos was not governed by arbitrary or disjointed forces, but by a tranquil geometric logic that operated with perfect, unwavering consistency across immense gulfs of space and vast spans of time. As scholars read these harmonic derivations in quiet libraries and university halls, they came to appreciate that mathematics was far more than an artificial tool invented by human societies to manage practical daily affairs. It was an intrinsic, serene language embedded within the very fabric of nature, waiting patiently across the ages to be understood by those who looked closely at the numbers describing the sky. As the quiet work of 17th century astronomy merged into the broader, unfolding history of mathematics, the discovery of these celestial harmonies opened the doorway to the development of modern calculus and classical mechanics, providing the necessary mathematical foundation for Isaac Newton and later thinkers to formulate the universal laws of gravitation. The realization that planetary orbits followed strict geometric proportions transformed the night sky from a mysterious, inscrutable vault into a deeply peaceful, predictable sanctuary of order, where every cosmic movement could be understood through gentle ratios, continuous curves, and balanced equations. In the quiet solitude of study rooms, observatories, and candlelit workspaces, the reassuring truth took root that the very same geometric principles governing the distant, majestic sweep of Saturn or Jupiter also governed the soft, parabolic trajectory of a falling leaf, or the rhythmic, soothing swing of a pendulum on Earth. Mathematics had bestowed upon humanity a calm and enduring lens through which to contemplate the vastness of the universe, replacing mystery and uncertainty with a quiet, abiding clarity grounded in verifiable numerical law. Tonight, as we reflect upon the long and tranquil journey of human thought, from the earliest tally marks carved into bone and counting stones resting on ancient riverbanks, to the intricate harmonic staves and geometric ratios of planetary motion, we can feel a profound sense of stillness in knowing that the universe moves according to such steady, beautiful principles. The planets continue their silent, unhurried journeys through the quiet dark, sweeping out their elliptical paths in perfect geometric proportion, carrying forward the timeless, peaceful music of numbers into the deep, restorative calm of the night. As the early decades of the 17th century unfolded across Europe, the study of numbers was quietly shifting from an arduous mechanical labor into a more meditative art of visual alignment and structural harmony. For generations, scholars, astronomers, and mariners had spent endless nocturnal hours submerged in long, exhausting columns of arithmetic, multiplying and dividing vast multi-digit figures by hand beneath the dim flicker of candlelight. Every voyage across uncharted oceans and every subtle tracking of planetary motion demanded pages upon pages of scratchwork, where a single misplaced digit could corrupt hours of careful thought. When John Napier first introduced the concept of logarithms to the world, he opened a serene pathway that transformed tedious, repetitive multiplication into the soft and manageable act of addition. Yet, even with these expansive printed tables of logarithmic values, a mathematician still had to turn page after page, cross-referencing numbers and writing down intermediate totals upon scrap sheets in the quiet study rooms and workshop quarters of London. Thinkers began to wonder whether the abstract beauty of logarithms could be carved directly into tangible materials, whether wood, brass, and physical length could take on the burden of calculation, so that the human mind might find a welcome pause. The air of 17th century England was filled with a subtle spirit of practical invention, where instruments of navigation and survey were crafted with meticulous patience from fine boxwood, ivory, and polished metal. There was a growing realization that numbers did not need to remain static ink trapped upon parchment. Instead, they could be transformed into spatial distances, stretched out along a straight edge where the eye and hand could interact with mathematical truth in a calm, intuitive rhythm. As natural philosophers observed the orderly movements of tides and heavenly bodies, they sought calculation methods that mirrored this underlying calm, seeking tools that reduced friction, quieted mental noise, and allowed mathematical thought to flow as smoothly and effortlessly as a slow-moving river through a peaceful, silent landscape. This peaceful evolution of mathematical craft reached a particularly elegant milestone in the quiet workshops along the River Thames. In 1620 in London, mathematician Edmund Gunter plotted logarithmic values along a 2-foot wooden measuring scale, using a pair of brass dividers to gently step between markings and multiply numbers without written calculations. Known simply as Gunter's line or Gunter's scale, this remarkable invention condensed complex arithmetic into a graceful dance of spatial measurement. By laying out numbers along a physical line according to their logarithmic proportion, the distance between one and any given number reflected its true logarithmic weight. When two numbers needed to be multiplied, one did not need to perform long written computations or consult dense books of reference tables. Instead, a practitioner merely adjusted the fine points of a pair of brass dividers to measure the physical span of the first value, and then gently pivoted those brass legs along the rule to add that distance onto the second value. The sharp, polished tips of the compass touched down softly against the smooth boxwood grain, stepping from one etched line to another with silent, reliable precision. In this tactile process, multiplication became an act of physical walking, where spatial distance replaced mental strain and complex numerical relationships were revealed through the simple geometry of length. Navigators standing on the rolling deck of a ship could now determine ratios, compute trigonometric proportions, and calculate trade routes with quiet confidence, needing only a steady hand, a well-marked rule of wood, and the rhythmic stepping of brass points. Gunter's wooden rule brought a profound sense of ease to practical mathematics, demonstrating that abstract numerical laws could be embodied in simple, elegant tools that allowed scholars and navigators to rest their minds while maintaining absolute precision across the vast and silent expanses of the sea, while physical instruments like Gunter's rule were simplifying numerical calculations. A parallel quiet revolution was taking place on paper, where scholars sought to streamline the visual language of algebra itself. For centuries, mathematical statements had been written out in full conversational sentences, burdened by long Latin phrases or cumbersome abbreviations that made reading complex equations feel like deciphering dense prose. To determine whether one quantity was greater or smaller than another, mathematicians had to write lengthy explanatory phrases which obscured the elegant symmetry hiding within their equations. Amidst the secluded studies of early modern England, scholars recognized that clear, minimalist notation could clarify thought just as effectively as a wooden scale could ease arithmetic. In 1631 in London, the posthumously published treatise Artis Analytici Praxis by mathematician Thomas Harriot introduced the inequality signs dollar and using subtle angled brackets to neatly balance smaller and larger quantities across manuscript pages. Harriet's brilliant innovation replaced cumbersome text with two simple, intuitive symbols that opened towards the larger value and converged to a point toward the smaller. Printed carefully upon the page, these slender brackets allowed the eye to immediately grasp the dynamic balance of an inequality without the distraction of redundant words. The symbol gently guided the reader from a lesser quantity to a greater one, while seamlessly reflected the reverse relationship, establishing a visual harmony that felt both natural and effortless. In the quiet layout of Artie's Analytici Praxis Asterisk, equations ceased to be tangled strings of words and became spacious, balanced compositions where relationships were visible at a single glance. Harriet's simple angled marks bestowed a serene clarity upon algebra, creating a visual language that transcended spoken tongues and allowed mathematical ideas to settle into the mind with profound restfulness and order. Together, these quiet breakthroughs in instruments and symbols transformed mathematics from a heavy, laborious chore into an inviting landscape of clarity and calm. Through the gentle stepping of Gunter's brass dividers along a boxwood scale and the peaceful balance of Harriet's slender inequality signs, the 17th century laid the groundwork for an era where computation and algebra could be practiced with fluid grace. The human mind was no longer required to hold vast columns of figures in memory or decipher convoluted paragraphs of mathematical text. Instead, it could rest quietly upon intuitive visual lines and harmonious symbols, as each mathematical concept found its natural resting place, whether physically marked upon polished wood or elegantly printed upon rag paper. Scholars were granted the freedom to focus on deeper underlying truths. Numerical calculations and algebraic expressions became harmonious arrangements, guiding thought effortlessly into tranquil understanding. As night settles over the history of numbers, we can appreciate how these thoughtful creations eased the human burden, turning the pursuit of truth into a quiet, peaceful journey where every mark on paper and every line on wood brings a comforting sense of order, balance, and quiet repose to the world. As the early 17th century settled over the quiet countryside of Western Europe, a subtle yet profound transformation was taking place within the quiet studies of scholars and natural philosophers. For many centuries, the work of mathematics had been conducted through long, descriptive passages of text, where every numerical operation was expressed in full sentences written by hand across sheets of parchment and heavy rag paper. Mathematicians translated their geometric insights and arithmetic steps into elaborate prose, describing the scaling of quantities, the division of parts, and the balancing of equations through continuous verbal narratives that required great patience to read, copy, and comprehend. While this tradition of rhetorical algebra had carried mathematical thought through many generations. It gradually created a dense landscape of words that could weigh heavily upon the inquiring mind. Slowly and gently, a collective movement emerged among scholars to seek a more peaceful visual shorthand, a quiet language of subtle marks and balanced signs that could allow numbers and their relationships to rest upon the page with effortless clarity. In sunlit scriptoriums and serene home libraries, illuminated by the soft flicker of candlelight, thinkers began replacing long Latin phrases with small, elegant symbols designed to guide the eye smoothly across mathematical expressions without distraction. The handmade paper of the era held these newly fashioned characters with a tranquil dignity, transforming long paragraphs of calculation into spacious arrangements where equations could breathe, revealing their underlying symmetries at a single glance. This shift was not driven by urgency or speed, but by a deep appreciation for mental stillness and visual order, allowing the human mind to bypass the friction of redundant words and move directly into restful contemplation of ratio, magnitude, and form. In the midst of this gentle era of notation reform, a quiet minister and devoted scholar passed his days in a peaceful Surrey parish, where the calm rhythms of rural life provided a harmonious backdrop for his lifelong study of mathematics. William Audid was a man of deep contemplation who found great joy in teaching young students and organizing the mathematical knowledge of his time into clear, accessible forms. Within his quiet parish at Albury, surrounded by rolling green hills, old oak trees, and the soft murmur of country lanes, English mathematician William Audid published *Clavis Mathematici* in 1631, introducing the diagonal cross, symbol \$ dollar for multiplication, by neatly paring down the St. Andrew's cross to align arithmetic factors across laid paper. Audid recognized that when two numbers were set side by side to be multiplied, the traditional practice of writing out words or using awkward abbreviations disrupted the visual flow of calculation. By taking the broad, sweeping form of the heraldic St. Andrew's cross and carefully trimming its arms into a compact, perfectly balanced diagonal sign, he created a symbol that sat comfortably between numbers, matching the height and proportion of surrounding numerals. When rendered in dark iron gall ink on the textured surface of laid paper, the small diagonal cross provided a clear visual anchor, showing precisely how two quantities were linked in multiplication without cluttering the page. The Clavis Mathematici*, whose title translated softly to the key to mathematics asterisk, served as a gentle handbook for generations of learners, offering them a refined set of symbolic tools that simplified complex calculations and rendered the structure of algebra far more intuitive. The creation of the multiplication cross reflected a broader philosophy of design, that prioritized harmony, visual space, and the conservation of mental energy during intellectual work. Before Ovid's elegant symbol gained acceptance, scholars had tried various ways of indicating multiplication, sometimes placing letters between numbers or relying on contextual notes in the margins, which often caused confusion for printers and readers alike. The trimmed diagonal cross solved this dilemma with quiet grace, offering a distinct mark that could not be easily mistaken for an addition sign or a letter of the alphabet. As ink dried upon the laid paper in Ovid's Algebra study, the symbol seemed to settle naturally into the rhythm of written mathematics, allowing factors to align neatly across horizontal lines of text. This visual order granted a restful ease to the scholar's eye, as complex multi-step problems could now be laid out in neat rows, where each step followed the previous one like steps along a peaceful garden path. The diagonal cross did not merely save space on the page. It freed the mind from unnecessary cognitive burden, allowing the mathematician to hold higher-level abstractions in focus without getting lost in verbal phrasing. Ovid's devotion to clarity also inspired his work with logarithmic scales, where he would later lay the groundwork for the circular and linear slide rules, physical instruments that translated these same symbolic relationships into smooth, mechanical movements. Through all his contributions, Ovid maintained a modest and serene presence, working quietly in his parish study to make the vast landscape of numbers more approachable and serene for all who wished to enter it. As the years drifted softly onward, the small diagonal cross published in the quiet village of Albury journeyed far beyond the borders of Surrey, finding its place on the desks of mathematicians across Europe and eventually around the world. Scholars at Oxford, Cambridge, and continental universities recognized the quiet utility of Ovid's notation, adopting the multiplication sign into their own textbooks, manuscripts, and correspondence, alongside other evolving symbols of the era, such as the plus and minus signs, the radical sign for roots, and the gentle parallel lines of the equal sign. The diagonal cross helped construct a universal visual language that transcended spoken tongues. This shared mathematical script allowed ideas to travel effortlessly across distant lands, enabling thinkers who spoke different languages to read each other's work with immediate understanding and peace of mind. Today, when a child first learns to draw two small crossing lines between two numbers on a clean sheet of paper, they are participating in a quiet legacy that stretches back to the peaceful parish rectory of Albury in 1631. The transformation from counting stones and heavy verbal descriptions to light, balanced symbols stands as one of humanity's most tranquil achievements, a gentle refining of thought that turned the study of mathematics into a quiet meadow of order, clarity, and rest. As night falls softly over historical libraries and quiet modern studies alike, these timeless symbols continue to rest upon the page, carrying the mind smoothly into a state of quiet wonder and peaceful sleep. The evolution of mathematical thought often unfolds not through sudden, disruptive discoveries, but in quiet moments of prolonged reflection, where the gentle boundaries separating distinct fields of human inquiry softly dissolve into a unified vision of order. For many centuries following the golden age of classical antiquity, the exploration of spatial form and the study of numerical relationships proceeded along two parallel yet distinct paths, each possessing its own traditions, tools, and serene ways of understanding the world. Geometry was long celebrated as the supreme art of spatial intuition, expressed through the visual elegance of straight lines, sweeping arcs, and precise geometric constructions drawn upon sand, parchment, or smooth vellum. Ancient geometers trained their minds to see the intrinsic harmony of shapes, triangles whose internal angles quietly summed to two right angles, circles defined by the constant distance of their perimeter from a central point, and regular solid forms whose mathematical symmetries reflected the architectural order of the natural cosmos. Algebra, by contrast, had grown along a very different trajectory, originating as a practical and symbolic language designed to calculate unknown quantities, balance commercial transactions, and resolve numerical puzzles through structured steps of arithmetic reasoning. Although both disciplines sought to illuminate the underlying patterns of reality, they remained separated by a subtle conceptual divide. Numbers were viewed as discrete counts or static measures of quantity, whereas geometric figures were perceived as continuous spatial forms that could not easily be reduced to simple numerical expressions. A curve was understood as a physical locus traced by a moving point or formed by the intersection of solid shapes, while an algebraic equation remained a sequence of symbolic statements far removed from the visual realm. For generations, natural philosophers recognized that a deeper connection must exist between the shapes we observe in the physical world and the abstract equations that describe their behavior. Yet the precise language capable of uniting them had not yet been forged. This peaceful separation left a quiet void at the heart of mathematical science, waiting for a unifying framework that could allow spatial curves to speak in the language of numbers and enable abstract equations to reveal their hidden beauty as visible landscapes flowing across a calm, well-ordered plain. In the early decades of the 17th century, this long-sought synthesis began to take form amidst the serene landscapes of Northern Europe, where the slow pace of rural life provided the stillness required for deep, uninterrupted contemplation. It was in this atmosphere of quiet seclusion that the French philosopher and mathematician René Descartes chose to spend many years of his adulthood, deliberately stepping away from the distractions of Parisian society in order to cultivate a calm space for philosophical and mathematical inquiry, preferring long mornings of quiet thought spent in the warmth of his study. He observed how the simple intersection of lines on a wall or ceiling could provide a fixed, reliable reference for describing position, movement, and form. In 1637, while residing in the quiet Dutch countryside of Egmond Binnen, René Descartes published La Géométrie asterisk, unifying algebra and geometry by using lowercase letters $, $y, and $z to represent unknown lengths along intersecting axes. At the center of this revolutionary yet soothing framework lay the concept of two perpendicular lines meeting at a single, silent point of origin, creating an unshakable grid of reference across an infinite plane. The horizontal axis offered a gentle, continuous measure of lateral position, while the vertical axis measured height and depth, allowing any point in space to be designated by a precise pair of numerical coordinates. By representing spatial dimensions as continuous numerical lengths, Descartes bridged the ancient divide between discrete arithmetic and continuous geometry, demonstrating that a point's location was simply a matter of measured distance from these central reference lines. Furthermore, by assigning the final lowercase letters of the alphabet to represent unknown or variable lengths along these axes, he established a clear symbolic convention where algebraic equations could be directly translated into geometric shapes. Under this unified system, an equation containing two variables was no longer just an abstract numerical puzzle. It was an exact rule governing a path through space, where every valid solution corresponded to a specific point on the coordinate plane. A straight line became the visual manifestation of a simple linear equation, while smooth, flowing curves, such as parabolas, hyperbolas, and circles, emerged as the natural geometric expressions of quadratic equations, bringing a luminous clarity to both disciplines. The creation of coordinate geometry transformed the landscape of human thought, offering a calm and elegant language that allowed mathematicians to analyze complex natural phenomena with unprecedented ease and grace. Shapes that had once required intricate geometric proofs could now be explored through the steady, step-by-step application of algebraic rules, replacing long sequences of visual deductions with clear, methodical calculations. When a thinker wished to understand the path of a planet drifting across the night sky, or the soft trajectory of a raindrop falling through the evening air, they no longer had to rely solely on complex physical models or static geometric drawings. Instead, they could trace the curve as a continuous equation unfolding smoothly across a coordinate grid. This harmonious fusion allowed operations in algebra to take on immediate geometric meaning. Shifting an equation by a constant value gently moved its corresponding curve across the plane, without altering its shape, while multiplying its terms expanded or compressed the curve with fluid symmetry. By demonstrating that spatial form and numerical relationship are merely two expressions of the same underlying truth, coordinate geometry provided a restful clarity to the mind, reassuring scholars that the physical universe operated according to a unified and intelligible harmony. This peaceful bridge between shape and symbol laid the indispensable foundation for future mathematical discoveries, opening the path for the development of calculus, classical mechanics, and the modern mapping of physical forces. As the quiet mantle of night settles over the long history of mathematical thought, the coordinate plane stands as a timeless testament to human curiosity, reminding us how a simple grid of intersecting lines can bring order to infinity, allowing every point to find its quiet place and every curve to move in peaceful alignment with the laws of number and space. As the 17th century unfolded across the quiet towns and countryside of Western Europe, the journey of human mathematical thought entered a period of peaceful reflection, where the dramatic discoveries of earlier eras settled into a calmer, more contemplative rhythm. Scholars and thinkers, moving beyond the immediate need to establish basic arithmetic and symbolic notation, began to look more deeply into the subtle architecture of numbers themselves, seeking an underlying order that felt both elegant and restful to the inquiring mind. In private studies shielded from the noise of daily life, where heavy velvet curtains softened the faint sounds of the evening street and wax candles cast a warm, flickering glow over wooden writing desks, mathematics became a quiet art of patience. The air in these sanctuaries of thought was filled with the gentle scent of aged paper, leather bindings, and dried oak gall ink, creating an environment perfectly suited for slow, deliberate contemplation. Here, dusty volumes of ancient Greek texts, works by Euclid, Apollonius, and Diophantus of Alexandria, lay open beside modern manuscripts, bridging centuries of human curiosity through silent conversation. Scholars found profound comfort in comparing ancient geometric intuition with the newer language of symbolic algebra, noticing how abstract variables could describe timeless numerical truths with newfound clarity and ease, rather than treating numbers merely as practical tokens for ledger books, land surveying, or trade. These quiet seekers viewed them as endless landscapes waiting to be explored with gentle curiosity. The slow passing of nighttime hours seemed to expand the mind's capacity for quiet wonder, allowing thinkers to sit undisturbed as they traced the subtle relationships between primes, squares, and higher powers, finding in their balance a reassuring stability that mirrored the steady movement of the stars above. It was precisely within this soothing environment of solitary evening study that the French jurist Pierre de Fermat found his greatest intellectual joy, spending his leisure hours immersed in the profound mysteries of arithmetic. living a modest and peaceful life in southern France. Fermat sought neither academic prestige nor public acclaim, preferring instead the tranquil solitude of his personal study after long days spent attending to his legal duties in the local magistrate. His favorite companion during these quiet evening hours was a heavy Latin translation of Diophantus's ancient work on algebraic equations, a text filled with intriguing problems concerning the properties of integers. In 1637, at his quiet desk in Toulouse, French jurist Pierre de Fermat scribbled a subtle note in the wide outer margin of his copy of Diophantus's Arithmetica, proposing his famous theorem, while noting the parchment margin was just slightly too narrow to contain the full proof. This brief and elegant inscription, written in a fine hand alongside a problem discussing how to divide a square number into two other squares, suggested that no three positive integers could satisfy the relationship where two numbers raised to a power greater than two sum to a third number of the same power. Fermat did not feel the pressing urge to publish his thoughts or rush to demonstrate his reasoning to the world. He was content simply to record the insight for his own quiet satisfaction, allowing the thought to rest peacefully upon the cream-colored parchment. The unwritten proof lingered like a quiet secret within the margins of his book, requiring no immediate validation, but offering instead a timeless riddle that would gently challenge and inspire mathematicians for more than 3 centuries to come. As the ink slowly set into the fibers of the paper, Fermat likely closed the volume and retired for the night, leaving his profound conjecture to sleep undisturbed beneath the cover of the ancient book, a testament to the calm joy of intellectual discovery for its own sake. A few years later, in another quiet corner of France, a different yet equally gentle expression of mathematical ingenuity took form, born from a son's deep filial devotion and a desire to bring ease to human labor. In the historic city of Rouen, nestled along the quiet waters of the Seine, young Blaise Pascal spent long evenings watching his father, Etienne, labor over mountainous stacks of official financial documents and tax assessments. The senior Pascal was a meticulous public servant whose duties required endless hours of manual summation, meticulously adding long columns of figures by the soft light of a tallow candle, while the household slept around him. Moved by a profound empathy for his father's fatigue, the young prodigy resolved to create a mechanical instrument that could perform these tedious calculations automatically, sparing the human mind from the exhausting monotony of constant mental carrying and totalizing. In 1642, in Rouen, 19-year-old Blaise Pascal built a mechanical calculator called the Pascaline, crafting brass gears and ivory dials inside a polished oak box that softly clicked to total financial tallies. Inside the elegant wooden housing lay a delicate system of interconnected wheel trains, spring-loaded levers, and carefully calibrated gear teeth designed to perform carry operations automatically. whenever a dial completed a full rotation from 9 to 0. The soft, rhythmic clicking of the internal brass components as they turned provided a soothing tactile feedback, transforming the heavy weight of financial accounting into a gentle, fluid process of mechanical harmony. Pascal spent months refining the precision of each hand-cut gear and smooth ivory faceplate, ensuring that the machine would operate effortlessly without jamming or slipping. Through this marvelous creation, calculation was transformed from a tedious mental strain into a serene mechanical dance, demonstrating how human ingenuity could construct physical tools to lighten the burdens of daily life, leaving the human spirit free to rest in calm contemplation. The quiet achievements of Fermat in Toulouse and Pascal in Rouen represented two complementary streams of mathematical thought, flowing peacefully into the modern era, one reaching inward toward the pure, abstract beauty of numbers, and the other extending outward into the physical, tangible world of mechanical calculation. Though working in different cities and addressing distinct challenges, both men shared a common devotion to bringing order, clarity, and serenity to the human mind through the language of mathematics. In time, their intellectual paths would gently cross through a warm and famous exchange of letters, wherein they collaboratively explored the mathematical foundations of chance and probability, laying down the quiet principles that govern games of outcome with remarkable poise and mathematical grace. Their correspondence was marked by deep mutual respect and a restful curiosity as they exchanged ideas across the calm distances of 17th century France without urgency or rivalry. The Pascaline had shown that human arithmetic could be entrusted to the quiet rotation of brass wheels, while Fermat's marginal note proved that simple questions about integers could hold infinite depth, waiting patiently for centuries to reveal their secrets. Together, these quiet discoveries offered a profound sense of comfort, demonstrating that whether written in ink upon the margins of an old book or embodied in the soft clicking of ivory dials, mathematics provided an enduring framework of peace and structure. As night deepened over the quiet rooftops of Europe, the gentle harmony of numbers continued to weave its soothing tapestry across the human imagination, inviting minds to quiet their restless thoughts and rest securely in the eternal, orderly beauty of the universe. As the evening quiet deepens and the world softens into stillness, the human mind naturally turns toward thoughts of peaceful expanse, seeking horizons that stretch beyond the narrow boundaries of daily tasks. In the long history of mathematical thought, a similar transition occurred when thinkers began to move beyond the immediate arithmetic of counting stones, measuring fields, and recording trade. For many centuries, numbers had been used to track the finite, the sheep in a pasture, the days in a seasonal cycle, or the coins in a purse. Yet beneath all these practical measurements, there always lay a quiet, underlying awareness of something far larger. A subtle recognition that numbers themselves have no final resting place, but continue outward in a tranquil, unending procession. To gaze upon the series of whole numbers was like looking up into a clear midnight sky, where every visible star is accompanied by countless others, fading softly into the dark of the cosmos. Early philosophers and geometers contemplated this boundlessness with a sense of gentle wonder, realizing that between any 2 points on a smooth line, one could imagine an endless sequence of smaller locations, just as within any quiet span of time, moments could be divided into ever finer drops of duration. In these early reflections, infinity was not viewed as a chaotic or overwhelming storm, but rather as an open, silent realm of potential, a calm ocean whose waters reached past the edge of mapmakers' charts. The ancient Greek geometers had approached this realm cautiously, using careful methods of exhaustion to calculate areas and volumes, wrapping their ideas in long paragraphs of precise prose. Medieval scholars, too, had filled manuscript pages with subtle distinctions, debating whether infinity could ever be fully present, or if it must always remain a horizon toward which one moves step by step. Yet despite all their deep insights, they lacked a simple, unified mark upon the page, a quiet visual anchor that could capture the concept of endlessness in a single stroke of ink. Their written thoughts on the infinite were like long, winding rivers flowing through dense forests of text, beautiful and profound, but waiting for a clearer, more restful language to emerge as the centuries turned. The turn of the 17th century brought a profound shifting in the rhythm of European mathematics, as natural philosophers began to look at the world through the lens of continuous change, geometry, and symbolic notation. In this era of quiet intellectual transformation, scholars no longer viewed algebra merely as a set of practical rules for finding unknown quantities, but as a flexible, expressive language capable of describing smooth curves and moving points. Libraries across the continent were filled with the gentle scratching of quill pens as mathematicians sought to standardize symbols for addition, subtraction, equality, and powers, weaving an elegant shorthand that allowed complex ideas to be seen at a glance. Amid this blossoming of symbolic thought, the ancient university town of Oxford stood as a peaceful refuge for deep study, its quiet stone quadrangles and shadowed halls providing a serene setting for mathematical contemplation. Here, among the high shelves of historic books and the soft light filtering through leaded window panes, scholars worked diligently to trace the properties of curves that extended indefinitely into space. It was within this reflective atmosphere, in 1655 at Oxford, that the English mathematician John Wallis published Asterisk de Sectionibus Conicis Asterisk, introducing the serene side-lying loop backslash infti dollar to represent infinity, drawing inspiration from the ancient Roman numeral for 1,000 to depict endless continuity. In this landmark treatise, dedicated primarily to the geometry of conic sections, such as ellipses, parabolas, and hyperbolas, Wallis found himself repeatedly working with expressions that involved endless series and lines that stretched without limit toward distant asymptotes. Rather than burdening his text with repeated, laborious descriptions of boundlessness, he placed this smooth, flowing glyph directly into his calculations, offering the mathematical world a tranquil shorthand that instantly conveyed the concept of an unceasing journey across space and number. To understand the quiet beauty of the symbol $, one must look back into the subtle history of numerical script, where visual forms evolved over centuries to hold large and mysterious quantities. In ancient Rome, before the standardized letter M became the universal sign for 1,000, scribes often recorded the number using a curved symbol that resembled CO, a central vertical stroke flanked by inward curving arcs, or sometimes a figure resembling an enclosed loop or a stylized sign for a vast multitude. To the Roman mind, 1,000 was not merely a precise count of 10 hundreds, but a poetical metaphor for an immense, almost uncountably large sum, a gathering so great that it blurred into a general sense of abundance. John Wallis, deeply versed in classical scholarship as well as mathematics, recognized in these ancient epigraphic forms a visual resonance that could be gently adapted to a higher purpose. By taking the closed, rounded structure of the ancient Roman sign and relaxing its form into a single, continuous, side-lying loop, he created a mark that had neither a beginning nor an end. The symbol $, often referred to as a lemniscate from the Latin word for a hanging ribbon, allowed the quill to trace its path smoothly without ever lifting from the parchment or encountering a sharp corner. Unlike standard numerals that stand firm with distinct starting and stopping points, this peaceful symbol moves in a perpetual, balanced curve, rising gently in one loop, crossing its own center, and curving with equal grace into its twin. When placed within an equation, the symbol did not represent a rigid, static quantity, but rather a quiet state of unbounded progression, a mathematical haven where values could grow beyond any fixed limit while remaining held within a single, harmonious visual form. The introduction of the infinity symbol marked a quiet turning point in how mathematicians conceptualized the vast, transforming the infinite from a source of philosophical hesitation into a serene and usable element of mathematical language. In the decades that followed Wallis's publication, thinkers across Europe, including Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany, were laying the foundations of calculus, a branch of mathematics built entirely upon the study of continuous change and infinite processes. The presence of the graceful loop / infti dollar provided these pioneers with a peaceful visual anchor, enabling them to express limits, infinite series, and integrals with an elegance that was previously unimaginable. When a scholar wrote of a line extending toward infinity, or a sum accumulating across endless terms, the side-lying loop stood at the edge of the equation, like a quiet beacon in a calm harbor, reassuring the mind that boundlessness could be contemplated with perfect clarity and order beyond its practical utility in formal calculations. The symbol \infti dollar slowly expanded into the broader human consciousness, becoming a universal emblem for eternity, continuous flow, and the quiet harmony of the universe. Its balanced form mirrors the natural cycles of the world around us, the rise and fall of the gentle breath, the unending motion of ocean, waves rolling against a silent shore, and the soft, perpetual rotation of stars across the evening sky. When we reflect upon this simple mark, drawn with a single smooth movement of pen on paper, we are reminded of the profound peace that comes from finding order within the infinite. Just as the night sky invites us to rest under a canopy of endless stars, the serene loop invites our thoughts to unwind, letting go of small daily measures and settling into the quiet, restful rhythm of eternal space and time. As the deep, velvet quiet of evening settles across the rolling hills and tiled roofs of 17th century Europe, the long history of human counting seems to pause for a quiet breath, gathering its centuries of progress into a calm and reflective stillness. From the early days when distant ancestors gently pressed tally marks into soft clay or arranged smooth pebbles along dusty trade routes, mathematics had continuously expanded, seeking ever larger frameworks to measure the earth, trace the slow dance of the planets, and order the commerce of growing towns. The discovery of zero had given the world a quiet anchor of nothingness, around which all numbers could comfortably revolve. And the elegant symbols of algebra had transformed complex word problems into delicate balances of unknown quantities. Yet, as the shadows lengthened across scholarly studies, lit only by the soft, amber flicker of candlelight, a quiet desire emerged to strip away all unnecessary complexity, looking past the 10 digits of human hands toward something more fundamental, tranquil, and eternal. In the calm solitude of these late hours, when the bustling noise of daytime trade faded into the night air, natural philosophers began to realize that the vast, intricate tapestry of numbers might be woven from a far simpler pair of threads. It was a time of quiet reflection, where the pursuit of mathematical truth felt less like a restless effort of computation and more like a peaceful meditation on the hidden order of the universe, inviting the mind to rest upon the calm geometry of simple lines, quiet surfaces, and the rhythmic balance between presence and form. It was within this atmosphere of patient wonder that the German polymath Gottfried Wilhelm Leibniz found himself contemplating the deep symmetry of numbers while sitting by his hearth during the long, dark season of the year. In 1679 in Hanover, Gottfried Wilhelm Leibniz drafted his binary number system on smooth laid paper, assigning ones and zeros to represent creation and stillness. After studying the ancient grid structures of Chinese asterisk, I Ching asterisk diagrams during quiet winter evenings, through letters sent across vast distances by scholars and travelers, Leibniz had received woodblock prints detailing the 64 hexagrams attributed to the ancient sage Fuzai. Each diagram composed of stacked lines that were either continuous and whole or gently split down the middle. As he traced these geometric patterns by the soft glow of his lamp, he recognized that these ancient diagrams were not merely symbolic figures, but an elegant, forgotten system of binary notation that matched his own mathematical reflections with quiet perfection. Where others saw simple divination charts, Leibniz saw a profound universal harmony in which a solid line embodied the active, illuminating force of unity, the number 1, while a broken line represented the receptive, calm space of nothingness, the number 0. The smooth laid paper beneath his ink pen became a quiet canvas where the infinite variety of all numbers was born from nothing more than the gentle interplay of these two basic states, stepping forward in a serene and orderly progression. Each stroke of his quill was deliberate and soft, recording how 0 and 1 could weave together to form 2, 3, 4, and every integer beyond, requiring no extra characters, no elaborate tables, and no complicated rules of calculation. In the quiet solitude of his Hanover study, the vast landscape of arithmetic seemed to simplify itself into a slow, rhythmic lullaby of presence and rest, bridging the deep wisdom of ancient Asian philosophy with the emerging light of modern mathematical thought. As the winter wind whispered softly outside the window panes, the beauty of this binary rhythm revealed a deep mathematical elegance that felt both revolutionary and comforting in its absolute clarity. In standard decimal counting, numbers march forward through 10 distinct digits, accumulating weight and complexity as they swell into tens, hundreds, and thousands, demanding memory and effort to keep track of their changing places. But in the gentle cadence of Leibniz's binary system, counting becomes as natural and serene as the slow rising and falling of a resting chest, moving gracefully through simple columns of ones and zeros. 0 stands as the silent lake before a ripple appears, a state of complete, unruffled peace where nothing is demanded and all possibilities remain dormant. 1 enters as a single, quiet spark of presence, marking the beginning of form and light, a solitary note sounding in the stillness. When 1 and 0 align, they do not push against each other, but step side by side in perfect balance, turning the simple count of 2 into a neat pair of digits, 1 and 0, that echoes the cosmic harmony of light and shadow, night and day, breath and rest. As the numbers grow gently higher, 3 becoming 1 and 1, 4 shifting softly into 1, 0, 0. The progression creates a hypnotic visual pattern across the page, a sequence of quiet pulses that can represent any number, any equation, and any logical thought imaginable. This fundamental simplicity meant that arithmetic no longer required complex memorization of multiplication tables. For multiplying by 0 leaves absolute stillness, and multiplying by 1 leaves the original light unchanged. In this peaceful framework, algebra found its ultimate distillation, reducing complex relationships into basic logical choices of truth and falsehood, presence and absence, allowing the mind to wander effortlessly through complex mathematical ideas without becoming burdened by cumbersome calculations. Looking back through the long passage of time, this quiet draft, written on a cold Hanover night, stands as a gentle bridge, connecting the ancient stone counters of early humanity to the silent, invisible calculations of the distant future. The journey of mathematics had traveled across vast continents and through countless civilizations, from the notch-carved bones of early African hunters to the sun-baked clay tablets of Mesopotamia, from the geometric proofs of ancient Greece to the brilliant algebraic manuals of 9th century Baghdad. Yet here, in the soft twilight of the 17th century, all of those vast rivers of human thought seemed to converge into a single, peaceful stream composed of just 2 digits resting peacefully upon paper. Binary arithmetic did not arrive with noise or display, but emerged like a calm night sky settling over a quiet world, offering a framework so light and pure that it would eventually allow mechanical gears, electric circuits, and distant computational devices to think without friction. But in this quiet hour, long before machines would hum with binary logic, the system remained a pure aesthetic dream, a vision of a cosmos held together by the gentle alternation of existence and tranquility, where every grand structure of thought could be rested upon the simplest foundation. As the lamp flame dims to a soft, lingering embers in the hearth, the mind can let go of equations, digits, and calculations, settling into the quiet space between 1 and 0. The air grows soft, the room settles into shadows, and the steady, peaceful beat of binary harmony wraps around the quiet dark, guiding every lingering thought into a deep, restoring sleep. As the 17th century drew toward its quiet middle years, across the sea in Japan, a unique and luminous tradition of mathematical thought was unfolding in serene isolation. Known as Wasan, this native art of numbers flourished during the long, undisturbed peace of the Edo period, where scholars, artists, and thinkers cultivated knowledge with the same deliberate patience and reverence for natural beauty that guided classical calligraphy. tea ceremonies, and garden design. In this peaceful atmosphere, separated from the rapid changes occurring in distant European universities, Japanese mathematicians approached problem solving not as a hurried search for practical utility, but as a form of contemplative practice, a quiet dialogue between abstract order, spatial pattern, and the physical world. The tools of Wasson were inherently tactile and visual, designed to bring subtle thought into gentle harmony with spatial form. Calculation was carried out upon fine wooden boards marked with delicate grid lines, using small rectangular blocks and slender rods that could be shifted by hand with soft, rhythmic movements across the smooth surface. To observe a mathematician at work in Edo was to witness a scene of profound stillness, daylight filtering softly through translucent paper shoji screens, the subtle scent of fresh rush straw rising from woven tatami mats, and the faint, resonant click of smooth wood against wood as equations were arranged, rearranged, and settled into quiet equilibrium. Rather than relying solely on abstract written symbols strung across long pages of text, this tradition mapped mathematical relationships directly into two-dimensional space, transforming complicated algebraic challenges into balanced arrangements of geometric clarity. In doing so, Wasson demonstrated that the human search for numerical truth is universal, yet deeply shaped by the quiet environments in which minds are allowed to reflect without distraction, laying a gentle foundation for discoveries that would echo across the history of global science. At the heart of this mathematical renaissance stood Seki Takakazu, a master of profound vision, whose quiet insight illuminated the subtle structure underlying complex systems of equations. In 1683, in Edo, Japanese mathematician Seki Takakazu developed the mathematical foundation of determinants, arranging small wooden counting blocks called asterisk sangi into precise grid patterns across quiet tatami mats to solve complex simultaneous equations. The sangi, crafted with exquisite care from polished hardwoods, bamboo, or smooth ivory, were small, narrow rectangular blocks laid upon a sandbin. A specialized counting board or paper sheet divided into neat, regular rows and columns. Each block represented a specific numerical quantity or coefficient. Its physical orientation, whether placed vertically or horizontally, signifying positive or negative values, while its position within a particular square marked its variable degree and power. With calm, unhurried precision, Seki would arrange these physical tokens across the floor of his study, transforming abstract algebraic statements into tangible, spatial landscapes of numbers, where others saw a daunting array of interconnected unknown variables. Seki recognized that the relationships governing these numbers could be captured by cross-multiplying and balancing the entries within the grid rows. By systematic elimination, moving the sangi gently across the board like pieces in a thoughtful game of Go, he derived mathematical rules could condense complex networks of simultaneous linear equations into single, manageable expressions. This breakthrough, accomplished years before similar concepts were formalized in Western Europe by mathematicians like Gottfried Wilhelm Leibniz, allowed scholars to determine whether a system of equations possessed a unique solution simply by analyzing the structural symmetry of its matrix of coefficients. The quiet sound of Sangi resting on tatami became the sound of structural algebra coming into being, showing how physical mindfulness and abstract thought can meet in perfect, tranquil alignment. The discovery of determinants brought an unprecedented clarity and ease to the study of algebra, offering a serene method to navigate complex systems without becoming lost in tedious, repetitive calculations. Before Secchi's profound realization, solving several interrelated equations simultaneously required laborious substitutions, where every additional variable increased the risk of error and obscured the underlying mathematical pattern. By arranging the numbers into systematic two-dimensional arrays, the determinant revealed an intrinsic property of the system as a whole, a single scalar value that acts like a master key, unlocking the system's behavior in one unified motion. One can picture these grids of numbers as calm pools of water, where ripples from different mathematical forces intersect and resolve into quiet stillness. When the rows and columns of coefficients are cross-multiplied according to Secchi's precise rules of diagonal expansion, the resulting determinant indicates whether the lines or planes represented by the equations meet at a single harmonious point, overlap in complete agreement, or run parallel in eternal quietude. This elegant spatial view transformed algebra from a collection of isolated numerical tricks into a coherent, structured discipline where spatial architecture and numerical truth merged into one. Mathematicians across Japan could now handle higher degree equations and multivariate systems with remarkable poise, passing their findings down through handwritten manuscripts filled with meticulously drawn grid diagrams and elegant commentary. The true beauty of Secchi's method lay not only in its mathematical power, but in its visual simplicity. A complex web of numerical relationships could be understood visually at a single glance, allowing the mind to rest upon the order of the grid rather than struggle against the weight of unstructured numbers. As night falls gently over ancient Edo, and the small wooden sangi are packed away into their cedar boxes, the legacy of Secchi Takakazu endures as a lasting testament to the quiet majesty of mathematical discovery. His pioneer work on determinants was a vital bridge in the global history of mathematics, prefiguring modern linear algebra, the spatial framework that today underpins everything from computer graphics and architectural engineering to theoretical physics and network science. Yet, in its original setting, Wasan remained a private art of deep tranquility, cultivated for the pure joy of uncovering eternal truth within physical form and numerical balance. The grid patterns that once lay spread across quiet tatami mats remind us that mathematics is fundamentally a search for harmony, a gentle way of organizing the complexities of the universe into clear, balanced structures that bring rest to the inquiring mind. As we reflect on the long, unfolding story of numbers, from simple notches carved into ancient bone and stones counted on dusty soil to the sophisticated wooden arrays of Edo, we see a continuous human endeavor to find stillness within complexity. Each historical step forward in algebra has been a step toward simplifying the intricate, allowing us to see vast systems of thought reduced to gentle, elegant principles. The spatial insight born on tatami mats shows that order need not be forced. When numbers are given their proper place, they resolve into equilibrium on their own. Now, as thought softens into rest, the neat grids of Sengi fade into the quiet background of memory, leaving behind a profound sense of balance, spatial harmony, and calm repose. As the light of the 18th century began to settle softly across the quiet study rooms of Europe, the study of mathematics was undergoing a gentle and profound transformation, gradually replacing long, descriptive sentences with a harmonious, universal shorthand of symbols. For thousands of years, thinkers across diverse cultures had marveled at the quiet constancy of the circle, recognizing that whether one observed a massive stone wheel, a polished silver coin, or a subtle ripple expanding on the surface of a silent pond, the ratio between the distance around its rim and the distance straight across its center remained forever unchanged. Ancient scholars in Babylon, Egypt, Greece, India, and China had devoted endless hours of quiet contemplation to measuring this fundamental proportion, calculating its value to ever greater degrees of precision. Yet, for generations, it lacked a single, unified mark to represent its presence on paper. Instead, mathematicians were forced to write out lengthy descriptions or rely on approximate fractions whenever they sought to express the relationship between a circle's outer edge and its inner diameter. This lack of a shared symbol meant that geometric calculations often appeared cluttered and dense, filled with repetitive phrases that obscured the underlying beauty of the mathematical relationships being explored. Yet, as the scientific world grew more interconnected, a collective desire emerged for a cleaner, more restful way to express these eternal truths. Thinkers realized that by assigning specific, elegant characters to fundamental constants, they could free the human mind from tedious verbal descriptions and allow the innate harmony of numbers to shine through with luminous clarity. This silent revolution in notation transformed mathematical manuscripts from dense blocks of prose into visual compositions of tranquil elegance, setting the stage for a new era of mathematical discovery, where ideas could be shared effortlessly across borders and languages, bringing a quiet sense of order to the vast complexity of the natural world. It was within this growing atmosphere of symbolic clarity that a modest Welsh teacher and mathematician made a lasting contribution to the visual language of science. In 1706, in London, Welsh mathematician William Jones published Synopsis Pomerium Mathesios asterisk, choosing the Greek letter \$, short for periphery asterisk, to represent the constant ratio of a circle's circumference to its diameter across quiet manuscript pages, drawing upon the ancient Greek word peripheria, which described the outer boundary or circumference of a curved shape. Jones recognized that this single, graceful character could serve as a serene placeholder for an infinite numerical relationship. By placing the letter \$, into his textbook, he offered scholars a peaceful way to hold an endless, non-repeating decimal within a single, elegant glyph that rested lightly upon the page, to encapsulate such an infinite mystery within two simple vertical strokes. And a gentle horizontal cap brought a soothing sense of calm to natural philosophy, allowing mathematicians to write down complex equations governing circular motion, wave phenomena, and planetary orbits with newfound elegance. Over the decades that followed, as other great minds adopted and popularized the notation across Europe, the symbol \$, quietly took root in the global mathematical consciousness, becoming an enduring emblem of geometric harmony. The adoption of \$, demonstrated how a thoughtful choice of notation could quiet the mind, replacing cumbersome arithmetic with a symbol that invited contemplation and rest. As ink dried on delicate sheets of paper, scholars could gaze upon the letter and reflect on the silent, perfect symmetry of the circle without becoming lost in endless strings of calculated digits. In this way, the simple letter \$, bridged the finite realm of human writing with the infinite nature of continuous curves, offering a quiet sanctuary of order where geometry and algebra could meet in peaceful accord, while notation brought a restful simplicity to the study of continuous curves. Other mathematicians began to turn their attention toward the quiet patterns hidden within physical landscapes and human pathways, seeking to understand how places and connections interlock. Far to the east, along the Baltic coast, lay the historic city of Königsberg, where daily life unfolded at a tranquil pace beside the waters of the Pebbles River. The river flowed gently through the heart of the town, splitting into two wide, reflective streams that encircled a central island before winding onward toward the sea. To connect the various quarters of the city separated by these cool currents, 7 wooden bridges were constructed over the years, joining the island and the surrounding riverbanks into a cohesive network of walkways and cobblestone thoroughfares. During warm afternoons and quiet evenings, The townspeople enjoyed taking long, unhurried strolls along the water, admiring the timber architecture and the soft rustle of the river breezes. Over time, a charming local riddle emerged among the strollers, passing softly from neighbor to neighbor during their restful walks. People wondered whether it might be possible to design a continuous walking route through the city that would allow a person to cross every single one of the 7 wooden bridges exactly once, without ever doubling back or stepping onto any bridge a second time. It was a gentle puzzle born of leisure and curiosity, holding no grand commercial or military importance, but offering a pleasant mental exercise for anyone wandering beside the Pagel's peaceful shores. For years, citizens and visitors alike attempted to chart such a path, tracing endless loops on maps or stepping out across the wooden planks, only to find themselves repeatedly blocked or forced to retrace their steps, leaving the quiet mystery of the 7 bridges floating softly over the river like a morning fog. The persistent mystery of the city's pathways eventually reached the attention of one of history's most creative mathematical minds, who saw in the townspeople's gentle riddle the seeds of an entirely new way of understanding space. In 1736, along the Pegel River in Königsberg, Swiss mathematician Leonhard Euler solved the problem of the city's 7 wooden bridges by abstracting land and water into a serene arrangement of points and lines, creating the field of graph theory. Euler realized with quiet brilliance that the physical distances between the shores, the precise shapes of the land masses, and the scenic details of the riverbanks were entirely irrelevant to the solution. Stripping away all unnecessary geographic features, he reduced the entire city to a simple, elegant diagram where each distinct land area became a single point or node, and each of the 7 wooden bridges became a smooth line or edge, connecting those points together. By examining this peaceful framework, Euler observed that a continuous journey crossing every edge exactly once could only occur if the number of lines meeting at almost every point was even, allowing a traveler to arrive and depart without getting stranded. Because all 4 landmasses in Königsberg were connected to an odd number of bridges, Euler demonstrated with calm mathematical certainty that no such strolling path could ever exist, gently settling the city's long-standing puzzle once and for all. This profound act of abstraction proved that mathematics could study the pure architecture of relationships and connections, independent of physical measurement. New field of graph theory blossomed from this serene insight, eventually providing modern humanity with the foundational tools to design transportation networks, map electrical grids, and understand the vast web of global communications. As the quiet waters of the Pegel continue to flow beneath the sky, the story of the 7 bridges reminds us that even the most tangled problems of space and movement can be resolved into quiet clarity when viewed through through the soothing lens of abstract thought. As our long and peaceful journey through the story of human thought draws to its quiet close, it is comforting to look back across the centuries and watch how the simple act of counting gradually softened into an elegant language of harmony, symmetry, and rest. Far back in the deep mist of early history, before the rise of cities or written words, human beings reached out to the earth beneath their feet, gathering smooth river stones, carving light notches into ancient wooden tally sticks, and marking the soft clay of riverbanks to keep track of the slow, reassuring rhythms of their world. They marked the turning of the seasons, the gentle waxing and waning of the moon, and the steady return of morning light. With each passing millennium, these humble tallies began to blossom into something far deeper than mere accounting. Across ancient Mesopotamia, along the sunlit banks of the Nile, and through the quiet stone courtyards of ancient Greece, early thinkers began to notice that numbers were not just tools for measuring grain or livestock, but held intrinsic shapes, hidden proportions, and peaceful geometric relationships waiting to be discovered. When Indian scholars welcomed the concept of zero into the family of numbers, they gave humanity not only a tool of immense practical elegance, but a profound symbol of quiet stillness, a peaceful empty space where calculation pauses before beginning again. This zero traveled along winding trade routes into the heart of the Islamic Golden Age, where thinkers like al-Khwarizmi wove arithmetic into the subtle, balance-seeking art of algebra. In algebra, every equation became a gentle conversation seeking rest, an invitation for unknown quantities to find their place, until both sides settled into perfect, symmetrical balance. As the centuries unfolded, this mathematical language continued to simplify its symbols, allowing the human mind to look beyond chaotic calculations and perceive the quiet architecture resting beneath the surface of things. In every era, moments of sudden clarity revealed that complex problems often surrender to surprising simplicity when viewed with a calm and patient eye. One such quiet revelation took place in 1787 in a quiet classroom in Brunswick, where 10-year-old Carl Friedrich Gauss instantly summed the integers from 1 to 100 on his slate tablet by grouping them into 50 peaceful pairs of 101, while the other children set to work performing long, tiring chains of addition. Young Gauss saw the hidden symmetry hidden within the numbers, realizing that 1 and 100, 2 and 99, and every pair between them softly met at the exact same total of 101, turning a tedious ladder of addition into a single, serene moment of balance that allowed him to lay his slate down in total rest. That simple, elegant insight of grouping numbers into resting pairs reflects the central spirit of mathematics itself. Beneath every complicated problem lies a quiet, orderly truth waiting to settle the mind into stillness. As algebra developed through the work of generations of scholars across many continents, It offered humanity a way to step back from the noisy particulars of daily life and observe universal laws that remain constant and undisturbed across time. An algebraic variable is like a calm, open container, a gentle placeholder that holds space without impatience, waiting softly for whatever truth belongs within it. When we look at an algebraic equation, we are looking at a timeless structure of pure balance, where every movement on one side is met with a corresponding, harmonious movement on the other, ensuring that harmony is always maintained. It is deeply soothing to remember that these quiet mathematical principles are not abstract inventions of the human mind, but are the very same rules that shape the physical world around us as we prepare for rest. The fluid curves defined by algebraic equations describe the gentle arc of a falling raindrop, the delicate spiral of a seashell resting on a quiet beach, the geometric perfection of a snowflake drifting through cold air, and the slow, silent orbits of stars sweeping through the dark ocean of space. The same logarithmic spirals that structure distant galaxies also guide the unfurling of fern fronds in a quiet forest at dusk. Nothing in this vast mathematical tapestry is hurried, aggressive, or chaotic. Everything moves according to unhurried laws that ask nothing of us, operating silently whether we are awake or asleep. When we contemplate this enduring order, the mind is naturally invited to lay down its own burdens of analysis, memory, and effort. We begin to see that mathematics is not a rigid challenge to be conquered, but a quiet sanctuary of order, a peaceful landscape where every question carries its own quiet resolution. Every equation naturally seeks equilibrium, and every complex pattern eventually relaxes into comforting simplicity. In the stillness of the evening, as the sounds of the day fade away, these eternal principles continue their quiet, invisible work, keeping the cosmos in gentle equilibrium while the world slumbers peacefully. Now, as the stories of counting stones, clay tablets, geometric proofs, zero, and algebra drift softly into the background, we can let go of the numbers altogether and simply enjoy the peaceful quiet they leave behind. The long human quest to understand shape, quantity, and pattern has brought us to this moment of absolute stillness, where there are no more slate tablets to write upon, no more equations to balance, and no more sums to compute. The hand that once notched a bone in the pale light of a prehistoric campfire, the hand that drew geometric circles in the sand of ancient Syracuse, the hand that recorded the zero on soft parchment, and the hand that wrote algebraic symbols in quiet libraries have all completed their work, leaving us with a world that is orderly, predictable, and safe. The numbers themselves seem to grow soft and heavy, like autumn leaves resting quietly on the surface of a still pond. One by one, the tallies fade into the surrounding dark. The fractions merge smoothly back into wholeness. The unknown variables rest content in their quiet placeholders, and the total sum of all human inquiry reduces to a single, deep, tranquil breath. is nothing left to measure, nothing left to keep track of, and nowhere else to go. The universe holds its own balance without any effort from us, cradling everything in a gentle, unbreakable harmony. As your body sinks deeper into the warmth and comfort of your bed, allow your mind to drift like a lone pebble, sinking slowly through calm, clear water, settling gently onto the soft floor of a quiet sea. Let the steady rhythms of mathematics soothe you, the regular beat of your heart like a calm, rhythmic count, the slow rise and fall of your chest matching the natural cadence of the world around you. Everything is in its proper place. Everything is balanced, and everything is at peace. Sleep comes now as a natural resolution, wiping the slate clean, welcoming you into a deep, dreamless rest where all numbers fade into silence, leaving only quiet, peaceful darkness.